Hey there, and welcome. Right from the moment we can talk, we start asking questions. That constant, nagging curiosity, well, that's the real heart of science. So today, we're going to look at science a little differently. Not as some hard subject in school, but as this grand adventure that, believe it or not, we're all already on.
So, let's just start with the most important question of all. Have you ever just stopped, looked at something, and wondered, why? Why is the sky blue? Why does my toast always land butter side down? That one little word, why, is the spark for every single discovery ever made.
Yeah, exactly. Questions just like these. Looking up at the night sky and asking, why are those stars shining? Or, watching a garden and thinking, how does a flower even know when it's time to bloom? These aren't just questions for super smart astronomers or botanists. They're human questions. We've all asked them. And they're the first step on a really amazing journey.
Which brings us right to our first big idea, looking at science as an adventure that belongs to every single one of us. Seriously, it's not about memorizing a bunch of facts. It's about a way of thinking, a way of exploring. I mean, just think about that for a second. This definition doesn't say anything about labs or complicated math. It's about thinking, observing, and doing. It frames science as this active thing, a powerful tool that any of us can pick up and use to figure out the world.
Okay, so if science is this big adventure, what's our map? Well, a really great way to picture it is to think of science as a giant, never-ending puzzle. See, every single discovery is like snapping another piece into place in this massive, massive puzzle. But, and this is the really cool part, sometimes a new discovery shows us that a piece we put in place maybe years ago is actually in the wrong spot, and that forces us to rethink the whole picture. It's what keeps science moving and so exciting. All right, so if we're all solving this giant puzzle, we need a strategy, right? We can't just be guessing randomly. That strategy, that powerful tool we use to solve all these mysteries, is something called the scientific method. Now, I know this might look all formal and stuff, but it's actually super intuitive. It all starts when you observe something, anything. That makes you ask a question. Then you make a little guess about the answer. After that, you test your guess. And finally, you analyze what happened. Observe, question, guess, test, analyze. That's it. That's the loop of discovery. Okay, so right about now you might be thinking, this is all great for scientists in lab coats, but what does it have to do with me? Well, it turns out everything. You actually use this exact method all the time, probably without even realizing it. Let's just take a super simple, everyday problem. You're writing something down, and all of a sudden, your pen just gives up. It stops working. What's the first thing that pops into your head?
I mean, think about what you actually do. First, you observe the pen isn't writing. Then you ask the question, why? You make a quick guess. The ink is probably finished. Your test? You open the pen to check the little refill tube. And then you analyze what you see. It's empty. Your guess was totally right. Boom! See that? You just ran through the entire scientific method.
And it's not just pens, right? You do this all the time. When you're cooking and the dal boils over, you try to figure out why. You do it when your bike gets a flat tire and you're searching for that tiny little leak. You even do it when a light bulb burns out and you have to figure out if it's the bulb or maybe the light switch itself. It's just how we solve problems. So let's get to the big point here. The punchline, really. If you're using the exact same method that scientists use to solve problems, well, what does that make you? Just look at this. On one side, you've got what a professional scientist does. They ask questions, they make a guess, they test it, and they find an answer. Now look at the other side. That's you. You ask questions, make a guess, test it, find an answer. It's the exact same process. The questions might be different, sure, but the way you think about them, it's identical. And that's the big takeaway. This isn't about having a fancy degree or a title. Anyone, and I mean anyone, who uses this method of observing, questioning, guessing, and testing is, in that moment, working just like a scientist. You're a scientist in your own life every single day. You know, I just love this quote because it wraps everything up so perfectly. Being wise isn't about knowing all the answers. It's about being the person who never stops asking why. Being a wise person is the whole foundation of learning and discovery. So, I'm going to leave you with this one last thought. Now that you know you've got the toolkit of a scientist built right into your brain, what mystery in your world, big or small, are you going to get curious about?
What's the one thing you're going to be a wise person about today?
Hey, welcome to The Explainer. Today, we're going to take a little virtual nature walk. And you know what? We're going to uncover some of the hidden patterns in the living world all around us. And forget about complex jargon. We're cracking the code of the wild using just our eyes and, well, a little bit of curiosity.
You know, this simple observation from our source material, it is the perfect starting point for our journey. It's just a little reminder that even in the sounds we hear every day, there's this incredible variety of life just waiting to be noticed.
And of course, it's not just sounds, right? I mean, even in a park you've been to a million times, or just your own backyard, there's a staggering variety of plants and animals. And this beautiful, really complex variety, that's what scientists call biodiversity.
Okay, but how do you even begin to make sense of it all? I mean, with so much variety, how do we start to understand the relationships between all these living things? Well, it turns out we can start by learning a really simple way to group what we see.
All right, let's kick things off with plants. And you don't need a microscope or anything fancy to get started, just some simple observable features. We're going to use their size and the type of stem they have to start seeing some of these fundamental patterns. So check this out. What's really cool about this is how it gives us a simple little toolkit to classify pretty much any plant we come across. You've got your short herbs, like a tomato plant, right? Green, tender stem. Then you have medium-sized shrubs, like a rose, with that hard, woody stem that branches out near the ground. And of course, the big ones. Tall trees like a mango, with that thick, woody trunk and branches way up high.
But, okay, grouping by size? That's really just the beginning. If we look a little closer, there's a hidden connection, a kind of secret pattern that links a plant's leaves, its roots, and even the very structure of its seeds. It's pretty amazing.
So, you ready to play detective for a minute? The first clue is right there on the leaf. We're going to look really closely at the pattern of the veins, which is a characteristic scientists call venation.
Okay, first up, we've got this beautiful web-like pattern. You can see it so clearly on something like a hibiscus or a mustard leaf. This is what's known as reticulate venation. It seriously looks like a tiny, intricate net just spreading across the whole leaf.
And then you have the second pattern, which is completely different. Here, the veins run in these straight, parallel lines, side by side, all the way from the base of the leaf to the tip. Just picture a blade of grass or a big banana leaf. That's what we call parallel venation.
So here's the kicker. This is the crucial point. This incredible link. A plant's leaves are literally telling you a story about what its roots are doing underground. If you see a leaf with that net-like reticulate venation, it almost always has a single main taproot burrowing deep into the ground. But if you see those parallel veins, you're going to find a whole cluster of thin, fibrous roots instead. And this just brilliantly illustrates the whole system. See how it all connects back to the seed? Plants are basically divided into two huge families. You've got monocots, which have one seed part, those parallel veins and fibrous roots, and then you have dicots with two seed parts, reticulate veins, and taproots. It's a perfect, totally interconnected system.
Okay, that was cool, right? Now let's switch gears and move on to the animal kingdom. We're going to see how this same logic, this observe and group method, applies here too. Just like with plants, we can start to see all sorts of patterns once we know what to look for.
You know, we can group animals based on so many different things. Where they live, what they eat, their shape, their size. But for now, let's just focus on one of the most obvious and honestly fascinating features: how they move. And right away, it's pretty clear that different animals use these really specialized body parts to get around their environment. A goat, for example, uses its legs to walk and jump. A pigeon uses both its legs and wings to walk and fly. And a fish, of course, uses its fins to swim. Each one is perfectly equipped for its own way of life.
You know, all of this, it brings us to a much bigger, more profound idea. The incredible diversity we're seeing, it's not random, not at all. Every single feature, from the veins on a leaf to the wings on an animal, is the result of life perfectly adapting to its home. These special features, they're called adaptations. Think of them like unique tools that allow each plant and animal to survive and really thrive in its specific environment, whether that's a scorching hot desert or a freezing cold mountain peak.
Take a cactus, for example. It's got that thick, fleshy stem that's brilliant at storing water, an absolutely essential adaptation for the desert. Meanwhile, you look at a deodar tree up in the mountains. It has this conical shape and sloping branches. Why? Well, that's the perfect design to let heavy snow just slide right off. See? Two different plants, two totally different problems, and two perfect solutions.
And get this, we even see this kind of thing within the same species. A camel in a hot desert has long legs to keep its body away from that blistering hot sand, and it has one hump. But a camel in the cold, mountainous desert of Ladakh, it's got shorter legs for better stability and two humps for extra food storage during those harsh winters. Amazing, right? So, the specific place where any organism lives, whether it's an ocean or a forest, is called its habitat. And a habitat isn't just a location on a map, it's a complete life support system. It provides everything that organism needs to survive: food, water, air, shelter, the whole deal.
And we can basically classify these life support systems into two main types. First, you've got terrestrial habitats, which just means land-based, like forests and deserts. And then you have aquatic habitats, which are water-based, like rivers and oceans.
So, why does any of this matter? I mean, why should we care about the difference between a taproot and a fibrous root, or how many humps a camel has? Well, it matters because this incredible biodiversity, this intricate web of life, is both unbelievably precious and extremely fragile.
What happens is, when habitats are damaged, and this is often because of human activity, it sets off this dangerous chain reaction. Plants and animals lose their homes, they lose their food sources, and then their populations start to decline. This is a direct loss of the very biodiversity we've been exploring.
So, you see, at the end of the day, protecting these habitats isn't just about saving one particular species. It's about maintaining the entire rich tapestry of life on our planet. Every single organism, no matter how big or small, plays a part in that.
And that brings our journey to a close. But in a way, yours is just getting started, because the next time you step outside, you'll have the tools to see the world just a little bit differently. So, my question to you is, what will you notice now that you didn't before?
So what does it really mean to eat healthy? It's a question we all think about, right? But the answer is about so much more than just counting calories. It's about, really understanding our food, where it comes from, and how it actually fuels our lives. So let's dive into this idea of mindful eating.
And this isn't a new question, not at all. An ancient Sanskrit proverb asks it pretty powerfully. The answer it gives us, well, that's going to be our roadmap for this entire explainer. It suggests true health isn't just about what you're eating, but also how much, when, and even where your food is from. Okay, so that brings us to a really key word from that proverb, wholesome. But what does that actually mean, in the real world? What's the difference between a food that's wholesome and one that, isn't? Let's figure it out. To answer this ancient question with a bit of a modern twist, we really need to look inside our food. What's it actually made of? What are the fundamental bits and pieces that give us energy and, keep us going? Everything we eat, and I mean everything, from a simple piece of fruit to a big dinner, is made up of these building blocks called nutrients. These are the substances our bodies use for absolutely everything, growing, fixing themselves, and just doing every single thing, from breathing to thinking. All right, so you can kind of break down the major nutrients into two key teams. First up, you've got the energy givers. That's your carbohydrates and fats. Think of them like the fuel in your car. They power everything you do. Then you've got the bodybuilders, proteins. They're like the construction crew, essential for building us up and repairing any damage. Okay, so we've got our fuel and our construction crew. But what about our defense system, our security detail? What are the things in our food that actually protect us from getting sick? This is where the story gets really interesting. And this story just illustrates the point perfectly. I mean, can you imagine being on a ship for months and your body literally starts falling apart? That was the reality for sailors with this disease called scurvy. And the cure? It wasn't some complex medicine. It was just lemons and oranges. This case showed us the incredible power of a single missing nutrient, vitamin C. And here's another amazing example. There was this huge health crisis in the Himalayan regions, and scientists trace it all back to one single missing element in the soil and the food: iodine. And the solution was so simple, it's almost hard to believe. They just added a tiny bit of iodine to regular table salt. This one little change improved millions of lives.
So, these examples just reveal the awesome power of what we call protective nutrients. We're talking about vitamins like vitamin C and minerals like iodine. We only need them in tiny amounts, but without them, the consequences can be huge. They are literally the guardians of our health. So, we've identified all the key players, the energy givers, the bodybuilders, and the protectors. The big question now is how do we put them all together to create that wholesome diet the proverb was talking about? And this is the key, right here. A balanced diet isn't about finding one magical superfood. It's about getting the right combination of all the essential nutrients, plus things like fiber and water. And what's right for you isn't one size fits all. It totally changes depending on your age, gender, and how active you are.
Let's make this super practical. Let's compare roasted chickpeas or chana to potato wafers. Okay, so the wafers have way more calories and, whoa, look at the fat. But then check out the protein and dietary fiber. The chickpeas are just in a completely different league. This right here, this is the difference between empty calories and food that's packed with nutrients.
So that basically defines what we call junk food. It's high in energy, sure, but it's from sugar and fat, and it's critically low in everything else your body actually needs. Protein, vitamins, minerals, and fiber. Trying to build a healthy body by relying on these foods, well, it's just not a good strategy.
But mindful eating, it's not just about the nutrients. It's also about understanding the incredible journey our food takes before it even gets to us. It's about looking beyond our plate to the bigger picture. I mean, think about something as simple as a chapati or a piece of bread. Its journey starts with a farmer planting a seed. From there, it has to be harvested, processed, transported, packaged, transported again, and then finally sold in a shop. It's a pretty incredible chain of events that involves a ton of effort and a lot of distance. And that entire distance that your food travels, it actually has a name. It's called food miles. It's a simple idea that just measures the whole journey from the farm, the producer, all the way to you, the consumer. So why should we even care about food miles? Well, cutting them down has some huge benefits. For one, it means less pollution from all that transport. It means more support for our local farmers and communities. And, really important for us, it often means our food is fresher, which means it's healthier. It connects our own health to the health of our community and even the planet. And this brings us right back to where we started. Remember that ancient proverb? It advised eating food that's appropriate for the place. Now we can really see how that wisdom connects everything, from the nutrients in our food to global supply chains. So the next time you're shopping for food, just think about it. How can your choices help the whole system we've just talked about?
Hey everyone, and welcome! Today we're diving into something you see every day but maybe don't think much about. Magnets. Yeah, they seem simple, right? Sticking to your fridge, holding a bag closed, but the science behind them has guided explorers for centuries and, honestly, powers our world in ways you probably don't even realize. So let's get into it. To get started, let's picture this scene, okay? It's something a young writer named Reesma dreamed up. Imagine a trading ship, way back when, caught in a massive storm. The sky is totally blacked out with clouds, and the sailors, well, they are completely and utterly lost.
So what do? This was the big problem Resma had in her story. The sailor's main guide, the stars, were completely gone. Without them, how could they possibly know which way to go to get to safety? Well, the answer lies in a pretty amazing piece of ancient tech.
As it turns out, Resma discovered that for hundreds of years, travelers had a kind of secret weapon for navigating when the sky was cloudy, the magnetic compass. It's a really simple device that runs on this incredible, invisible force.
Yeah, long before we could manufacture the magnets you find in toys or on your fridge, people found these really special rocks out in nature and they called them lodestones. These things were basically nature's own magnets, and they were the key to unlocking travel across the globe. Okay, so to really get how a compass works, we've got to take a step back and ask a super basic question. What do magnets actually do? Like, what kind of stuff do they even stick to?
It's actually pretty simple. Certain materials, like iron, nickel, and cobalt, get pulled towards a magnet. So we call these, you guessed it, magnetic materials. Easy enough.
But then there's pretty much everything else. Things like wood, plastic, rubber, glass. A magnet completely ignores them. They're non-magnetic. So a magnet is actually really picky about what it interacts with. All right, so we know magnets attract certain metals, but here's the next question. Is that magnetic pull the same all over the magnet, or are some parts way stronger than others? This is the next big clue to understanding the compass.
Just imagine for a second we have a simple bar magnet, and we sprinkle a bunch of tiny iron filings all over it. What do you think would happen? Would they spread out evenly, or would they all clump together in certain spots?
And check this out. This slide shows us exactly what happens. The filings don't spread out evenly at all.
They practically pile up on the two ends of the magnet, and there's almost nothing in the middle. So these two special ends, right where the magnetic force is the strongest, those are called the poles of the magnet. And every single magnet, doesn't matter what shape or size, has two of them, a north pole and a south pole.
Now, this is absolutely crucial. You can't have a magnet with just one pole. It's impossible. If you take a bar magnet and snap it right in half, you don't get a north piece and a south piece. Nope. You get two brand new, smaller magnets, and each one has its own north and south pole. It's just a fundamental rule of the universe.
And believe it or not, this idea, the idea of two separate poles, is what finally gets us back to our lost sailors and solves their whole problem. How can a tiny little magnet help you find your way on a giant planet?
This right here, this is maybe the most magical thing about a magnet. If you let it hang and spin freely, say from a piece of string, it's not going to stop just anywhere. It will always, every single time, swing around and line itself up pointing north and south. And the reason why is just mind-blowing. Our entire planet, the Earth itself, acts like one gigantic bar magnet. So the north pole of your tiny little magnet is trying to point to the Earth's magnetic north, and its south pole is pointing to the Earth's magnetic south. It's this huge, invisible planetary connection.
Okay, so we know a magnet will line itself up with the Earth. But what happens when you bring two regular magnets close to each other? Do they always just stick together?
Well, there's a really simple rule for this, and you've probably heard it before. If you try to push two of the same poles together, like a north to a north or a south to a south, they'll push away from each other. They repel. But if you bring opposite poles together, a north and a south, they'll snap right together. Opposites attract. So, knowing these rules isn't just for science class. It lets us do some pretty cool stuff, like even build our very own version of that ancient navigational tool.
And this is something you can totally try at home. If you take a regular sewing needle and just stroke it with a magnet over and over in the same direction, you can actually turn that needle into its own little temporary magnet. Then you just pop it through a small piece of cork, float it in a bowl of water, and boom! You've just recreated the same basic tech that helped those sailors find their way home.
But a quick heads up about magnets. They might seem tough, but their magnetic power can be pretty fragile. If you heat them up or drop them or, hit them with a hammer, you can actually scramble their internal structure and make them weaker. So you got to treat them with a little bit of care to keep them strong.
So think about how far we've come, from a ship lost in a storm all the way to the fundamental laws of push and pull. These super simple rules, opposites attract, likes repel, and a free magnet always points north. They're the secret behind everything from a simple compass to super fast levitating trains. The principles are simple, but what you can do with them? That's endless. So now that you know the rules, what would you build?
Welcome to the explainer. You've heard the question, right? How long is a piece of string? It sounds like a joke, but it's actually one of the most fundamental questions in all of science. Today, we're going to dive into the surprisingly tricky world of measurement, and we'll do it by following the story of some very curious friends.
Our story kicks off with this ancient instruction, char angula, or 4 fingers width. Simple enough, right? But wait, whose 4 fingers are we talking about? A little kid's? A giant's? And right there, that seemingly simple phrase opens up a huge problem. If we can't even agree on the width of a finger, how can we possibly build anything or do any kind of science at all?
So, here's our game plan. We're going to start this journey with a simple piece of cloth and, believe it or not, end up defining what motion itself is. We're going to tackle what we're calling the handspan problem, see why we desperately need a universal standard, and discover how these basic ideas are the absolute bedrock of modern science.
All right, let's jump right in and meet our main character, a really curious student named Deepa.
So Deepa starts noticing something kind of weird. The shopkeeper at the market uses this stiff metal rod. The tailor uses a soft, flexible tape. And our own mother just uses her fingers. I mean, think about it. 3 different people, 3 totally different tools, all trying to do the exact same thing, measure length. This gets her and her friends talking, and it sparks a big question. Which way is actually the right way? All this curiosity about how people measure things leads the friends to try a little experiment of their own, right there in the classroom. They decide to use a unit of measurement that's, well, as old as people are, the handspan, or as Deepa's mom calls it, a balisht. The plan seems super simple. Everybody measures the exact same table using their handspan, and they just write down what they get. What could possibly go wrong?
Well, here's where it all gets a little chaotic.
They all measure the exact same table, but just look at these results. Anish gets a little over 13, Padma gets exactly 13, and Hardeep gets a full 14 handspans. This isn't just a tiny difference in numbers, they fundamentally disagree on the length of the table. And this, of course, leads them to the most important question of the day. If the table itself didn't change size, why on earth were all of their measurements so different? And then it hits them. The problem wasn't in their counting. The problem was the unit itself. A handspan isn't a fixed thing because everyone's hand is a different size. So to get the same answer, they don't just need to measure better. They need a standard, a single unchanging unit that's the same for everyone, no matter where you are.
So how did the entire world solve this exact same problem? Well, by creating a universal standard, which is kind of like a common language for measurement that everybody could agree on.
The solution is this, the International System of Units, or SI for short. You probably know it as the modern metric system. And this is the reason that a car part built in Germany fits perfectly into a car being assembled in Mexico. It guarantees that a meter in Mumbai is the exact same length as a meter in Paris. It just gets rid of all the confusion and makes global science and trade possible.
Now for length, the main unit, the base unit, is the meter. And this is where the system is just brilliant. You can easily scale it up to kilometers to measure the distance between cities, or you can scale it way down to centimeters and even millimeters for really small stuff.
But the real magic of this system is how simple it is. Everything is based on the number 10. A kilometer is 1,000 meters. A meter is 100 centimeters. Now, compare that to a system where you've got 12 inches in a foot and 5,280 feet in a mile. Yikes. The SI system just makes moving between units so incredibly easy.
So, great, we have our universal standard. But here's the thing, a standard is only as good as the person using it. You know, just because you own a guitar doesn't make you a rock star. And just having a ruler doesn't mean you're going to get an accurate measurement. You have to know how to use it right.
First things first, and this is the most important rule, placement. Your ruler or your tape measure has to be pressed right up against the object, and it has to be perfectly parallel to the edge you're measuring. Any kind of angle or gap, and your reading's going to be wrong. Simple as that.
Okay, now here is a super clever solution for a really common problem. What do you do if your ruler is old and the end is broken off so you can't see the zero mark? You don't have to throw it out. Just line up the start of the object with any other clear number, like the 1 centimeter mark, for example, then measure to the end and just subtract that starting number from your final reading. It's a great little trick that guarantees an accurate measurement every time.
Okay, so we've pretty much mastered how to measure the length of an object. But what about measuring something you can't exactly hold, like distance? Well, we can take that same core idea of a standard and apply it to something more abstract, like describing exactly where something is.
So, the friends get into another debate. Which is farther away, the school or the garden? It seems like a simple question, but they just can't agree. And then they realize they're actually all kind of right. The answer totally depends on a huge piece of missing information. Where are you starting from?
And that brings us to this absolutely crucial idea, the reference point. To describe a position, just saying a distance isn't enough. You need a fixed, shared starting place that everyone agrees on. Without that reference point, saying something is 2 kilometers away is totally meaningless. 2 kilometers away from what?
You see this idea out in the real world all the time. Another one of the friends, Padma, is on a bus trip. She looks out the window and sees this kilometer stone. It's telling her that her current position is 70 kilometers away from her reference point, which, in this case, is the city of Delhi. A little while later, she sees another stone. And look, the number has changed. Now she's 60 kilometers from Delhi. That change in her position, relative to that fixed reference point, well, that change is the very definition of what it means to be in motion. She's not just at a new spot, she is actively moving.
And that very idea, this concept of a changing position relative to a reference point, is what brings all of these pieces together for our final concept.
So here it is. This is the official definition of motion. It's not just about moving, it's about an object's position changing over time when measured against a fixed reference point. Think about it for a second. Without a standard unit, like a meter, we can't accurately say how much the position changed. And without a reference point, we have no way of knowing if the position changed at all. See, all those earlier ideas had to come first. And you can see all these different kinds of motion everywhere you look. A kid's park is actually a perfect laboratory for this. A child zipping down a slide, that's linear motion. A merry-go-round spinning, that's circular motion.
And a kid on a swing going back and forth, that's oscillatory motion.
And this whole journey leaves us with one last, kind of mind-bending question to chew on. A car is full of passengers. Are those passengers in motion? Well, compared to the driver next to you or the seat you're sitting in, you're perfectly still. But compared to a tree on the side of the road, you're flying by. So what's the answer? Well, the answer depends entirely on your reference point, and that takes us right back to where we started.
All right, today we're putting on our detective hats. We're going to dive into an investigation into the world that's literally all around us. It's a mystery that's super simple on the surface, but actually goes surprisingly deep.
No, seriously, just for a second, look around you, right now. You've probably got a phone, maybe a desk, a window, a cup of coffee, but have you ever stopped to think, what is all this stuff? Like really, that's the big question we're going to crack today.
Okay, so every good detective story starts with the first clue, right? For us, that clue is all about looking at the things we see every day and figuring out what they're actually made of.
Think about it. A pen isn't just a pen. It's actually a bunch of different things put together. You've got plastic for the outside, a little bit of metal for the tip, and of course the ink inside. Or a book, it's paper, ink, and glue. So it turns out, pretty much every single object is just a collection of one or more, well, let's call them materials.
And that's our first key term, a material. It's super simple. A material is just any substance that's used to create an object. This is like the ground floor of our investigation. Wood, glass, plastic, clay, yep, those are all materials.
So, okay, it's one thing to say that everything is made of materials, but how do we tell them apart? How do we know glass isn't wood? Well, as detectives, we look for clues, right? And for materials, these clues are called properties.
Let's start with an easy one, how it looks. Specifically, is it shiny? That shine has a fancy name, luster. So you've got your lustrous materials, like shiny metals. Think gold, or even a brand new piece of iron. And then you've got the non-lustrous stuff, the dull things, like paper or wood. It's a really basic visual clue that helps us start sorting everything out.
All right, next clue, hardness. Basically, how does it feel? Can you squish it? Can you scratch it? Some materials, like a rock or a piece of iron, are really tough to compress. We call those hard. But other things, like a sponge or an eraser, are super easy to squish or scratch. Those are soft. It's all about how much it pushes back.
Okay, this next one is kind of fun. Imagine you're playing hide and seek. Where you decide to hide has everything to do with this next property. And the question is simple. Can you see through it?
So if you can see through something perfectly, like you're looking through a super clean window and can see everything outside crystal clear, that material is called transparent. You know, like glass or water or even the air. And yeah, definitely a terrible hiding spot.
But what about those materials where you can kind of see through, but not really? You see light, you see blurry shapes, but you can't make out any details. That's called translucent. A frosted glass door in a bathroom is a perfect example. You can tell if someone's on the other side, but that's about it.
And of course, the championship hiding spot is behind something that is opaque. These are the materials you can't see through at all. Think a solid brick wall or a big tree. So there you have it, transparent, translucent, and opaque. 3 really important ways we sort materials based on how light gets through them or doesn't.
Okay, let's take our investigation out of the playground and into the kitchen. Have you ever stirred sugar into your tea or lemonade and watched it just disappear? That little magic trick is actually our next big clue. This whole idea is called solubility. When we put that sugar in water and stir it up, it vanishes because it's soluble. It dissolves. But now, what if you tried the same thing with sand? It would just sink right to the bottom, right? That's because sand is insoluble. It's a super simple test, but it tells us a whole lot about a material.
So far, we've been looking at all the things that make materials different from each other. Shiny, dull, hard, soft. But now we get to a really cool part. What about the properties that everything has in common? And I mean everything. It turns out there are 2 universal rules that apply to, well, all the stuff.
Okay, universal rule number 1 is mass. Now, mass is just a scientific word for the amount of stuff packed into an object. It's what makes something feel heavy. It's literally a measure of all the tiny little atoms and molecules that make it up.
Let's make this super practical. Imagine you have 3 identical cups. You fill them up to the exact same line, but one has water, one has sand, and one has pebbles. Which one's going to be the heaviest? The pebbles, right? That's because the pebbles have more mass packed into that same amount of space. And if we were to actually weigh them, we'd be measuring that mass directly.
And that brings us to universal rule number 2, volume. This one's even easier. Volume is all about space. It's just the answer to the question, how much room does this thing take up?
Just look at these two tumblers. They're exactly the same size, but one is almost full of water and the other is only half full. The water in the fuller tumbler is taking up more space, right? So we just say it has a greater volume. It really is that simple.
All right, team, case report time. We've gathered all our clues. We know everything is made of materials. We know those materials have different properties that help us tell them apart. And, this is the big one, we know that everything, no matter what, has two things in common, mass and volume. I think it's time to solve this mystery.
So, what's the one word? What is the single, big picture, scientific term for anything that has mass and takes up space?
The answer is matter. That's it. That's the solution to our whole investigation. You, me, the chair you're on, the air you're breathing right now, even the stars way up in the sky, it's all matter. It's the one word that describes all the physical stuff in the entire universe.
So why go through all this trouble? Why does sorting and classifying even matter? Well, because it's something humans have always done. It's how we make sense of a really big, complicated world. And believe it or not, we've been doing this for a very, very long time. Yeah, this is not some new scientific idea. Get this. 8,000 years ago, our ancestors were already figuring out which clays were best for making pottery. The Harappan civilization got really, really good at it. And ancient systems like Ayurveda in India had this incredibly detailed way of classifying all physical matter using 20 different properties. It's like it's built into us to want to sort and understand the world.
And that brings us right back to today. We understand materials so well now that we can invent brand new ones from scratch, like plastic. But that leads to one last really tough question for our investigation. When you think about all its properties and its huge impact on the world, has plastic been a boon, a massive help, or a bane, a source of huge problems? That's a big one to think about. Thanks for joining me on this detective story.
Hey, is the water you're touching hot or is it cold? Seems like a pretty simple question, right? But what if I told you your own hands could lie to you, that they could give you two completely different answers for the exact same water? Let's dive into why our senses can be so deceiving. So, here's our game plan. We're going to start with a really cool trick that proves you just can't always trust your sense of touch. Then we'll get into the tools that give us the real story, from the thermometer in your medicine cabinet to the science behind your daily weather forecast.
All right, first up, your senses can lie. You know, we do it all the time. Dip a finger in the bathwater or touch a forehead to check for a fever. It feels like a pretty reliable instinct, but can we really trust what our skin is telling us?
This is a really important question because we rely on touch constantly, right? But when it comes to temperature, our hands can be surprisingly bad at their job. In fact, I can prove it to you with a super simple experiment. Okay, just picture this. You've got 3 bowls of water. You put your right hand in some nice warm water and your left hand in ice cold water. Let them sit there for about a minute. Then you plunge both hands into that middle bowl, which is just plain old room temperature water. So, what do you think happens next? And here's the wild part. Your warm hand now feels that room temperature water as cold. Meanwhile, your cold hand feels the exact same water as warm. Your brain is getting 2 totally contradictory signals from the same source. And that proves it. Our sense of touch is relative. It's not absolute. It's easily fooled. So if our hands are so unreliable, how do we get a straight answer? Well, that brings us to our next section, finding a much better way to measure how hot or cold something really is. And that reliable measure is called temperature. See, it's not just a feeling, it's a number. It's basically a measure of how much the tiny little particles in an object are moving and jiggling around. More energy and more jiggling means a higher temperature. Less energy, lower temperature. It's simple, reliable, and it won't lie to you like your hands just did. And the hero of this story is, of course, this device, the thermometer. It's built to give us that precise, reliable measurement, and it takes all the guesswork and sensory confusion right out of the equation. Okay, on to section 3. Let's start with the thermometer we all know. And, well, the one we all know, the clinical thermometer, the one we use to keep an eye on our health. What's so special about a clinical thermometer is that it's a specialist.
It's not designed to measure boiling water or freezing ice. No, it has one job and one job only: measuring human body temperature. Its range is kept intentionally narrow, focusing only on the temperatures a living person can actually have. So, if you're using the Celsius scale, that gold standard for a normal, healthy body temperature is considered to be 37 degrees. This is the number doctors pretty much everywhere use.
But you might be a lot more familiar with this number, 98.6 degrees Fahrenheit. It's the exact same temperature as 37 Celsius, just measured on a different scale that's commonly used in places like the United States. And, using one correctly is absolutely key to getting an accurate reading. Always wash the tip, pop it under your tongue, and wait for that beep. Oh, and this is important. Never hold it by the tip because the heat from your fingers could actually mess up the measurement. All right, now for section 4. Let's meet the clinical thermometer's bigger, more versatile cousin, the laboratory thermometer. This thing is the workhorse of science and industry.
So let's put them head to head. The differences are pretty huge. A clinical thermometer has that tiny, specific range for the human body. A lab thermometer, it can measure a massive range, from way below freezing to above boiling. And here's a really key detail. You take a clinical thermometer out to read it, but you have to read a lab thermometer while it's still in the substance to get an accurate number.
So why does getting temperature right matter so much? Well, in our final section, let's connect all these dots to the world around us, from the daily weather report all the way out to the stars.
This quote from the incredible Indian scientist Anna Mani just hits the nail on the head. Getting the measurement right is everything. An inaccurate number isn't just useless, it's actually misleading. It can send you down a completely wrong path. And Anna Makani, who was known as the weather woman of India, really lived by this idea. Her work creating accurate weather instruments was a total game changer for India's scientific community. And that expertise eventually helped the nation become a leader in fields like renewable energy. It just goes to show you, progress starts with a good, reliable measurement. We all see the impact of this every single day. The maximum and minimum air temperatures on the weather report, those are crucial data points. They don't just tell you whether to grab a jacket, they guide huge decisions for entire industries, like farming.
And all this leaves us with one final mind-bending question. Science tells us there is a coldest possible temperature. It's called absolute zero, where all molecular motion just stops. But is there a hottest? According to our best understanding, nope. There's no upper limit. From the core of our sun to exploding supernovas, the universe's potential for heat seems to be infinite. It's a question that really pushes the boundaries of what we know. Thanks for joining me for this one. Have you ever just looked at a glass of ice water and thought, wait a minute, is that solid block of ice really the same thing as the water swirling around it? I mean, they seem so different, right? One's hard, you can pick it up. The other just flows right through your fingers. It's a question that sounds simple, but it's actually the key to unlocking some of water's most amazing secrets. So let's put on our detective hats and solve this watery puzzle.
This is the exact same puzzle a character named Thirav from our source material was wrestling with. His argument is pretty straightforward. Ice is hard, water is fluid, you can't hold them the same way, so they must be different things. And honestly, that's a perfectly logical conclusion to come to, isn't it? It really makes you wonder if our everyday observations are telling us the whole story. So, that's our mission today. We're going to become water detectives. We're going to follow the clues. We're going to explore some simple but really powerful ideas. And we're going to solve a few mysteries about water that you've probably noticed your whole life, but maybe never really stopped to think about. I mean, if you look at the evidence laid out like this, Thirov's case is pretty convincing. Ice is hard. Water flows. Ice doesn't really splash. Water, oh, it definitely does. And here's the big one. An ice cube keeps its shape, but water, it just takes the shape of whatever you pour it into. It's really easy to see why you might think they're two completely different substances. But here's where the plot thickens. The story doesn't just end with ice and water. See, there's a third, kind of invisible identity, water vapor. Each of these states of water plays by its own set of rules. You've got the solid state, ice, holding its own shape. The liquid state, taking the shape of its container. And then the gas state, water vapor, which just expands to fill up whatever space it's in. It's all H2O, just behaving in these totally different ways.
All right, detective, let's get to work on our first case. We've all seen this happen. It rains in the morning, there are puddles everywhere. But by the afternoon, they've vanished. Poof! Where did all that water go? It's a classic childhood question, and it's our first big clue in understanding water's incredible disappearing act.
Okay, so a common theory, and a really logical one, is that the water just soaks into the ground. And yeah, on a playground, that's for sure part of what's happening. But is it the whole story? What about a puddle on the solid pavement? Or, a dish that you've left out to dry? Let's investigate.
Okay, picture this really simple experiment. We take a spoonful of water and put it on a solid steel plate. We can flip the plate over, it's bone dry on the other side, so the water is definitely not seeping through. And yet, if we just wait long enough, we come back, and the water on top of the plate is just gone. So if it didn't go down, where did it go?
It went up. That's right. This invisible escape act has a name. It's called evaporation. The liquid water literally transformed into its gas state, that water vapor we talked about, and just floated away into the air. And there you have it, the solution to mystery number 1. The puddle didn't just sink, it also took flight.
And once you know about evaporation, you start seeing it everywhere. It's the reason your wet clothes actually get dry on the clothesline. It's why a mopped floor doesn't stay wet forever. It's even why sweat disappears from your skin, and why hand sanitizer feels like it just vanishes as you rub your hands together. It's the same cool trick every single time. Okay, now that we've cracked the case of the disappearing puddle, let's move on to another classic. Mystery number 2, the sweating glass. You know the scene. You pour a nice cold drink on a hot day, and just a few minutes later, the outside of the glass is covered in these little water droplets. Where in the world is this water coming from? A really logical first guess, right, is that the glass must be a little bit porous, and tiny amounts of water are somehow leaking through from the inside. It makes perfect sense. The water's inside, and now there's water on the outside. But is that what's really going on? How could we prove it? Well, here's the killer clue. If we were to put that glass of ice water on a really sensitive digital scale, we'd discover something amazing. The weight doesn't stay the same, and it certainly doesn't go down. The weight of the glass actually increases. That means water's being added to the glass from the outside, not leaking from the inside. So where did that extra water come from? Well, it was hiding in plain sight the whole time. It was in the air around us. This process is the total opposite of our last mystery. This is condensation. The invisible water vapor that's always in the air touches the cold surface of the glass, it cools down really fast, and transforms back into liquid water. And just like that, mystery solved.
So we've seen water turn into a gas, that's evaporation, and we've seen that gas turn back into a liquid, that's condensation. Now these aren't just isolated little tricks, they are the 2 most important moves in a massive planet-wide dance called the water cycle.
So here's how that dance plays out all over the globe. First, evaporation lifts water from oceans, lakes, and rivers, sending it way up into the atmosphere. Then, high up where it's much colder, condensation takes over, turning that vapor back into tiny little droplets that all clump together to form clouds. And finally, when those droplets get heavy enough, we get precipitation. The water comes back to Earth as rain or snow, and it's ready to start the whole journey all over again. Okay, time for our final mystery, and this one reveals a really cool, really practical side effect of everything we've been talking about. Why does water stored in a traditional clay pot, sometimes called a matka, stay so wonderfully cold, while water in a metal bottle or a plastic jug gets warm pretty fast? So here's the secret. Unlike a steel pot, the clay is actually a little bit porous. That means a tiny amount of water seeps through all these microscopic holes to the outer surface. And what does water do when it's exposed to the air? That's right, it evaporates. Now here's the key. For evaporation to happen, it needs energy, and it pulls that energy in the form of heat away from the pot, which leaves the water inside much cooler. It's basically natural air conditioning. And this brings everything right back home to our own bodies. This is exactly why we sweat. Our body puts a thin layer of water on our skin. When we stand in front of a fan, that moving air speeds up the evaporation of the sweat. And as it evaporates, it pulls heat away from our skin, and we feel cooler. So the next time you feel a nice breeze on a hot day, you can thank the amazing power of evaporation. So the next time you take a sip of water, just pause for a second. Think about its incredible journey. That exact same H2O might have once been locked inside a glacier or evaporated from the Pacific Ocean, floated in a cloud over a continent, and rained down on a mountain. It's been on this endless cycle for billions of years, and after you drink it, its great escape begins all over again. What do you think its next journey will be?
All right, let's dive in. We're going to talk about something you do all the time, probably without even realizing it. I'm talking about separation, unmixing stuff. It sounds simple, right? But from your own kitchen to these huge industrial plants, it's fundamental to how pretty much everything works.
Yeah, of course you have. See, we're separating things constantly. And those little actions, believe it or not, are the perfect entry point for understanding some really, really clever science that we use to sort, purify, and basically create all the materials that make up our world.
And you know what? This isn't just some newfangled scientific concept. The idea of separating what's useful from what's, useless, the good from the bad, that's ancient. I mean, just listen to this incredible verse from the poet Kabir. It shows that figuring out how to separate things is, in a way, about understanding wisdom itself. Pretty deep, right? Okay, so to help us explore all these different methods, we're going to follow two awesome, super curious siblings, Molly and Volley, on their summer vacation. As they travel all across India, their journey is going to uncover all this amazing science that's just hiding in plain sight.
So their first stop is their Nani's house in Haryana. And picture this. They're right in the heart of farmland, surrounded by these huge fields, big piles of grain. You can almost smell it, right? This is where their first lessons in separation are going to kick off.
So the first big puzzle Molly and Volley come across is, how do you separate different solids from each other? I mean, solids mixed with other solids. The solutions they discover are honestly super simple. But as you're about to see, they're also incredibly effective.
First up is the one we all know. Hand-picking. It's exactly what it sounds like. They see their family carefully picking out tiny stones from grains of rice. And then, of course, at lunch, Volley totally calls out her brother Molly for doing the exact same thing, picking the black peppers out of his pulao. It's the same principle, right?
Then, when they're out in the fields, they see these farmers just whacking bundles of stalks against a big wooden log. And their uncle explains, oh, that's called threshing. It's this really powerful, kind of physical way to just knock all the valuable grains loose from the stalks.
Okay, but wait. Threshing creates a new mix-up, right? Now you've got the heavy grain all mixed in with this light, flaky husk. So what do? Well, the solution is just genius. Farmers stand up on a platform, they let the mixture fall, and the wind, just the wind, carries away the light husk while the heavier grains fall straight down into a neat pile. This amazing, clever process is called winnowing.
So, just before they hit the road again, their mommy is in the kitchen making some methi puri for their train ride. And to get the flour just right, she uses a sieve. You've seen this, right? It separates the superfine flour from the coarser bran. That's sieving. And it's the perfect way to separate solids of different sizes, whether it's flour in a kitchen or, on a huge scale, sorting rocks and sand at a construction site.
All right, time for the next leg of the journey. Molly and Volley are heading to the coast, and this brings up a totally new kind of problem. I mean, what do you do when the solid you want isn't just mixed with a liquid, but totally dissolved in it? So they get to Ahmedabad, and a visit to the historic Sabarmati ashram gets Molly's wheels turning. He starts thinking about the famous Dandi March, the Salt March. And that leads him to ask a really great question. Where does salt actually come from? Like, how do we get it out of the ocean?
Well, the answer is pretty amazing. You basically let the sun do all the work for you. See, seawater gets collected in these huge, shallow pits right by the coast. Then you just wait. The sun and the wind team up, the water slowly disappears into the air, and what's left behind? Piles of pure, solid salt.
So the science behind this is a process called evaporation. It's basically the kind of magical way a liquid turns into a gas or a vapor. And it is the perfect method for getting a solid out when it's been completely dissolved in a liquid, just like salt in seawater. And we're off again. Next stop, Puducherry. Here in their Dada and Dotty's kitchen, something super simple, just making a cup of tea, is about to become another amazing science lesson.
So their grandfather shows them there are two ways to deal with the tea leaves. Option 1, you can just let the leaves settle to the bottom and then carefully pour the tea off the top. Option 2, you can use a strainer.
One way is super quick, but you might get some leaves in your cup. The other takes an extra second, but gets the job done perfectly.
Okay, so that first method, it's actually a two-step process. First comes sedimentation. That's just the fancy word for the heavier tea leaves settling at the bottom. Then comes decantation. That's the part where you gently pour the liquid off the top. Like I said, it's fast, but yeah, you might end up sipping a few tiny leaves.
Now, that second method with the strainer, that's called filtration. The strainer is your filter, right? It traps the solid stuff, the tea leaves, but lets the liquid tea flow right on through. It's way more precise, and honestly, it's the same basic idea behind your coffee maker, your car's oil filter, and even giant water treatment plants.
All right, we're on the final leg of the journey, but Molly and Volley aren't done yet. They're about to discover a couple more specialized but seriously cool ways to separate things.
So they're at a dhaba in Madhya Pradesh, just kicking back with some buttermilk, and they learned about churning. You know, when you take curd or cream and just agitate it like crazy. Well, all that stirring makes the lighter bits of butterfat clump together and float, separating from the heavier buttermilk below. It's an amazing process that takes one thing and turns it into two delicious things, butter and buttermilk.
And for their last stop, in Shillong, they run into a carpenter who's in a bit of trouble. He's accidentally spilled a whole box of iron nails into a giant pile of sawdust. Oh no! But the kids have this brilliant idea. They find a magnet, run it through the sawdust, and poof! Like magic, the magnet pulls out every single nail, leaving the sawdust behind. That, my friends, is magnetic separation.
Wow. What an incredible trip, right? So after traveling all across India with Molly and Volley, what's the big takeaway? Let's pull all these amazing ideas together and see how they fit into the bigger picture.
So here it is. This is the awesome separation toolkit that they've built along the way. You've got hand picking, threshing, winnowing, sieving, then there's evaporation, sedimentation and decantation, filtration, churning, and finally, magnetic separation. They've shown us so many clever ways we unmix our world, often without a second thought.
And get this, these aren't just little kitchen tricks. Think about that magnet the kids used to find a few nails. Now, imagine that on a massive scale. That's exactly what we do. Giant cranes with huge electromagnets use that exact same principle to lift tons of scrap iron and steel out of junk piles for recycling. It's a perfect example of how a simple idea can have a gigantic impact.
So here's my challenge to you. As you go about your day, just look around. The next time you strain pasta, shake some salt on your food, or even just take a breath, your nose hairs are a filter, by the way, think about the science of separation. Because now that you know what to look for, I promise you are going to start seeing it absolutely everywhere.
Have you ever just looked at something and wondered, is that alive? Well, today, we're going to dive into that very question by taking a closer look at the amazing tiny wonders all around us.
Okay, I know it sounds like a weird riddle. What on earth could a quiet little snail shell have in common with a super annoying, buzzing mosquito? But stick with me, because this contrast is actually the key to a much, much bigger question. It seems like it should be simple, right? But you'd be surprised. The line between what's living and what's not can get a little blurry. So today, we're going to be detectives. We're going on an investigation to figure out what it really means to be alive. And our whole investigation kicks off with that snail shell I mentioned, all thanks to a simple question someone asked while out on a walk.
This is it. This one question from a kid named Avahari is our perfect starting point. How can something that looks totally lifeless, just sitting there, actually have a living creature inside? To figure that out, we need to gather some clues.
So let's get into it. Biologists have basically come up with a checklist, 7 key things that all living creatures have to do. These are the telltale signs of life.
First up, movement. Now, this isn't just about a dog running or a bird flying. Think about a sunflower in a field slowly turning its head to face the sun throughout the day, or a vine, day by day, wrapping itself around a fence. It might be slow, but it's definitely movement. Then, of course, you've got growth. This one's pretty easy to get. We've all had that moment where we realize our favorite jeans don't fit anymore, right? That's because all living things get bigger over their lifetime. And to power all that growth, you need fuel. That's nutrition. It doesn't matter if you're a plant soaking up sunlight or a wolf hunting for dinner. Every single living thing needs to take in energy to survive. Now here's where it gets really cool. A car moves, right? So it checks that first box. But Does a car grow? Nope. Does it need food? Not in the same way a pigeon does. This shows us something super important. To be considered alive, you can't just check one or two boxes. You gotta check them all. Okay, our fourth sign is respiration. And just a heads up, this is way more than just breathing in and out. It's the whole chemical process of turning food into energy. For us, yeah, that involves our lungs. But plants do it too. They breathe through these tiny little pores on their leaves. And, what goes in? Well, it's gotta come out. Excretion is all about getting rid of waste products. For humans, that can be sweating. For a plant, those little drops of water you sometimes see on the tip of a blade of grass? That's actually the plant getting rid of extra water. Living things are always reacting to the world around them. You touch a hot stove and you pull your hand back instantly, without even thinking. That's a response. A really cool plant example is the touch-me-not plant. The moment you touch it, its leaves fold up. How cool is that? And finally, we have reproduction. This is, how life keeps going. Living things make more of their own kind, which makes sure their species continues on to the next generation. Okay, so we've got our 7-point checklist. Now let's put it to the test with a real biological puzzle, the case of the sleeping seed. I mean, really think about it. You hold a dry little bean seed in your hand. It's not moving. It doesn't look like it's eating anything. It's not doing, anything. So is it just a non-living thing, like a little pebble? Or is there something more going on? To solve this mystery, scientists set up a simple but really smart experiment. They took 4 pots with bean seeds and gave them each different conditions. One got sunlight but no water. Another got way too much water. A third was in the dark. And the 4th pot? It got the just right combination of sunlight and moisture. The big question was, which one would wake up? And after about 2 weeks, the results were crystal clear. The only seeds that germinated were in pot D, the one with the perfect conditions. By sprouting, they proved they could respond to their environment, that's a check, and they definitely started to grow, another check. So the verdict is in. That seed was never non-living. It was just dormant. It was alive the whole time, like a tiny package of potential, just waiting for the right moment to kick off its life cycle. But what about when life doesn't just grow bigger, but completely transforms itself? Let's check out some of the most dramatic changes in the animal kingdom. This is called metamorphosis. Take a look at this. The life of a mosquito is like a 4-act play. It starts as a tiny egg on the water, hatches into this wriggling little larva, changes into a tumbling pupa, and then, boom, emerges as the flying adult we all know. 4 totally different forms, but all one single life. And for another absolutely incredible story of transformation, all we have to do is look in a nearby pond. The frog's journey is just as wild. It goes from a jelly-like egg to a fish-like tadpole, breathing underwater and swimming with a tail. Then it starts to grow legs while its tail literally shrinks away, becoming a froglet. And finally, it becomes an adult frog that can live both in the water and on land. It completely rebuilds its body to live in a new world. So, from a quiet snail shell to a dormant seed to a tadpole that becomes a frog, what have we seen? We've seen that life isn't just a state of being, it's a dynamic process. It's all defined by this shared set of actions, growing, changing, and responding to the world. This amazing, unbroken cycle is happening all around us, all the time. So the real question is, now that you know the signs to look for, what are you going to notice? A tiny little plant pushing its way through a crack in the sidewalk? A bird building a nest? Life is everywhere, just waiting for us to see it. Thanks for joining this explainer. Okay, so let's jump right in. We're going to follow along with 2 kids, Bhumi and Surya, as they go visit their grandmother's village. But get this isn't just some simple holiday trip. Oh no, it's actually a journey to find all these amazing and sometimes totally invisible treasures that nature gives us, things we need to survive. So, their grandmother, Aji, she kicks things off with this really simple but kind of profound question. She asks them, what are these treasures of nature and how do they really make our lives better? And that question, well, that's what sets up our whole journey here. So let's stick with Bhumi and Surya and see what answers they dig up. All right, so where do you even start on a journey of discovery like this one? Well, they start with the most basic thing for life, something we all completely take for granted, mainly because, well, you can't see it. We're talking about the air we breathe.
I mean, think about it. You take something like 20,000 breaths every single day. But when was the last time you actually stopped and thought, hey, what am I actually breathing in right now? What is this invisible stuff that's so important for us to even exist?
So if you actually look at what air is made of, it's kind of surprising for a lot of people. It's mostly nitrogen. But the part that's absolutely crucial for us, that's the 21% oxygen. And here's some perspective for you. We can go for weeks without food, days without water, but only a few minutes without oxygen. It is the one non-negotiable fuel for our bodies.
But, air is rarely just still, right? When it gets moving, we call that wind. And it can be anything from a nice, gentle breeze to a crazy, destructive storm. But the idea behind it is exactly the same. It's just air in motion. And that motion, that's a seriously powerful source of natural energy. So Aji shows the children this perfect little example, a simple pinwheel, or a firki as they call it. The moving air pushes the paper and makes it spin. It's that simple. Now just imagine that same idea but scaled way up. That's exactly what a massive wind turbine is. It's just a giant pinwheel, really, generating clean electricity. What a brilliant way to harness one of nature's treasures. Okay, next up is water. And we call Earth the blue planet for a reason, but that's kind of deceiving. Sure, over 70% of it is covered in water, but listen to this. Less than 1% of all that water is actually fresh water that we can use for drinking or for farming. That's it. This incredible scarcity makes every single drop precious, and it really drives home why saving water isn't just a nice thing to do, it's an absolute necessity for our survival. Okay, so we've covered the invisible stuff like air and the flowing water. Now the kid's journey of discovery turns downward, to the solid gifts from the earth itself. We're talking forests, soil, and rock, the very foundation of our world. Now, forests are so much more than just a bunch of trees standing together. They're these super complex, living communities. Think of them as vibrant ecosystems, providing food, materials for shelter, and a home for this incredible web of wildlife. They are true living treasure chests of biodiversity. And right beneath our feet is another one of these critical resources, soil. And hey, it is not just dirt. It's a complex, living thing that's formed when rocks break down over thousands, even millions of years. I mean, think about that timescale. Without this incredibly slow-forming treasure, growing our food, well, agriculture as we know it just wouldn't be possible. All right, now let's talk about the energy that literally built the modern world we live in. Everything from our cars to the electricity in our homes. For a long time, our civilization has been powered by a very specific, very potent, and pretty controversial type of natural treasure. We're talking about fossil fuels, and their name tells you their ancient story. They are literally the stored up energy of ancient life. We're talking about the fossilized remains of plants and animals that got transformed over millions and millions of years by incredible heat and pressure deep inside the earth. And this is probably the single most important thing to understand about them. That whole creation process, it takes millions of years. It works on a geologic timescale, not a human one. So once we burn them, they're gone. For all practical purposes, they're gone for good. So this huge difference in timescales, a tree growing versus coal forming, that brings us to what is probably the most important idea in this whole explainer. Every single natural resource we've talked about so far can be sorted into one of two really important categories, renewable or non-renewable. So first, let's talk renewable resources. These are the treasures that nature can basically make more of, all on its own, within a reasonable amount of time, like a human lifetime. The sun is always going to be shining, the wind is going to keep blowing, and new trees can always grow from seeds. And then, on the other side of the coin, you've got the non-renewable resources. These are the finite ones. There's only a certain amount of them in the ground, and once we use them up, they're gone. At least on any timescale that matters to us humans. So, let's sort all the treasures we've talked about. On the renewable side, you've got the things that are part of a constant cycle, right? Air, water, sunlight, forests. And on the non-renewable side, you got the stuff we have a limited supply of. Fossil fuels, minerals, and you know what? Even soil, because it takes so long to form. Understanding this one single difference, it changes everything about how we need to think about managing our planet.
Okay, so as Bhumi and Surya's visit comes to an end, their trip back home gives them this really stark, real-world lesson about what happens when we rely on these different kinds of treasures.
Remember the village? That was a world that ran mostly on renewable treasures, right? The air was fresh, the water was clean, the forests were alive. The whole place just felt clean, cool, and sustainable.
But the second they get back to the city, everything changes. The whole sensory experience just shifts dramatically. They can smell the smoke in the air from all the cars and factories, and that's the direct result of burning all those non-renewable fossil fuels. The difference between these two worlds, you just can't deny it.
And this really brings us to a final, powerful quote from Mahatma Gandhi. He said, "Earth provides enough to satisfy every man's need, but not every man's greed." And that's just the perfect way to look at everything we've just talked about. It leaves us with the ultimate question, doesn't it, for all of us? How do we choose to live? Are we using nature's treasures to meet our needs, or are we letting our greed destroy them for everyone who comes after us?
You know, for as long as we've been, well, human, we've looked up at the night sky and just wondered. So today, we're going to take this whirlwind tour of our cosmic neighborhood. We'll go from the familiar patterns our ancestors saw in the stars all the way to the truly mind-boggling scale of the universe itself.
And that feeling, it's totally universal. I mean, picture this. Two kids, Youngdal and Dorje, living in Ladakh, India. They're under some of the clearest, darkest skies on the entire planet. And the stars they see? They're the same ones their ancestors saw, lighting up the sky and inspiring that exact same feeling of wonder.
So what are we really looking at up there? It sounds like a simple question, right? But the answer? Oh, the answer is huge. See, you're not just looking at a bunch of random sparkly things. You're looking at history, at ancient navigation tools, and you're looking at our own address in a cosmic neighborhood that is just staggeringly vast. So you ready? Let's dive in and break it all down.
Okay, so our journey starts, well, right here, with our feet planted firmly on the ground. Everything we know, everything we've learned about the universe, it all started by just looking up and trying to make some sense of the view from our own planetary backyard.
And this quote, it really gets to the heart of it. Think about it. Ancient people didn't just see a chaotic mess of lights. No way. They saw hunters and animals, gods and heroes from their stories. They literally connected the dots, turning the cosmic chaos into a map that felt familiar, a map that had meaning.
And these patterns, of course, are what we call constellations. Now, fast forward to today, and astronomers have basically mapped the entire sky. They've divided that whole imaginary dome above us into 88 official regions, each one named for the pattern inside it. So every single star you can see belongs to one of these 88 constellations. It's like a complete official map of the heavens. Pretty cool, right?
And listen, this map wasn't just for telling cool stories around a campfire. It was a critical tool. For sailors crossing these huge empty oceans or travelers in the desert, these stars were their GPS. They were quite literally a guide to survival, a lifeline.
So what made this whole system work so darn well? Well, it turns out some stars are incredibly reliable. If you're in the northern hemisphere, there's one star that's the MVP, the pole star or Polaris. It just seems to hang there in the sky while everything else spins around it. And you can find it yourself. It's super easy. Just find the Big Dipper, look for the two stars at the end of the cup, and just shoot an imaginary line north. That's it. For centuries, that one star has been a steady, trustworthy guide.
All right, so for thousands of years, those faraway, fixed stars were our map. But while all that was going on, something else was happening much, much closer to home, with objects that didn't stay fixed. So, it's time to zoom in. Let's leave those distant signposts behind and meet our immediate cosmic neighbors in the solar system.
First up, you got to talk about the big boss of the solar system, right? The sun. Now, our sun is a star, just like all those billions of others you see at night. But why does it look like this giant blazing ball of fire while all the other stars are just tiny little specks of light? Well, it all comes down to one thing: distance. The sun looks so big and bright simply because it's our star. It's right here in the neighborhood.
And when I say it's close, close is a very relative term here. We're talking about 150 million kilometers away. This number is so important, actually, that astronomers gave it its own special name, 1 astronomical unit, or AU. It's basically our yardstick for measuring things in the solar system. Okay, so hold on to that number, because this next one is gonna blow your mind. It shows just how incredibly isolated we are. So if the distance to our sun is our yardstick, right, 1 AU, the very next star, Proxima Centauri, is about, get this, 269,000 of those yardsticks away. That is a mind-boggling amount of pure empty space between us and our next-door neighbor.
Okay, so orbiting our sun, we've got the 8 planets. You can kind of split them into 2 groups. First, you've got the 4 small, rocky guys on the inside. Mercury, Venus, our home, the blue planet Earth, and of course Mars, the red planet. Then you jump over this huge asteroid belt, and you get to the 4 big guys, the gas giants, Jupiter, Saturn, Uranus, and Neptune.
But here's the thing. The solar system isn't just this neat and tidy collection of 1 star and 8 planets. Oh no. It's actually a pretty messy place, filled with all this other cool stuff, kind of like the leftover scraps from when the whole system was built billions of years ago.
So what are we talking about? Well, for starters, moons. Or natural satellites if you want to get technical. We've got 1, Mars has 2, the big guys have dozens. You've got asteroids, which are mostly hanging out in a belt between Mars and Jupiter. And of course, you've got dwarf planets. Yeah, I'm looking at you, Pluto. It was reclassified in 2006 because astronomers realized it was just the first of a whole new category of worlds out there.
And then you have the comets. These are like these dramatic visitors from the super far out parts of the solar system. They're basically dirty snowballs, and when they swing in close to the sun, they heat up and create that amazing tail. You've probably heard of the most famous one, right? Halley's Comet. It swings by to put on a show for us every 76 years or so.
Okay, you ready? Time for one final zoom out. We've toured our home, but what's beyond our little cosmic cul-de-sac? Let's go for the biggest picture possible and see where we really fit in the grand scheme of things.
So picture everything we've talked about so far. The sun, all 8 planets, the asteroids, the comets, the whole shebang. All of that, it's just one tiny speck inside a gigantic spiral of stars we call the Milky Way galaxy. In India, it's known as the Akasha Ganga. And you know that faint milky band of light you can see in a really dark sky? That's it. That's us, looking at our own galaxy from the inside out.
And here it is, the final leap, the one that really puts it all into perspective. Our galaxy, the Milky Way, with its hundreds of billions of stars, is just one galaxy in a sea of countless others, each one with its own billions of stars and probably its own planets. Honestly, the scale it's just almost impossible to wrap your head around.
Which, of course, brings us to the biggest question of all. When you look at all that unimaginable vastness, you just have to ask, right? Are we alone? Scientists are looking, they're searching for an answer, but for right now, we just don't know. It is maybe the greatest mystery there is, and it just goes to show, no matter how much we figure out, there's always so much more to explore out there.
You know, when you think of science, what's the first thing that pops into your head? For a lot of us, it's probably a dusty old textbook, maybe some complicated formulas to memorize. But what if I told you that's, well, completely wrong? Today, let's forget all that and rediscover what science is really all about. And trust me, it's a thrilling invitation to just be curious. And this quote right here, it just hits the nail on the head. Science isn't a list of rules. It's an invitation to question everything, to try things out, to perform experiments, and to just explore the world with brand new eyes. So that's exactly what we're going to do in this explainer. We're going to peel back all those layers of what we think science is and get right to its core, that amazing thrill of discovery that all starts with a little bit of curiosity.
All right, let's begin. Our first stop, an invitation to explore. And this is all about seeing science not as a class, but as a grand adventure where your own curiosity is the only compass you really need.
I love this metaphor. We're kind of taught that learning is this straight, predictable line from point A to point B. But real discovery? Oh, it's so much messier and more beautiful than that. It's a lot more like the flight of a butterfly or a paper airplane. It zigs, it zags, and it follows wherever your curiosity decides to take it. And this slide shows you just how powerful that can be. I mean, think about it. It all starts with something so simple, right? A paper plane gliding through the air. But that simple little observation sparks a huge question. Hey, how can we do that? How can we fly? And that one question, that's what kicks off this massive journey of discovery, from studying how birds fly to engineering the jumbo jets that cross oceans today. It all comes back to one simple moment of curiosity.
Okay, so if curiosity is the spark, what's the engine? Well, that brings us right to our next section. Science is a process. And the main idea here is a real game changer. It's not about what you know, it's about how you think. This slide just lays it out so perfectly. On one side, you've got the old view, the one most of us probably learned in school. Science is just a big book of facts you have to memorize for a test. But the real view, oh, that's where the magic is. It's a way of thinking, a method that doesn't just put up with questions, it absolutely thrives on them. It welcomes them. And this way of thinking is fueled by much bigger, juicier questions. We're moving beyond what is this, and we start asking how does this work? We stop at what happened and dig deeper to why did it happen that way? These are the kinds of questions that blow the doors wide open to whole new worlds of understanding. And what's so cool is that this mindset isn't just for one subject. Which brings us to a world of questions. We're about to see how this kind of curious thinking connects literally everything, from the tiniest atoms to the biggest galaxies. Let's do a little rapid-fire tour, okay? Take a simple question, like, why are some fruits sour? Boom, that's chemistry. You're suddenly exploring acids and pH levels and how they interact with your taste buds. Or how about this one? What kind of materials make a lamp glow? Just like that, you've jumped into the world of physics, asking questions about electricity, resistance, and conductivity. The questions can get personal, too. How do our bodies change as we grow? Now you're diving headfirst into biology, exploring the incredible, complex processes of life itself. And it's not just about us humans. Ask, how did plants get their food? And you've just asked another huge biological question that unlocks the secrets of photosynthesis and really how entire ecosystems work. We can even go massive with these questions. How does the Earth cast a shadow in space? Bam! Now you're asking a question about astronomy, thinking about light, planets, and orbits. Do you see the pattern here? Chemistry, physics, biology, astronomy, they're all just different flavors of the same thing, curiosity. Which brings us to our final, and honestly, probably the most important section. Now you ask. Because the real engine of science, the most powerful tool in the universe, isn't in some high-tech lab. It's right inside your own head. It's your curiosity. So, to get that curiosity muscle warmed up, we're going to try this really fun exercise called Question the Answer. The idea is super simple. I'm going to give you an answer, and your job is to work backwards and come up with a great question for it. It's all about thinking like a scientist. Because this is the absolute truth. Great scientists aren't just remembered for the answers they found. They're remembered for the incredible, groundbreaking, sometimes crazy questions they dared to ask in the first place. That's always the starting point. Ready? It's your turn. Here's your first answer, because the cat's teeth were crooked. Okay, so what in the world is the question? Could it be, why couldn't the cat play the trumpet? Or maybe, why did the vampire run away screaming? Let your mind go wherever it wants. Let's try another one. The answer is, just add some milk. So what's the question? Maybe it's, how do I make my coffee less bitter? Or what's the secret ingredient for the perfect mac and cheese? What do you think? All right, here's one for all my fellow nerds out there. The answer is, don't panic. I have my towel. The question could be something like, the spaceship is about to explode and we're being sucked into a black hole. What do you say to calm me down? And for our last one, an absolute classic. The answer is 42. Now, sure, you could go with the obvious sci-fi reference. But what else could it be? Maybe, how many times did you have to refold that map before it fit in the glove box? Or, what's 6 times 7? And that's really what this is all about. Science isn't some destination you arrive at. It's a direction you choose to go in. It's the simple, powerful process of looking at the amazing world around you and having the courage to ask, why? So I'll just leave you with this final thought. What amazing question will you ask today?
Ever wanted to write a secret message? You know, one that's totally invisible until you reveal it? Well, today we're going to figure out exactly how to do that. We're stepping into a school science fair to solve a mystery using some chemistry that's actually surprisingly simple.
So imagine this. 2 siblings, Ashwin and Kirthi, walk into their science fair, and they're handed a blank sheet of paper. Someone sprays it with the liquid, and bam, a message just appears out of nowhere. Now, it looks like magic for sure, but by the end of this, you'll know exactly how it all works. All right, to solve any good mystery,
You need clues. And our very first clue, the one that helps us tell different substances apart, comes from a simple but really powerful tool, a color change. This is step 1 for decoding our chemical secret.
So how do scientists even begin to sort out, well, everything in the world? One of their key tools is this special little strip called litmus paper. And you can see here, when they tested a bunch of common household items, the paper changed color. This let them sort everything into 3 neat little groups, A, B, and C.
That litmus paper is a perfect example of something called an acid-base indicator. You can think of it like a chemical detective. It's basically a substance that changes its color to tell you what kind of chemical environment it's in. Pretty cool, right?
So, those 3 groups we got from our litmus test, they actually have official scientific names you've probably heard before. We're cracking the code now, and we call them acids, bases, and neutrals.
Let's break down the basic differences. Acids, which were the substances in Group A, often taste sour. Think about lemon juice, and they're the ones that turn blue litmus paper red. On the flip side, you have bases from Group B. They often feel kind of slippery or soapy, and they do the exact opposite. They turn red litmus paper blue.
And this brings us to a super important safety point, okay? While we might know that things like vinegar are acidic and sour, there is a hard and fast rule in science. You never, ever taste an unknown chemical to figure out what it is. That's exactly why we have these amazing colorful indicators.
So let's put it all together. Group A, with things like lemon juice and vinegar, those are our acids. Group B, which has stuff like soap and baking soda, those are our bases. So what about Group C? The ones like tap water or sugar solution that didn't change the litmus paper at all? Well, we call those neutral.
Now here's what's really cool. You don't need a fancy lab to find these little chemical detectives. Nature is just full of them. And you can totally expand your toolkit by making your own indicators right from your own kitchen. I mean, check this out. You can just take some red rose petals, you crush them up, add a bit of hot water, let it sit for a few minutes, and then you just filter out the petals. That beautiful colored water you have left, that's it. It's a natural acid-base indicator.
And here you can see it in action. If you add an acid, like lemon juice, to this rose indicator, it turns this vibrant red. But if you add a base, like a soap solution, it shifts over to green. It's just a super clear visual signal of the chemistry that's happening. You know, here's another fantastic example from the natural world. Turmeric. The source material had this great observation. If you've ever gotten a yellow curry stain on a white shirt and then tried to wash it with soap, you might have been totally shocked to see it turn bright red. It's not a new stain, it's just science.
And the reason is that turmeric is a natural indicator. It stays yellow in acidic or neutral stuff, but the second it touches a base, like the soap you're using to clean that stain, it has this dramatic color change to red.
Okay, so we know what acids and bases do all by themselves. But what happens when you mix them together? This is kind of the plot twist in our story. It's this key idea called the balancing act.
You see, when an acid meets a base, they do this cool chemical reaction called neutralization. They basically cancel each other out. And what you're left with are 2 brand new neutral things, water and a type of chemical called a salt. And it also gives off a little bit of heat.
This one single idea, neutralization, is the key that unlocks not just our science fair mystery, but a ton of everyday problems too. This is the moment, right here, where science solves the case.
And once you know what to look for, you start seeing it everywhere. That nasty sting from an ant bite? That's an acid, which you can soothe or neutralize with a base like baking soda. Farmers use a base like lime to neutralize acidic soil so their crops can grow better. Even factories use it to neutralize their waste before it's released, which protects all the fish and plants in our rivers. Which brings us right back to where we started. We have all our clues now, right? We know about bases, we know about natural indicators like turmeric, and we know how they react with each other. We are so ready to solve the case of the appearing message.
And here it is. The big secret was to first write the message with a clear, basic solution, something as easy as soap water, and then let it dry. It's totally invisible. Then the volunteer at the science fair just sprayed the paper with a turmeric solution. The yellow turmeric indicator immediately reacted with that invisible, basic soap writing, turning it red and making the secret message appear right before their eyes.
So in the end, this just goes to show you that science isn't just for labs.
It gives us the tools to understand all the magic that's happening all around us, from our laundry rooms to our backyards. Which really just leaves us with one final question to think about. What other everyday magic is really just science waiting to be explained?
Have you ever really stopped to think about how a simple torchlight works? You know, you just flick a switch and boom, there's light. Well, today, we're going to metaphorically take that everyday object apart, piece by piece, to really understand the fundamental magic of electricity. I mean, it's such a common thing, right? We barely even give it a second thought. But there's this simple kind of magical thing happening. In total darkness, with just one little click, you can create light. So, how's that even possible?
That is our big question for today. How does this thing actually work? What is going on inside that little plastic or metal case? We're about to solve this mystery together, one step at a time.
Okay, so to solve any mystery, you've got to start at the source. That light isn't just coming from nowhere. It needs energy. It needs power. So let's go find the heartbeat of this torch.
All right, let's do this. Imagine we're unscrewing the back of the torch right now. As that cap comes off, we can see the few simple but absolutely crucial parts that make this whole thing go.
And here it is, the power source itself. We call this an electric cell. You can think of it as a little self-contained packet of chemical energy, just waiting to be turned into electricity. All that potential is organized between 2 points, the positive terminal, which is that little metal cap on top, and the negative terminal, that flat metal disc on the bottom. Now, a lot of torches need more, juice than a single cell can provide. And that's why you so often see 2 or 3, or even more of them all lined up, positive end to negative end. When you combine cells like this, you've officially created what we call a battery, which gives you a stronger or longer-lasting source of power.
Okay, so we've got our power. Awesome. But that energy is totally useless if it's just sitting inside the battery, right? So how do we get it from the battery all the way to the little lamp? Well, it needs a path. It needs an electrical highway to travel on.
And you know what? Creating this path is surprisingly simple. If you take one wire and connect it from one end of the cell to the lamp, and then you take a second wire from the lamp back to the other end of the cell, you create a complete loop. The moment that loop is finished, bam, the lamp glows.
This complete unbroken loop, well, it has a name. It's an electrical circuit. And here is the absolute key takeaway. For it to work, the path has to be a continuous, unbroken loop. The electric current has to be able to flow from the positive terminal through the lamp to make it light up and all the way back to the negative terminal.
And this really just says it all, doesn't it? If there's no complete path, there's no flow of current. And if there's no current, there's no light. It is that simple.
Right, but a torch that's always on isn't very useful, is it? We need to be in control. We need a way to open and close that electrical highway whenever we want. And that, my friends, is the job of the switch. It's actually a really beautiful and simple mechanism. When you flip that switch to on, you're literally closing a physical gap inside, which completes the circuit. The highway is open, the current flows, and the lamp lights up. Then you flip it to off, and you create a gap, breaking the path. The current gets blocked, and the light goes out. On, off. Simple as that. Now let's talk about the highway itself. Why are the wires made of metal, and why are they always covered in plastic or rubber? Well, the materials we use are just as important as the path itself. They're basically the rules of the road for our electric current. Just think about different everyday materials. If we put a metal key into our circuit, the light would stay on. Why? Because metal is a conductor. It lets electricity flow through it super easily. But what if we used a wooden stick or a rubber eraser? The light would go right out. These materials are insulators. They block the flow of electricity. And that is exactly why wires look the way they do. The inside is made of a conductor, usually copper, which acts as that perfect highway for the electricity. But the outside is coated in an insulator, like plastic. That coating keeps the electricity on its path, and probably more importantly, it protects us from getting shock. And here is the crucial safety takeaway. Our bodies are also conductors of electricity. This is exactly why we need those insulated coatings and why we have to handle all electrical devices with care and respect. Seriously, safety first, always. So we've completely deconstructed a simple torchlight. But here's the incredible thing. These basic principles don't just apply to torches. They apply to, well, everything electronic. And to talk about them, engineers and scientists needed a universal language.
I mean, can you imagine having to draw a super detailed picture of a battery and a lamp every single time you designed a circuit? It would be impossible. So that's why engineers developed a shorthand, a set of simple, standard symbols for each component. Here you can see the symbols for a cell, a lamp, and a switch in both its on and off positions.
The reason this is so powerful is that it creates this shared language. An engineer in Tokyo can look at a circuit diagram drawn by a colleague in Berlin and understand it instantly. It's a universal way to communicate these ideas. And that really is the big idea here. The principles of having a complete path, a power source, and a controller aren't just for torchlights. They are the absolute bedrock for every single electronic device you use, from your phone to a supercomputer. So, we've mastered this tiny circuit that creates light in your hand. The question I want to leave you with is this. How do these same simple rules scale up to power not just one little lamp, but our homes, our cities, and the massive electrical grid that connects our entire world? It all starts right here with these basics. Thanks for joining the explanation.
Hey everyone, and welcome. Ever stop to think about what our world is actually made of? I mean, really made of. From the phone in your hand to the air you're breathing right now, it all comes down to some really basic materials. And that's exactly what we're jumping into today, the amazing world of metals and nonmetals.
Okay, so to get us started, let's picture this. We're following two students, Yashwant and Anandi, on a trip to a local ironsmith's workshop. You can almost feel the heat from the furnace, right? You hear that clang, clang, clang of the hammer on the anvil. And right there, in the middle of it all, is a block of iron, glowing this incredible red-hot color, just waiting to be shaped. So, Anandi sees the smith take that glowing piece of iron and start hammering it into the shape of an axe, and she asks this just perfect question. She's like, wow, you can beat iron into a flat shape. Can we do that with other stuff? And you know what? That one simple question is the spark for everything we're going to explore. Why can you shape some things, while other things just fall apart? All right, to answer Anandi's question, we've got to look at what makes these materials special. Let's dive into their physical properties. You can think of them as their superpowers.
So, let's do a quick thought experiment. Imagine you've got a hammer. First, you hit an iron nail. What happens? It probably flattens out, right? Okay, now, what if you hit a piece of coal with that same hammer? Yeah, totally different story. You already know it's just going to shatter into a million little pieces. Well, that thing the ironsmith was doing, that first superpower, it has a name, malleability. It's just a fancy word for the ability to be hammered into thin sheets without breaking. And we see this all the time. Think about the aluminum foil you wrap your leftovers in, or even those super thin silver foils they sometimes put on sweets. That's malleability in action.
And if we actually did this experiment, the results are, well, they're pretty black and white. The iron nail flattens, the aluminum piece flattens, but the coal, it breaks into pieces. The lump of sulfur, same thing, shatters everywhere. This really nails down a huge difference. Metals are malleable, and nonmetals are what we call brittle. Okay, superpower number 2 is called ductility. This one is incredible. It's the ability of a material to be stretched out or drawn into a wire. The most common example is probably the copper wiring inside our walls. But get this, it's also how they make the ridiculously tiny, complex wiring inside our phones and computers. It's a huge deal. And if you want to know just how wild this can get, check this out. Take just 1 single gram of gold. That's tiny, smaller than a pea. You can stretch that 1 little gram into a wire that is 2 kilometers long. That's just mind-blowing, isn't it? And for our last physical superpower, we've got something called sonority. It's simple, really. Think about the sound a coin makes when you drop it on the floor. It has that clear, ringing sound, right? Now, what if you drop a piece of wood? Just a dull thud. That ringing sound is a special property of metals. It's exactly why we make bells out of metal and, well, not out of wood. Okay, so we've covered the things you can see, bend, and hear. But that's not the whole story. Some of the most important properties are kind of hidden. Let's talk about their hidden talents for conducting heat and electricity. Let's go back to Yashwant and Anandi. Imagine they do this super simple experiment. They take a cup of hot water and stick 2 spoons in it, 1 metal, 1 wood. They wait a couple of minutes. What happens when you touch the ends of the spoons? You know this one. The metal spoon's handle is hot, but the wooden one is still cool to the touch.
And that little test shows us something fundamental. Metals are good conductors of heat. They let heat travel through them easily. Nonmetals, on the other hand, are poor conductors. We also call them insulators. And this is why we design things the way we do. Your frying pan is metal, so it can get hot and cook your food, but the handle is plastic or wood, so you don't burn your hand picking it up. Makes perfect sense.
And guess what? It's the exact same story with electricity. If you hook these materials up to a simple circuit with a light bulb, you see the same pattern. Copper wire, the bulb lights up. Iron nail, yep, lights up. But a piece of coal or a lump of sulfur? Nothing, no light. They just don't let that electricity pass through.
All right, so we've spent a lot of time talking about what makes a metal a metal. Now let's flip the script and take a closer look at the other team, the nonmetals. So in a nutshell, nonmetals are pretty much the polar opposite of metals. Instead of shiny, they're usually dull. Instead of being malleable, they're brittle. They break easily. They can't be drawn into wires, and as we just found out, they're terrible conductors of heat and electricity. We're talking about stuff like carbon, sulfur, oxygen, phosphorus, the list goes on. Okay, so that's the physical stuff, how they look and feel. But what about their chemical personalities? How do they behave when they mix with other things? Let's find out by looking at what happens when they meet something they run into all the time, the air around us.
I mean, everyone knows about rust, right? You leave your bike or some tools out in the rain and, you know the deal, it gets that flaky, reddish-brown stuff all over it. But here's the key thing to remember. Rust doesn't happen with just water or just air. You absolutely need both of them together for iron to rust.
But then there's this, the Iron Pillar of Delhi. This thing is an absolute marvel. It's been standing outside for over 1,600 years through rain and sun, and it has almost no rust. It's just an incredible piece of history that shows how unbelievably skilled ancient Indian metalworkers were.
So this brings us to a really important chemical rule. When a metal, like iron, reacts with oxygen, it creates something called a metal oxide. Now, these metal oxides have a specific chemical personality. They are basic. If you remember from chemistry class, basic is kind of the opposite of acidic. They're two sides of the same coin. And you can probably guess where this is going. When a nonmetal, like sulfur, reacts with oxygen, it forms a nonmetal oxide. And here is the big reveal. These oxides are acidic. This is one of the most fundamental chemical differences between metals and nonmetals. One group makes bases, the other makes acids. It's a clear dividing line.
So, we've talked about all these properties, physical and chemical. But the big question is, so what? Why should you care? Well, let's bring it all home and see why these materials are so incredibly important in our everyday lives.
You know, it's easy to focus on the flashy, strong metals, but we absolutely cannot forget about the nonmetals. They are, quite literally, the stuff of life. Think about it. Oxygen, we need it to breathe every second. Carbon, it's the building block of, well, us, and all life on Earth. Nitrogen is in the fertilizers that grow our food. Chlorine purifies our water. Iodine is used on cuts. These things aren't just nice to have. We couldn't exist without them.
And that kind of leaves us with a really cool final thought to chew on. Metals build our world, our buildings, our cars, our tech. But nonmetals build us, our bodies, our food, the very air we breathe. So here's my question for you. Which one do you think is actually more important? Something to think about. Thanks so much for tuning in.
Hey, welcome. Today, we're basically becoming detectives. You know how all around us things are constantly changing? Stuff is melting, or burning, or growing. But what's really going on? We're going to dive in and uncover the science behind all these everyday transformations.
I mean, think about it for a second. An ice cube melts into water, but it's still, water, H2O. But when a piece of wood burns, it turns into ash and smoke. It is definitely not wood anymore. So what is the fundamental difference here? That's the big mystery we're cracking today.
All right, let's open our first case file, Physical Changes. And really, the subtitle says it all. This is all about a makeover. It's a new look, but the stuff itself, it stays exactly the same.
Okay, so here's the official definition. A physical change is when you're just messing with properties like shape, size, or state. You can squish it, tear it, freeze it, boil it, but at the end of the day, you haven't actually created a brand new substance.
Let's do a super quick test right now. Imagine you take a piece of paper. You fold it up into a sweet little airplane. You've totally changed its shape. But then what happens when you unfold it? Yeah, it's a bit crumpled, but it's 100% still paper. Its actual identity didn't change one bit.
And you see this exact same principle everywhere. If you crush a piece of chalk, you just have tiny pieces of chalk. You boil water, it turns into steam. But that steam can easily turn right back into water, right? It's the same deal with inflating a balloon, chopping up some veggies for a salad, or melting an ice cube in your drink. The actual stuff isn't changing.
So if there's one thing to remember for physical changes, it's this. Super simple. The stuff is still the same stuff. No matter how different it looks on the outside, its chemical identity is totally untouched. Now let's check out our next case file, which is a whole different ballgame.
And now for case file number 2, chemical changes. Okay, this is where it gets really cool. We are not talking about a simple makeover anymore. Oh no, we are talking about a complete, total transformation.
So, let's put these side by side. This is the absolute key difference. Physical change, same substance, just looks different, and you can often reverse it, right? Like freezing water back into ice. But a chemical change? You create a brand new substance with totally new properties, and usually there's no going back.
And here's the formal take. A chemical change just means a chemical reaction has happened. The original ingredients have literally been taken apart and put back together in a new way to form something completely different. It's like you've baked a cake. You can't unbake a cake and get your flour and eggs back, right? Think about that classic experiment you might have done in the kitchen, mixing vinegar and baking soda. The second they touch, you get this crazy instant reaction. You can just hear that fizzing and bubbling and see all those gas bubbles forming. That's your first major clue that something new is happening.
And that fizzing is the evidence. That's not just air. That's the creation of a brand new substance, carbon dioxide gas. The original vinegar and baking soda are gone. They've been replaced by something totally different. That, right there, is a chemical change in action.
Okay, let's zoom in on probably one of the most dramatic chemical changes there is. We're going to do a special report on the science of fire, or what scientists like to call combustion.
So for combustion, for a fire to happen, you need 3 things. You can think of it as the fire triangle. First, you need fuel, something like wood or paper. Second, you need oxygen, which luckily is all around us in the air. And third, you need heat, but not just any old heat.
You need enough heat to hit what's called the ignition temperature. That's the specific point where a substance just says, okay, I've had enough, and bursts into flame all on its own. For paper, that famous temperature is 451 degrees Fahrenheit. Once you hit that mark, the reaction kicks off.
So the really important thing to get here is that burning isn't just making something hot. It's a full-on chemical change that is completely transforming that fuel. The wood or paper is chemically reacting with oxygen and creating totally new things. Ash, smoke, gases like carbon dioxide, and you can never ever turn that ash back into wood.
All right, pop quiz for you. What about a burning candle? Think about it. The wax melts, which, well, that seems like a physical change. But there's a flame, and we just said fire is a chemical change. So what is it? Is it one, the other, or maybe both?
Okay, let's break this case down. Part 1 is actually pretty straightforward. The solid wax gets hot and turns into a liquid. That's just a change of state, right? Solid to liquid. It's still wax. So the melting part, absolutely a physical change.
But, and here's the cool part, the wick actually soaks up that liquid wax, and the intense heat turns it into a gas or a vapor. And it's that wax vapor that's actually burning. The vapor reacts with oxygen in a chemical change, and that's what gives us the light and heat. So a burning candle is, beautifully, both changes happening at once. So now that we've cracked the case on physical versus chemical changes, let's zoom out. Let's look at the bigger picture and see how these two processes are shaping literally everything in the world around us. This chart here really helps pull it all together. Check out that last column, reversibility. It's a huge clue. You can refreeze melted ice. That's a reversible physical change. But you can't unchop a carrot, even though that's also a physical change. And chemical changes, like making popcorn or burning wood, almost always a one-way trip.
And these changes are going on all the time, for better or for worse. I mean, we count on desirable chemical changes to cook our food or ripen a banana. We spend a lot of time fighting undesirable ones, like an iron gate rusting or food going bad. And over huge amounts of time, even slow changes, like rocks weathering away, create the very soil we stand on.
So,
Here's your final challenge. Seriously, for just a second, look away from the screen. Look around whatever room you're in. Maybe you're sipping a drink with melting ice. Maybe the battery on your device is discharging. Your own body is turning food into energy. How many physical and chemical changes can you actually spot? Once you start looking for them, you realize they are absolutely everywhere.
Hey everyone, welcome. Today we're going to talk about something that literally every single person goes through. Growing up. It's this wild ride, right? Full of changes, a ton of questions, and some pretty cool discoveries. So let's jump right in. Okay, so think about it like this. You can't just plant a little seed and expect to get an apple from it the next day, right? Of course not. It's got to have time, it needs a little help, and it goes through all these stages, from a tiny sprout to a little sapling, and then finally, bam, it's a full-grown plant. It's a whole process. And guess what? It's pretty much the exact same thing with us. Just like that little seedling, our bodies and our minds, well, they can't do everything from day one. We need that time to grow, to develop, and to mature through all the different phases of life. So let's really dig into this whole journey. We're going to focus on that really key time, that bridge between being a kid and, becoming an adult. And that bridge, it's got a name. It's called adolescence. It's this really incredible, kind of crazy period, usually from around age 10 to 19, where your body and your mind are basically getting ready for the main event, adulthood. It's a time of super fast growth and some really big changes. And the thing that kicks it all off? That's puberty. Puberty is just the name for all the physical changes that happen to get your body ready for being a grown-up. And it's all powered by these things called hormones. Think of them like tiny messengers in your body, delivering the news that it's officially time to start changing. All right, so let's get into what this actually looks like. The physical changes you can see and feel. You can think of this next part as kind of like the body's blueprint for growing up.
I bet you've had a moment like this, right? You see a friend you haven't seen in a little while and you're like, whoa, you got so tall, or your voice sounds totally different. Those are the first, most obvious signs that the blueprint is kicking in a gear. Okay, so if we look at the breakdown here, you'll see the changes are different for everyone. For boys, you've got things like mustaches and facial hair starting to grow, and the voice gets deeper. That's the Adam's apple, you might notice. For girls, a really key change is the development of breasts. And then there's a whole bunch of stuff that's common for everybody. Getting taller, gaining weight, growing hair in new places like your armpits, and yep, the classic pimples and acne. It's all part of the deal.
Now, this is maybe the most important thing to remember. There is no right timeline for any of this. Seriously, your friend might have a growth spurt a whole year before you do. Your voice might change way later than someone else's. And you know what? That is all completely, 100%, absolutely normal. Everybody's body has its own unique schedule. But, of course, growing up isn't just about what you see in the mirror. There is just as much, if not more, going on inside. So let's talk about that. Let's talk about the feelings, the thoughts, and how to navigate your own inner world.
Yeah, during this time, your emotions can feel, well, like someone cranked the volume dial all the way up. You might have mood swings that come out of nowhere, or just feel everything so much more intensely than you did as a kid. But it's also a time where you might get super curious about new things, or start feeling a real sense of empathy for other people. It's all totally normal, just your brain building new pathways. And you know what's so cool about that? All that new emotional energy, it's not something to be scared of. It's actually like a superpower. You can channel it into amazing stuff. It can fuel your creativity, maybe you get into art or music. It can make you a better problem solver, or it can inspire you to actually get out there and help people. So, okay, with all this stuff happening, both physically and emotionally, how do you take care of yourself? What's the game plan? Well, this next part is all about building healthy habits to help you through the whole journey.
First up, personal hygiene. It just becomes extra important now, to stay healthy and just feel good. We're talking about simple stuff, like keeping your body clean. For girls, this also means knowing how to handle menstruation with sanitary pads or reusable ones, and knowing how to dispose of them properly is a big part of that. And for everyone, getting some regular exercise, huge. It's one of the best ways to keep both your body and your mind feeling fit and strong.
And while we're on the topic of menstruation, let's talk about the timing, because it can seem a little mysterious. A typical cycle is often said to be about 28 to 30 days. But, and this is a big but, just like with everything else, normal is actually a pretty big range. A cycle anywhere from 21 to 35 days is totally common and totally healthy. It's just your body figuring out its own unique rhythm. This is so important. We have got to separate the myths from the facts here. For way too long, there have been these old, totally wrong ideas floating around that menstruation is some kind of sickness or something to be ashamed of. Let's be crystal clear. The scientific fact is that it's a natural, healthy process. It's a sign of good reproductive health. There is zero scientific reason for anyone to feel ashamed or to be isolated because of it, period. So you see, all of these changes are really setting the stage for your future. The choices you start making right now about your health, your friends, how you treat people, how you treat yourself, these are literally the building blocks for the adult you're going to become. And let's be real, in today's world, a huge part of that is your social life, especially online. The rules are actually pretty simple, but they're super powerful. Be respectful, be kind. Think for a second before you post something. And please, protect your privacy. Don't share personal stuff with strangers. And here's the big one. If you ever deal with cyberbullying, know that you are not alone. Don't be afraid, handle it wisely, and please, talk to an adult you trust, whether it's a parent, a teacher, or a family member.
Okay, another massive choice is about your health. Saying no to things that can harm you, like tobacco, alcohol, and illegal drugs, is honestly one of the most powerful things you can do for your body and your brain. These substances can cause real, serious damage and totally mess up your future. And this quote, it really nails it. Addiction doesn't just happen overnight. For almost everyone, it starts with that one little thought, what's the harm? I'll just try it once. And that's exactly why being firm and saying no right from the very beginning is so important for staying healthy. So, when you boil it all down, this whole period of your life is about laying the foundation for, well, the rest of your life. Every choice you make, every good habit you build, it's like putting another strong brick into that foundation. So, I'll leave you with this question. What will you choose to build?
Hello and welcome. Today we're going to pull back the curtain on an invisible force that, well, runs pretty much everything. It cooks our food, it drives our weather, and it even keeps us warm from 93 million miles away. We are talking about heat, and by the end of this, you'll see the world in a whole new way.
And it all kicks off with this really simple but honestly brilliant question from a curious girl named Pema. She's watching her grandmother cook and just asks, why? Why metal? And it's a question that, let's be honest, we've all probably wondered about. The answer is our first key to unlocking how heat gets from A to B. So let's meet Pema and her brother Palden. Picture this, it's a cold evening, they're sitting by a fire, and their minds are just buzzing with questions. Why is it so warm right here but cold over there? Why is the pan made of metal but the handle is like plastic? And why does the smoke from the fire always go up? So you see, these aren't just random kid questions. They're actually 3 amazing puzzles. And by solving them, we're going to uncover the 3 fundamental ways that heat moves through solids, liquids, gases, and even through the complete emptiness of space. So let's get started with that first puzzle, the metal pan.
All right, first up, Pema's question about why her grandma's pan is made of metal. This brings us to our very first type of heat transfer, and this one is all about what happens when things touch.
To really get this, let's imagine a classic experiment. You take a metal strip and you stick a few pins on it using wax. Then you heat up just one end with a candle. Now for those pins to fall, the heat has to travel down the strip to melt the wax, right? So, what do you think is going to happen? Which pin falls first? And boom, the result is just perfect. The pin closest to the flame drops first, then the next one, and the next, all in a perfect, predictable line. It's a chain reaction. Heat is literally marching down that strip, from the hot end to the cold end, with one particle bumping into its neighbor and passing the energy along. This process has a name. It's called conduction. It's how heat moves through direct contact, and it mostly happens in solids. Now, the key thing to remember here is that the tiny particles themselves aren't actually traveling down the strip. Nope, they're just vibrating in place and passing that energy on. It's kind of like a microscopic game of telephone.
And this slide right here is the aha moment that completely solves Pema's puzzle. See, materials like metals are amazing conductors. They let heat pass through them super easily. That's why we make the main part of the pan out of metal, to get the heat to the food. But other materials like wood or plastic are terrible at it. They're called insulators. And that's exactly why the handle is made of plastic, to stop that heat from conducting right into your hand.
And we use this idea literally everywhere. Think about a woolly sweater. It doesn't actually make heat.
What it does is trap a layer of air right next to your body. And air is a fantastic insulator. It stops your own body heat from escaping. It's the exact same reason why 2 thin blankets are often warmer than 1 thick one. It's not about the blanket, it's about that sneaky, trapped layer of air in between.
Okay, 1 mystery down, 2 to go. Let's move on to our second puzzle. Why does the smoke from the fire always rise? To answer this, we need a totally different way for heat to travel.
The answer is actually pretty simple, but it's so powerful. When you heat up air, or any liquid or gas for that matter, its particles start zipping around and spreading out. The air expands. This makes it less dense, or basically lighter than all the cool air around it. And what does lighter stuff do? It floats up. The smoke you see is just catching a ride on this invisible elevator of rising hot air.
And this process is called convection. Now remember how with conduction the particles stayed put? Well, convection is the complete opposite. This is all about the actual movement of particles. The hot, lighter stuff physically rises, and the cool, denser stuff sinks to take its place. This creates this amazing circular flow, a convection current, that's constantly mixing things up and transferring heat.
You want to see a perfect, huge example of this? Just think about the beach. During the day, the land heats up way faster than the water. So the hot air over the sand rises, and all that cool air from over the sea rushes in to fill the gap. We call that a sea breeze. But then at night, the whole thing flips. The land cools down faster, so now the warmer air is over the sea. It rises, and the cooler air from the land flows out to take its place. The whole coastline is just this massive convection engine running 24/7. This brings us to our final puzzle. How could Pima and Paulden feel the warmth of the fire, even though they were sitting at a distance? They weren't touching it, so it's not conduction, and they weren't directly above it in the rising air, so it's not convection. So, what's going on? The answer is radiation. This is heat that travels as invisible waves of energy. And the wildest thing about radiation is that it doesn't need anything to travel through. No solids, no liquids, no gases. It can travel through the total vacuum of empty space. In fact, that's exactly how the sun's warmth gets to us, across 93 million miles of nothing. It's just pure energy, flying through space. And you actually deal with radiation every single day. Just think about your wardrobe. Why do we wear light-colored clothes in the summer? Because they reflect most of the sun's heat radiation. And in the winter, we wear dark colors because they do the opposite. They absorb more of that heat radiation, helping to keep us warm. It's simple physics, right there in your closet. So we've got our 3 methods: conduction, convection, and radiation. But here's the thing. In the real world, they almost never work alone. In fact, they all team up to power one of the most important systems on our entire planet. The entire water cycle is just this beautiful symphony of heat transfer. It all starts with the sun's energy traveling through the vacuum of space. That's radiation. That energy then hits the Earth and warms up our oceans, lakes, and rivers.
So, that solar radiation causes water to evaporate. And what happens to that warm, moist air? Well, it's lighter now, so it rises. That's convection. As it gets higher and higher, it starts to cool down and condenses into clouds. Eventually, you get rain or snow, and the whole amazing cycle starts all over again. It's a planetary scale heat engine.
So it's clear that nature uses these principles on a massive scale. But what happens when we humans really understand this flow of heat? Well, we can do some pretty ingenious things with it.
Okay, so here's our toolkit, right? We've got conduction, which is heat by touch, convection, which is heat by flow, and radiation, heat by waves. Now let me show you an absolutely stunning example of how mastering this toolkit can help solve one of the world's biggest problems, finding enough water.
Get ready for this. We're going to the Himalayas, to a region called Ladakh. They face a massive water shortage every spring, right when the farmers need it the most for their crops. Their solution is pure genius. In the middle of winter, when it's unbelievably cold, they just spray water from a stream up into the air. It freezes instantly and falls, building up layer by layer into this huge cone of ice, basically a man-made glacier. Because of its shape, it's shaded from the spring sun, so it melts really slowly, releasing a steady supply of water just when they need it. It is a masterful use of heat transfer to solve a life-or-death problem. From the pan in your kitchen to the breeze on your face and the water you drink, these 3 invisible flows of heat are constantly shaping your world. And that's the real takeaway here. Once you know what to look for, you'll start to see them absolutely everywhere. So, what are you going to notice first?
Have you ever stopped to think about how we went from telling time with shadows to, measuring a race down to a thousandth of a second? It's kind of amazing, right? Well, today, we're going to dive into that incredible journey, from ancient sundials all the way to how we define speed itself. So this whole thing starts with a question from a young runner named Prana. She was watching the Olympics, just blown away by the incredible precision of it all, how a gold medal can be won or lost by a tiny fraction of a second. And it got her thinking, how did anyone measure time before all this crazy technology? For a runner like Purna, timing is everything. At her school, a simple stopwatch gets the job done. But at the Olympics, we're talking hyper-advanced systems. And that huge gap just goes to show how essential precise timekeeping has become, especially in the world of sports. And it's not just in sports, is it? We are literally surrounded by clocks. They're on our wrists, in our pockets, with our phones, and there are even specialized ones that talk or use Braille. We completely take them for granted. So to really answer Perna's question, we have to go back, way back, to a time before any of these existed. So how did ancient civilizations keep track of the day? They didn't have batteries or gears, but they had something just as powerful: observation and some serious ingenuity. They looked to the world around them, to the sun, to water, even to a burning candle. The most intuitive clock, of course, was the sundial. The whole concept is just so simple and brilliant. As the sun moves across the sky, the shadow cast by an object moves right along with it. All you have to do is mark where the shadow falls at different hours, and boom, you can tell the time of day. But what do you do on a cloudy day or at night? That's where water clocks came in. Some of them worked by letting water drip steadily out of a marked container. Others, like the Gatika Yantra from ancient India, were even more clever. Just picture this: a small bowl with a tiny hole in it, floating in a bigger basin of water. It would slowly fill up, and after a very precise amount of time, it would sink, and someone would strike a gong to mark that interval. Pretty smart, huh? And the creative solutions didn't stop there. The hourglass, which you've definitely seen, used the consistent flow of fine sand to measure a fixed period of time. And candle clocks had marks on the side to show how much time had passed as the wax steadily burned down. And don't go thinking these ancient instruments were just crude guesses. Some were incredibly sophisticated. Take the Samrat Yantra in India. It's a massive, 27-meter-high stone sundial. It is so precise, you can actually watch its shadow move at a rate of 1 millimeter every single second. Wow! For centuries, these methods were the best we had. But the next great leap forward in timekeeping, well, it wouldn't come from the sun or from water. It would come from a simple swinging weight and a moment of brilliant observation. So the story goes that the famous scientist Galileo Galilei was sitting in a church, probably a little bored, when he noticed a lamp swinging from the ceiling. He started using his own pulse as a timer, and he made this amazing discovery. No matter if the swing was wide or narrow, the lamp seemed to take the exact same amount of time for each full back and forth motion. This super consistent timing, that's what we call the time period of a pendulum. It's the time it takes to complete one full swing, or oscillation. Galileo realized right away that this predictable, repeating motion was the perfect foundation for a truly accurate clock. But what actually determines that time period? Well, through experiments, Galileo found something that's totally counterintuitive. It wasn't the weight of the bob at the end or how far back he pulled it. The only thing that mattered was the length of the string. And that was the secret. A pendulum of a specific length will always swing with the exact same rhythm. And this just perfectly shows the power of scientific discovery. Galileo had the insight, and then, a few decades later, a Dutch scientist named Christian Huygens took that principle and used it to build the very first pendulum clock. This invention completely revolutionized timekeeping, making it way, way more accurate than ever before. Okay, so we've now mastered accurate time. What does that unlock? Well, once you can reliably measure time, you can finally start to reliably measure things that happen over time. And this is the crucial link to understanding motion. This brings us straight to the concept of speed. At its very core, speed is just the distance an object covers in a certain unit of time. The formula is pretty straightforward. You just divide the total distance you traveled by the total time it took. And in science, we usually measure this in meters per second.
You know, the relationship between these three things, speed, distance, and time, is actually beautifully simple. If you know any two of them, you can always figure out the third. So if you want to find the distance you traveled, you just multiply your speed by the time. It's this fundamental principle that's the bedrock for calculating all kinds of motion. But speed can be a little more complex than just a single number. I mean, think about a car trip. You don't travel at the exact same speed for the entire journey, right? You speed up, you slow down, you stop at lights. So we really need to distinguish between different types of motion.
The two basic types are what we call uniform and non-uniform motion. Uniform motion is when an object is moving at a perfectly constant speed, covering the exact same distance in every equal time interval. Non-uniform motion, which is much more common, is when its speed keeps changing, so it covers different distances in those same time intervals.
This whole difference becomes crystal clear when you look at an example. So imagine two trains. Train X travels a perfect 20 kilometers in every single 10-minute interval. That's classic uniform motion. But then you have train Y. It's more realistic. Its speed is all over the place. Sometimes it covers 15 kilometers, sometimes 25. That's non-uniform motion.
And let's be honest, which of those trains sounds more like real life? Train Y, of course. In the real world, perfect uniform motion is incredibly rare. And that's exactly why we usually calculate something called average speed, the total distance divided by the total time, to get a useful measure of a journey.
And that brings us completely full circle. We started wondering how ancient people told time, we saw Galileo's swinging lamp, and we ended up with the invention of the pendulum clock. That massive breakthrough in accurately measuring time was the essential key that finally allowed us to truly begin measuring and understanding motion. You really couldn't have one without the other.
Today, our best atomic clocks are so mind-bogglingly precise they'd lose maybe 1 second over millions of years. We have become absolute masters at measuring time. But that leaves us with a final, much, much deeper question. We know how to measure it, but what, fundamentally, is time? Now that's a thought for another day. Thanks for joining this explainer.
Your body is this incredible machine, right? It's working nonstop, 24/7 to keep you going. But have you ever really stopped to think about what's powering it all? Well, today we're diving into the two big processes that make everything possible: how your body turns the food you eat into fuel and how it uses the very air you breathe to ignite it. I mean, think about it. You eat a burger, a salad, whatever, and then what? It's so easy to just forget about it once you swallow. But that's when this amazing, super complex journey really kicks off inside you. So let's follow that journey, right from the very first bite to that final spark of energy.
You know, the best way to picture this is to think of your body as a high-tech factory. The food you eat, full of stuff like carbohydrates and proteins, that's the raw material coming in. But your body can't use it as is. Nope. It's got to be broken down, refined, and converted into a simple fuel that your cells can actually burn.
And the main assembly line in this factory? It's called the alimentary canal. It's basically one long, winding tube that starts at your mouth and, well, ends at the other end. Every single step of digestion happens somewhere along this incredible pathway.
Okay, let's get into it. We're going to trace the path of your food as it travels through this amazing system, stop by stop. Our food's journey has 5 main stops, starting in the mouth and going all the way to the large intestine. Each one of these stops has a totally unique and absolutely crucial job to do in breaking down our food and grabbing all the good stuff we need. The whole process kicks off the second food enters your mouth. Your teeth start crushing it up, sure, but the chemical breakdown begins right away too. Your saliva is packed with digestive juices that get to work on complex carbs or starches, turning them into simple sugars. In fact, that's why if you chew a piece of bread for a really long time, it actually starts to taste sweet. Pretty cool, right? After a quick slide down the esophagus, the food lands in the stomach. Now this place is a powerhouse. The walls churn and mix the food with super strong digestive juices and acid. It's the perfect environment for breaking down proteins. And don't worry, your stomach is totally fine. It's lined with a thick layer of mucus to protect itself from its own acid. And what's really wild is how we even figured all this out. It's an incredible story. Back in 1822, a guy named Alexis St. Martin was accidentally shot, and it left him with a hole in his stomach that never quite healed.
His doctor, William Beaumont, realized he had a literal window into the human body. He used it to watch digestion happen in real time, and his experiments basically formed the foundation of everything we know today. So from the stomach, our food moves into the small intestine. And get this, despite the name, it's anything but small. If you were to stretch it all the way out, it would be about 6 meters long. To put that in perspective, that's like almost twice the height of a classroom ceiling. It is by far the longest part of the whole digestive tract.
So why is it so ridiculously long? Well, its main job is something called absorption. This is the moment we've been waiting for. It's the point where all those simple sugars and other nutrients that we've worked so hard to break down finally get passed from the digestive system into your bloodstream, ready to be delivered all over your body.
And the way the small intestine is built is just genius. Its inner lining isn't smooth at all. It's covered in millions of tiny little finger-like folds. This massively increases the surface area, creating this huge space for all those nutrients to get absorbed super efficiently into your blood. It's all about maximizing that absorption. Of course, it's not just us humans with these incredible systems. Let's take a quick look at how other animals have adapted to handle their own unique diets. It's pretty fascinating. Take grass eaters like cows. They have this crazy system where they partially digest their food, then bring it back up to chew on it again. That whole process is called rumination. Then you've got birds who don't have any teeth. So instead, a lot of them swallow tiny stones that go into a muscular organ called a gizzard, which then grinds up all their food for them. Okay, so we've broken down our food into fuel. We've got it into our bloodstream. But how do we actually use that fuel? For that, you need a spark. And that spark, my friends, is oxygen. This brings us to the other half of our story, the incredible process of breathing and respiration. Now, this is a super important point. Breathing and respiration are not the same thing. Breathing is just the physical act, in and out, moving air into your lungs. Respiration, on the other hand, that's the chemical reaction happening deep inside your cells, where oxygen is used to unlock the energy that's been stored in your food. And you can actually see the evidence of this happening. Look at the air we breathe in. It's about 21% oxygen. But the air we breathe out, only about 16% oxygen. At the same time, the carbon dioxide jumps from almost nothing to about 4%. So where did that oxygen go? And where did all this new carbon dioxide come from? A chemical change definitely happened inside our bodies. And we can prove it with a simple science experiment using something called lime water. It's a clear liquid that turns milky when it comes into contact with carbon dioxide. If you bubble normal air through it, nothing happens. But if you blow your own breath through a straw into it, it turns milky almost instantly. That's hard proof that our breath is loaded with carbon dioxide. And this whole amazing process can be summed up in this one simple, beautiful equation. The glucose, that's the simple sugar from our food, combines with the oxygen we breathe. This reaction releases the energy that powers everything we do, and the waste products are just carbon dioxide and water. Isn't that incredible? This is happening in trillions of your cells right now. Okay, so we've looked at two totally separate systems, right? But the real magic is how they work together. Let's zoom out and connect all the dots to see the full picture. Here it is, the grand finale. Digestion creates the fuel. Respiration uses oxygen to unlock the energy from that fuel. And then the circulatory system, your blood, acts like a massive delivery service. It picks up the fuel from the small intestine and the oxygen from the lungs, and then it transports them to every single cell in your body. It is a perfectly coordinated masterpiece. Every single day, this whole complicated process happens trillions and trillions of times at a cellular level, and you don't have to give it a single thought. It really makes you wonder, doesn't it? What other incredible, invisible wonders are at work inside of you right this very second? Have you ever really thought about plants? I mean, really thought about them. They're everywhere, this massive, silent, green kingdom. But they can't move to hunt. They can't go to the grocery store. So how do they live? How do they get so big? What's their secret? Think about it. You can picture a wolf chasing down its prey. You can picture a squirrel nibbling on a nut. But try to picture a tree eating. It's a weird thought, right? You can't really picture it. Well, that's the mystery we're going to solve together today, the hidden engine that powers all plant life. All right, so let's play detective. The first step in any mystery is to gather the clues. And our first question is a basic one. What are the absolute must-have ingredients for a plant to even survive? Turns out, the clues are all around us. Check out this super simple experiment. In pot A, you give the plants sunlight and water, and look, it's happy, green, and growing. Now pot B. It gets sun, but we take away the water. The result? It completely wilts. Not good. And pot C. It gets water, but we stick it in the dark closet. It gets all weak and yellowy. The evidence here is crystal clear. Sunlight and water are totally essential. We found our first two key ingredients.
Okay, so we've got our ingredients, sun and water, but, just having flour and eggs in your kitchen doesn't magically make a cake. You need a chef, you need a process. For plants, their leaves are the kitchen, and they're about to whip up some serious culinary magic.
So what's the secret ingredient in that kitchen? It's a little thing called chlorophyll. Now, chlorophyll is what makes plants green, sure, but it's so much more than just a color. You can think of it as millions of tiny living solar panels packed into every leaf, and they have one job: soak up the energy from sunlight. This is the power source for the entire factory. And this whole amazing process has a name you've probably heard before: photosynthesis. This is it. This is the answer to our big mystery. This is how plants eat. They take that sunlight energy they've captured and they use it to smash together water and carbon dioxide to create their own food, a type of sugar called glucose. But how do we know this is actually happening? I mean, where's the proof? Well, scientists have this really cool test using iodine. Basically, they take a leaf, get rid of the green chlorophyll, and then add a few drops of iodine. If the leaf has been making food, it will turn this deep blue-black color. That color change is the smoking gun. It proves that starch, which is just stored up glucose, is there. The food factory is officially open for business. So here it is, the simple recipe that powers pretty much all life on Earth. A plant takes in carbon dioxide from the air we breathe out and water from the ground. Then, using sunlight as the oven, it cooks them up into glucose, its energy food. But look at what's left over: oxygen. The plant just releases it into the air. And that one little act, that leftover ingredient, well, it changes everything for the rest of us. Right, but how does the carbon dioxide even get into the leaf in the first place? Well, if you look really, really closely, the leaf is covered in these thousands of tiny little pores called stomata. You can think of them as microscopic mouths that open up to breathe in the carbon dioxide it needs and then breathe out the oxygen it doesn't. This is great. The leaves are making tons of food. But hold on a second. The roots are way down in the dirt, and they need energy too. And the water the roots absorb needs to get all the way up to the leaves. So how does everything get where it needs to go? Well, it turns out plants have a pretty amazing internal plumbing system. It's basically a two-way highway. First, you have what's called the xylem. Think of it as a water elevator, a bunch of one-way tubes that are just for pulling water and minerals up from the roots to the rest of the plant. Then you have the phloem. This is the food delivery service. It takes all that sugary glucose made in the leaves and distributes it everywhere else, down to the roots, over to the flowers, wherever energy is needed. So, the food has been made in the leaves and it's been delivered all over the plant. You'd think that's the end of the story, right? Job done. But actually, no. Just like for us, having food in the fridge is one thing, but you still have to convert that food into usable energy. Making the food was only half the battle. This really breaks it down. These two processes are like two sides of the same coin. On the left, you have photosynthesis, which we know is all about producing food. But on the right, you have respiration, and its job is to release the energy from that food. And here's the really crucial difference. Photosynthesis only happens when there's light, but respiration, that's happening all the time, day and night, in every single living cell of the plant. So this is how the plant actually unlocks the power it made. It takes that glucose, combines it with a little oxygen, and basically burns it to release energy for everything it needs to do: grow, repair itself, you name it. And get this, what are the leftovers? Carbon dioxide and water, the exact same ingredients it needs to start photosynthesis all over again. It is a perfect self-sustaining loop. So when you step back and put all these pieces together, the food factory and the leaves, the plumbing system, the way it releases energy, you start to see this beautiful, perfect cycle. It's an incredible self-powering system that has allowed plants to conquer pretty much the entire planet. So let's just recap what a plant really is.
First, it's a producer. It literally makes its own food out of thin air and sunlight. It's incredibly organized with that complex delivery system moving things around. It's also a consumer because it has to burn that food to get energy. But maybe the most important thing for us is that it's a giver. That oxygen it pumps out isn't just waste. It's the very air that we and almost every other animal need to take our next breath.
So we started with a simple puzzle. How do plants eat? And we found the answer. But along the way, we stumbled upon a much deeper truth. Our entire existence is completely tangled up with theirs. They are the base of the entire food web and the source of the very air we're breathing right now. So this final question, it's not just a hypothetical. It's a reminder of just how much we depend on these quiet, green, life-giving engines.
Light. I mean, it's literally everywhere, right? But have you ever really stopped to think about the rules it follows? Today, we're going to do just that. We're diving into the pretty amazing world of light, shadows, and reflections to figure out the science behind what we see every single day.
And our whole story today starts with a simple question. The kind of question we've probably all had at some point. It was on a bus ride home that a boy named Keshav was looking out the window at the moonlit landscape, and he just started wondering, where does that light really come from? And that question? Well, that's our launch pad for everything we're about to explore.
Okay, so let's get right into it. To answer Keshav's question, we first have to understand a really key idea. Not everything that shines is actually making its own light. We've got to solve this first mystery to get anywhere else.
And it all boils down to one simple difference. You've got luminous objects, things like the sun, distant stars, even tiny little fireflies. They're the source. They create their own light. And then you have, well, everything else. The moon, planets, this screen you're watching, even you and me. We're all non-luminous. We're only visible because we're reflecting light from somewhere else.
And there it is. Mystery number 1, solved. Keshav was totally onto something. The moon doesn't produce any light of its own. It's basically acting like a giant, beautiful mirror up there in the sky, bouncing the light from our ultimate luminous source, the sun, right back at us.
So now we know about light sources. But that just brings up another question, right? How does that light get from the sun all the way to the moon and then all the way back to our eyes? Well, it turns out it follows a very, very strict rule. Let's dig into how light actually moves.
You know, it's one thing to just say light travels in a straight line, but how can we actually prove it? The cool part is, you don't need a fancy lab for this. Just a couple of clever, really simple experiments you could honestly try at home.
Okay, so proof number 1 is this matchbox activity. Imagine you line up 3 matchboxes, each with a little hole punched in the exact same spot. If you shine a flashlight through one end, that beam sails straight through all 3 holes and hits a screen on the other side. But what happens if you just nudge one of those boxes, even a tiny bit? Poof, the path is blocked. The light is completely gone.
And this one illustrates the exact same thing. Take a straight, hollow pipe and look at a candle flame, you'll see it perfectly. But the second you bend that pipe, the flame disappears. The light from the candle just cannot navigate that corner. It's a straight shot or nothing.
So, both of these incredibly simple tests lead us to the same undeniable conclusion. It's our first fundamental rule of light. It travels in a straight line. And this simple fact, I promise you, is the key to understanding pretty much everything that comes next.
All right, we've established that light travels in a straight line. We've got that down. But what happens when something gets in its way? Let's check out how light interacts with all the different stuff that makes up our world.
We can basically sort materials into 3 groups based on this. You've got transparent stuff, like clear glass, which lets light pass right through. Then there's translucent materials, like tracing paper, which lets some light through but kind of scramble it up. And finally, you have opaque materials, which block light completely.
Let's really focus on this last one, opaque. This is your book, a wall, a tree, basically any object that stands in the way of light and just says, nope, you're not passing through here. This idea is absolutely crucial for our next concept.
Which of course leads us to a very logical question. We have light, it's traveling in its straight line, and then we put an opaque object smack dab in its path. What's the immediate result?
And the answer is something we see every day. A shadow is formed. But here's the thing, a shadow isn't actually a thing. It's simply an area where light is being blocked. It's the absence of light.
So, you can think about making a shadow like following a recipe. You need 3 essential ingredients. First, you need a source of light, a flashlight, the sun, whatever. Second, you need an opaque object to get in the way.
And third, you need a screen for that shadow to show up on, which can be as simple as a wall or just the ground. So, we know what happens when light gets blocked, but what if it isn't blocked? What if it hits a surface and just bounces off? Well, this is where we get into the really cool world of reflections. This whole bouncing phenomenon is called reflection. When a beam of light, cruising along in its straight line, hits a smooth, shiny surface like a mirror, it doesn't get absorbed. Instead, it bounces off at an angle and heads off in a brand new direction. And that reflection is what lets us see ourselves in a mirror. But have you ever noticed that the image in a regular, flat mirror has some very specific qualities? For one, it's always upright. It's always the same size as you, and it always looks like it's the same distance behind the mirror as you are in front of it. And then, there's the really weird part. Let's talk about that weird part, lateral inversion. It's that thing that kind of messes with your brain. When you raise your left hand, your reflection looks like it's raising its right hand. The mirror performs a perfect left-right reversal. And this isn't just some fun little quirk, it has a critical, real-world application. This is exactly why the word ambulance is written backwards on the front of emergency vehicles, so that when a driver looks in their rearview mirror, that lateral inversion flips the text back to normal and they can read ambulance instantly. Just a fantastic, life-saving use of physics. Okay, let's put all these pieces together. We've seen that light traveling straight can be blocked to form a shadow, or it can be reflected to form an image. But how does an image in a mirror compare to one made by something simpler, like a pinhole camera? This table really lays out the key differences. Notice how a mirror image is always upright, but a pinhole camera image is actually upside down. And here's a big one. You can't project your reflection onto a screen, but a pinhole image is a real image that you absolutely can. All these differences just come down to how the light is being handled. Is it bouncing off a surface or being focused through a tiny opening? And as we wrap up, here's one last kind of mind-bending fact for you. Sunlight travels incredibly fast, but it still takes about 8 minutes and 20 seconds to get here. That means when you look at the sun, you're not seeing it as it is right now. You're seeing it as it was over 8 minutes ago. You're literally looking into the past. So we started with a simple question about the moon and ended up uncovering the fundamental rules of light, shadows, and reflections. The final question is for you. Now that you know these rules, what other mysteries in the world around you can you start to explain? Thanks for joining this explainer.
All right, welcome to the explainer. Today, we're digging into a question that, it starts right here on the ground, but it's going to take us all the way across the solar system. We're talking about the fundamental dance between our planet, our star, and our moon.
So this whole thing kicks off with a 12-year-old named Rashmika from Tamil Nadu, India. Riding her bike to school, she noticed something simple. Her shadow was really long in the morning, but by the afternoon, it was short. And that simple observation sparked a massive question. So, is the sun moving or are we? I mean, it sounds simple, right? But the answer, wow, it completely flipped our understanding of the universe on its head. To really get to the bottom of it, we need to think about how we even perceive motion in the first place.
All right, to get to the answer, let's start with something you've probably experienced, a merry-go-round. And believe it or not, this simple ride is the key to understanding how our planet moves every single day.
Okay, so our source material has this fantastic analogy. Picture this. You're on a merry-go-round, and it's spinning anti-clockwise. As you're going around and around, what happens to, say, the trees or the benches just outside the ride? From your point of view, they look like they're spinning past you in the opposite direction, clockwise, right? And that, right there, is the huge difference between what seems to be happening, what we call apparent motion, and what's actually happening. From where we stand on this giant spinning merry-go-round we call Earth, it sure looks like the sun is the one doing the moving, but really, we're the ones spinning. So this daily spin has a name. It's called rotation. The Earth is turning on this imaginary line, its axis, that goes right through the North and South poles. And that full spin, well, that's our 24-hour day. It's the reason we have day and night.
You know, what's just incredible is that this idea is ancient. The brilliant Indian astronomer Aryabhata figured this out way, way back in the 5th century. He used a really similar idea, talking about being on a boat to explain why the stars, which are totally stationary, look like they're drifting across the night sky.
Okay, so that makes sense for the daily motion, right? But that just opens up a whole new can of worms. If the Earth is just spinning in place every day, then why does the night sky change throughout the year? Shouldn't we see the exact same stars every single night?
Well, the reason we don't see the same stars is because that daily spin, that's only half the story. This brings us to the Earth's other major move, its huge year-long journey all the way around the sun.
And this trip has a name too, revolution. So, while our planet is spinning on its axis every 24 hours, it's also cruising along this massive path, its orbit around the sun. And that whole lap takes about 365 days, 1 year.
So think about it. As we travel around the sun, the slice of the universe we're looking at during the night is constantly changing. It's kind of like walking around a big campfire at night. Your view of the dark woods behind the fire is totally different depending on where you're standing. It's the same idea with Earth. Our view of the galaxy in June is completely different from our view in December.
All right, let's talk about one of the biggest misconceptions out there in science. This yearly journey, this revolution, is what gives us our seasons. But it's probably not for the reason you think. So a lot of us think, okay, summer must be when we're closer to the sun, and winter is when we're farther away. I mean, it makes sense on the surface, right? But it's actually totally wrong.
Yeah, the evidence here is just rock solid. That whole closer, farther idea is just not it. The change in distance is way too small to matter. But here's the real kicker. For those of us in the northern hemisphere, the Earth is closest to the sun in January, the middle of winter. How crazy is that?
So, if it's not the distance, what is it? Well, it all comes down to one crucial thing, the tilt. See, the Earth doesn't spin perfectly upright. It's tilted on its axis, about 23.5 degrees. And that little lean? It changes absolutely everything. So, here's why that tilt is the whole ballgame. In June, the northern hemisphere is tilted towards the sun. That means we get sunlight that's really direct and concentrated, kind of like shining a flashlight straight down on a spot. Plus, our days are longer. But in December, we're tilted away from the sun. The sunlight hits us at an angle, so that same energy gets spread out over a much bigger area, and our days get shorter. That's what makes it colder. It's the angle, not the distance.
Okay, so now that we've got this incredible cosmic dance of rotation and revolution down, we can start to understand some of the most spectacular shows in our sky, eclipses.
I mean, think about it for a second. How can our tiny little moon completely block out the massive giant sun? Seriously, the sun is 400 times bigger than the moon. It just doesn't seem possible. Well, you can actually figure this out with a little experiment right now. Go ahead, hold your thumb out at arm's length. See how, even though your thumb is small, it can easily cover up something huge in the distance, like a whole building or a person's head? It's because it's so close to your eye.
And that's the secret right there. It's this mind-blowing cosmic coincidence. The sun is, yes, about 400 times wider than the moon, but it's also about 400 times farther away. And because of that, from our unique spot here on Earth, they appear to be almost the exact same size in our sky. It's just perfect.
So it's not about actual size at all. It's about apparent size. And that's what makes the magic of a total solar eclipse happen. The moon is just the right size and just the right distance away to perfectly block out the sun.
Okay, so there are two main types of eclipses, and they're both just cosmic shadow plays. During a solar eclipse, the moon gets in the way and casts its shadow on us here on Earth. During a lunar eclipse, the Earth gets in the middle and casts our shadow on the moon. And please, remember, never look directly at the sun during a solar eclipse, but a lunar eclipse, totally safe to watch with your own eyes.
So there you have it, from a simple question about a shadow on the way to school to understanding the Earth's tilt that gives us summer and winter and the incredible coincidence that gives us eclipses. It all just goes to show it starts with looking up and being curious. Thanks for joining this explainer.
What if I told you that you could think like a scientist right now, without a lab coat, without a PhD? Well, today we're going to unlock that exact mindset. We are going on an investigator's journey, not just to memorize old facts, but to learn how to find brand new ones for ourselves. Just picture this for a second. You're in the kitchen, the air is warm, and it's filled with that incredible smell of frying dough. You watch a puree puff up like a perfect golden balloon. But have you ever really stopped to notice that one side is always paper thin while the other side's thicker? It's such a tiny detail, right? But a question just like this is the spark that can ignite a real scientific investigation. And you know, that same spark of curiosity can launch you from the kitchen right into the cosmos. Take a second and really think about this one. What's your gut feeling?
This isn't just a piece of trivia. It's a massive puzzle that makes us grapple with these two different kinds of infinity and the just mind-boggling scale of our universe versus our world.
Or hey, we can bring that curiosity right back down to Earth and ask one of the biggest questions there is. Why bother with millions of different species? Why isn't there just, I don't know, one perfect kind of leaf or one super efficient insect? This question, this is the very heart of biology. It's a mystery that reminds us that the world all around us is a living, breathing laboratory, just overflowing with clues.
So, what's the really crucial point here? This explainer isn't about just handing you a big list of facts to memorize. It's about giving you a new kind of superpower. We want to help you shift from being a passive learner to an active investigator, ready to unravel the mysteries of the world for yourself.
Now, every great investigator needs a toolkit, and ours has two incredibly powerful mental models. They're called root and kite thinking. These aren't physical tools, of course, but two totally different ways of approaching a problem that, when you use them together, can lead to some amazing breakthroughs.
Think of it this way. The root is your inner detective. It's grounded, it makes careful observations, it gathers the hard evidence, and it builds a really solid foundation of facts. It asks, what do I actually see here? But you also need the kite. The kite is your inner explorer. It's your imagination, your creativity. It soars high, and it asks, what if? And I wonder. A real investigator knows how to balance both, using that root to stay grounded in what's real and the kite to explore incredible new possibilities.
Okay, so now you're armed with this powerful toolkit of root and kite thinking. You're ready for anything. You can go on a journey of discovery that spans from the tiniest, teeniest little things to the cosmically huge. The same tools work everywhere.
I mean, just think of the possibilities. What if you decided to investigate that teeming, invisible universe that's inside a single drop of pond water, or decode the flow of electricity that's powering your phone right now? The principles are the same, whether you're exploring the forces that stop a moving car or connecting the phases of the moon to the calendar on your wall. Each one is a world just waiting to be investigated.
Okay, we've talked about the big ideas, the grand journeys. But how does all this work in the real world? It's time to put our new toolkit to the test. Let's go ahead and tackle our very first case, the mystery of the puffy purry.
And hey, forget what you've seen in movies. You don't need a fancy lab coat or a bunch of bubbling beakers. Your laboratory is anywhere you could be curious and observe carefully. So today, our lab is the kitchen.
All right, investigator, here's our 5-step plan of attack. First, we state the question, why does the puree puff up this way? Then, we identify our suspects, all the little things we can change. We control the scene, we meticulously observe the evidence, and this is the most important part, we use what we find to ask even smarter questions.
So let's put on our detective hats. What are our suspects here? What are the variables we could change? Could it be the thickness we roll the dough? What about the type of flour we use? Or the temperature of the oil? You know, maybe it's even the angle we slide it in at. Any one of these could be the key to cracking this case.
But here it is, the cardinal rule of any investigation. You must change only one thing at a time. I mean, think about it. If you change the flour and the oil temperature at the same time, you'll never know which one was the real culprit. To get to the truth, you have to isolate your suspects and test them one by one. That is the heart of a controlled experiment.
And as you run your tests, you become a forensic observer. Use all your senses. Watch the purry. Does it puff up? Yes or no? Time it. How many seconds does it take? Now listen. Can you hear that sizzle? Smell the air. Does the oil smoke? Did it smell different this time? Every single detail, no matter how small, is a clue. You have to record everything.
Now, after all that careful observation, you might think the goal is to find the answer and, close the case. But in the world of science, the real prize isn't a single solution. It's a deeper, more profound, more interesting question. Your first experiment is just the beginning of a much bigger adventure.
And here's the most mind-blowing part of this whole investigation. You might think the puree problem is simple, right? Something figured out ages ago. But get this. The actual physics of how the steam rapidly expands to create that thin, delicate layer, it is so incredibly complex that even today, scientists do not fully understand it. Yeah, let that sink in for a minute. It just proves that profound mysteries are hidden all around us, in the most ordinary things.
So, what's the ultimate takeaway here?
that science isn't just a subject you study in school, filled with a bunch of names and dates. It's a lens. It's a powerful new way of looking at the world, a mindset of curiosity, creativity, and investigation that can transform the ordinary into the absolutely extraordinary.
And now, the torch is passed to you. We've given you the toolkit, the mindset, and a method. All that's left is to begin. So look around your own world. What's something that's always made you wonder? Why does a cat always land on its feet? Why do soap bubbles have rainbows on them? Your first investigation is waiting. What will it be?
You know, in the air you're breathing, the water you drink, even inside your own body right now, there's an entire world, a bustling, invisible world just teeming with life. So what if you could actually see it? Well, in this explainer, we're going to do just that. We're making that world visible. I mean, really think about it. If you could suddenly see everything, no matter how small, a single drop of water wouldn't be just water. It would be a crowded city. The air in front of your face, it'd be full of countless tiny travelers zipping around. Answering this question, well, that's the key to unlocking a whole hidden universe. You know, for most of human history, this entire microscopic world was a complete and total mystery. And the key to unlocking it, it wasn't some kind of magic spell. It was just a simple, curved piece of glass, the lens. This little invention became our very first window into a world we never knew existed. And in the 1660s, a couple of pioneers basically threw that window wide open. You had Robert Hooke, who published this incredible book called Micrographia, full of detailed drawings that just blew people's minds. And at the same time, this guy, Antony van Leeuwenhoek, was making these amazingly powerful lenses. He was the first person to see what he called animalcules, what we now know as bacteria, and even the tiny red cells flowing through our blood. So, one of Hooke's most famous discoveries came from looking at a super thin slice of cork. He expected to see a solid thing, but instead, under his microscope, he saw it was made of all these tiny empty rooms, kind of like a honeycomb. And this simple observation, it was the beginning of something huge. Hooke needed a name for these little rooms, so he called them cells. And that name? It stuck. It was the very first time anyone had used that word to describe a piece of a living thing. Without even knowing it, he had just named the fundamental building block of everything alive on our planet. Okay, so Hooke gave us the name, but what exactly is a cell? If we're all made of them, from the smallest bug to the biggest tree, what are they made of? The best way to think about it is like this. A cell is to you what a brick is to a house. It's the most basic unit you've got. You stack them together, you organize them, and pretty soon you can build anything. An onion, a whale, or even a person. And the coolest part is, you don't need some high-tech lab to see them for yourself. You can literally take a thin, almost see-through layer from an onion, add a drop of stain to make things pop, and look at it under a basic microscope. You'll see them right there, these neat, rectangular bricks, all lined up in perfect rows. But not all cells are created equal. Plant cells, like that onion, have a tough, rigid outer wall that gives them their blocky shape. Animal cells, like ours, are a lot more flexible. And of course, plants have these things called chloroplasts. They're like tiny solar panels for making food out of sunlight. Yeah, our cells definitely can't do that. But despite their differences, most cells share a basic floor plan. There's the cell membrane, which is like the bouncer at the door, controlling what gets in and out. Inside, you've got the cytoplasm, this jelly-like stuff where all the action happens. And then there's the nucleus. That's the main office, the control center that calls all the shots. Now, when we talk about cells, we're usually thinking microscopic, right? Tiny. Well, get this. The largest single cell you can find on Earth today is the yolk of an ostrich egg. It can be 170 millimeters across. That's right, that whole yolk is just one cell. Kind of makes you realize that in this invisible world, size is all relative. So we've got these incredible building blocks, some microscopic, some not so microscopic. But how in the world do you get from a single cell to a complex creature like you or me? The answer is all about teamwork. It's about organization. See, it all starts with specialization. A cell's shape is a huge clue to what it does. Your muscle cells are long and spindle-shaped because they're designed to pull and contract. And your nerve cells? They look like these long branching wires because that's exactly what they are. Living wires built to send messages in a flash. And these specialized cells, they team up.
A bunch of similar cells get together to form a tissue. Different kinds of tissues work together to make an organ, like your heart or your lungs. Then, a bunch of organs team up to form an organ system, like your whole digestive system. And when all those systems work together in harmony, well, that's you, a complete living organism, all built up from that one basic unit, the cell.
But wait, the story isn't over. It's not just about the cells that build us. There's this other massive part of the invisible world, full of creatures that are often just a single cell all by themselves. It's time to meet the microbes. Microorganisms, or microbes for short, are exactly what they sound like: microscopic living things. And when I say they're everywhere, I mean they are everywhere. From the bottom of the ocean to the top of Mount Everest, and yep, trillions of them are living inside your gut right now. They really are the true rulers of this planet. And man, are they a diverse group. You've got your major players like bacteria, protozoa, fungi, and algae. And then you have the real outliers, viruses. These guys aren't even technically cells. They're like little pirates that can only make copies of themselves by hijacking a living host cell. Now, I know when you hear words like bacteria or virus, you probably think about getting sick. And sure, some of them are bad news, but the vast, vast majority are not only harmless, they're absolutely essential for life on Earth to even exist. They're our helpful, hidden friends. You actually depend on them every single day, especially in the kitchen. Ever wonder what makes bread so fluffy? That's yeast, a type of fungus, basically burping out carbon dioxide gas. And that bacteria that turns milk into thick, tangy yogurt, that's a microbe hard at work, fermenting sugar and completely changing our food. And their day job is even more important. On a planetary scale, microbes are nature's cleanup crew, breaking down dead stuff and recycling nutrients. But here's the real mind blower. Tiny little algae in the ocean produce more than half of all the oxygen we breathe. Seriously, every other breath you take, you can thank a microbe. They're also incredible partners in farming. There are certain bacteria, like rhizobium, that live inside the roots of plants like peas and beans. What do? Oh, they just pull vital nitrogen right out of thin air and feed it to the plant. It's like a built-in, all-natural fertilizer factory. So when you pull it all together, from the cells that literally build our bodies to the microbes that keep our planet running, you realize this invisible world isn't some strange, faraway place. It's a fundamental part of us. It's not just around us, it's in us, which really leaves you with one last question to chew on. What other critical, hidden systems are running our lives that we're overlooking every single day? You know, you open up your phone, turn on the TV, and you're just flooded with health headlines. It's a lot. And it makes it really tough to know what we should actually be focusing on. So in this explainer, we're going to cut right through all that noise and get some real clarity on the biggest health challenges we're facing today. So let's just start with a number that's almost impossible to wrap your head around. The Indian Council of Medical Research found that over 100 million people in India are now living with diabetes. Just think about that for a second. That's a massive, massive number. And then you've got this other threat, one that's literally right in our hands all day long. For kids especially, all this screen time isn't just about needing glasses. It's being directly linked to some really serious stuff: obesity, problems with sleep, and even anxiety. And it's not just what we're putting in our bodies, it's the very air we breathe. Air pollution isn't some far-off environmental issue anymore. It's a full-blown public health emergency, causing everything from a nagging cough to severe asthma. Okay, so diabetes, screen time, pollution. It just feels overwhelming, right? It kind of brings us to the big question we're trying to answer here. In this crazy modern world, what does being healthy even mean anymore? To even begin to answer that, we've got to get on the same page about what health really is. Because as it turns out, it is so much more than just not having a cold. The World Health Organization gives us a great definition. They say true health is a state of complete well-being. And check this out, it's across 3 areas: physical, mental, and social. So it's not just about your body, it's about your mind and your connections with other people too. All 3 have to be working together. All right, to make sense of all these different threats flying at us, we can actually sort them out with a really simple framework. Believe it or not, it all comes down to just 2 basic types of disease. Yep, pretty much every health threat can be dropped into one of 2 buckets: On one side, you've got your non-communicable diseases. Think diabetes or cancer. You can't catch these from somebody else. They're linked to our lifestyle, our genes, and our environment. Then on the other side, you have the communicable diseases. These are the ones caused by germs, pathogens, that can spread from person to person, like the flu. Honestly, just understanding this one difference is the key to everything. So first up, let's dive into that non-communicable bucket. People often call these lifestyle diseases, and for good reason. They're incredibly connected to how we live our day-to-day lives. And this right here is why this is so important. The whole health landscape has done a complete 180. These non-communicable diseases, or NCDs, are now the #1 cause of death in India. That is a huge change from our parents' or grandparents' generations, where infections were the biggest killer. So, what's causing this massive shift? Well, it's the small, daily choices. Things like eating a lot of processed, sugary foods, not moving our bodies enough, being overweight, and of course, things like tobacco and alcohol. These factors are really what's driving this whole epidemic of NCDs. Okay, let's switch gears and talk about that other category, communicable diseases. These are the classic infections, right? The threats that come from outside our bodies and try to get in. And the villain in this story has a name, the pathogen. It's just a catch-all term for any tiny troublemaker, like a bacterium or a virus that can invade our bodies and make us sick. So how do these little villains get around? Well, they're pretty clever. They can travel through the air when someone coughs or sneezes. They can hide out in food or water. They can pass from person to person through a simple handshake, or even hitch a ride on an insect like a mosquito. They've got a lot of ways to get to us. So now that we get the two major types of threats, we can talk about our most powerful weapon against them, which is, you guessed it, prevention. It really is all about building up our defenses before we get sick. I mean, if you want to see the power of prevention, just look at the story of the very first vaccine. It all started back in the 1700s when a doctor named Edward Jenner noticed something funny. Milkmaids who got this mild disease called cowpox, well, they just never got the deadly disease smallpox. So he tested his idea, and it worked. That single, brilliant idea led to a global campaign that completely, totally wiped smallpox off the face of the planet by 1979. How incredible is that? So what's the magic trick here? It's actually really simple. A vaccine is basically a training camp for your immune system. It introduces a safe, weakened, or dead piece of a germ so your body can study it, learn its weak spots, and be ready to destroy the real thing if it ever shows up for a fight. But, okay, what happens if we do get sick? Well, for some infections, we have treatments, like antibiotics. But, and this is so important, they are not a magic pill for everything. Antibiotics are highly specialized weapons. They only work against bacteria. They do absolutely nothing to viruses like the common cold or the flu. Zero. And that leads to a huge problem that, frankly, we've created. By using antibiotics when we don't need them, like for a virus, or by not finishing the whole prescription, we've basically given bacteria a training ground to evolve and get stronger. And now, some common infections are becoming really, really hard to treat. So it makes you stop and ask a pretty serious question, right? We have this amazing medical tool that has saved countless lives, but are we using it wisely? Are we protecting it so it will still be there for our kids and their kids? Okay, let's pull this all together. It all comes down to building your own personal health toolkit. Simple things, right? Washing your hands, keeping your space clean. That's your #1 defense against those communicable diseases, those outside germs. And then eating good food, moving your body, getting enough sleep, managing stress, those are your absolute best weapons against those non-communicable lifestyle diseases. It really does come down to these fundamentals. So there you have it. We've taken this big, confusing world of health and broken it down into two main threats and a toolkit to fight them both. The only question left is for you. Now that you know the difference, what's the one thing in that toolkit you're going to start focusing on first? What's your next move? So what's really going on inside a simple electrical wire? You know, it's not just a flow of energy. There are these invisible forces at work. And in this explainer, we're going to uncover two of electricity's most powerful and often totally hidden effects, magnetism and heat. Okay, let's kick things off with a little story from a school science fair. So there's this student, Sumana, and she built a model crane. But here's the cool part. Instead of a regular hook, she uses an iron nail, just wrapped in some wire. And when she flips a switch, that nail acts exactly like a magnet.
I mean, how cool is that? It's a pretty fascinating observation, right? And it brings up this huge question that scientists actually started wrestling with more than 200 years ago. So let's dive into that first hidden force, the wild connection between electricity and magnetism.
All right, so how on earth did that nail suddenly become a magnet? Let's break it down. We're going to look at this homemade gadget, which, by the way, has a name. It's called an electromagnet. And what's amazing is just how simple this whole setup is. The students in our story, they were so fascinated, they went ahead and built one themselves. All you really need are three basic things: some insulated wire, an iron nail to be the core, an electric cell, like a regular battery, to give it some juice.
And here it is, the magic moment. The second you connect those wires to the battery, electricity starts flowing through that coil of wire, and bam! Suddenly the iron nail can pick up paper clips. But what do you think happens when we cut the power?
Yep, the instant that circuit is broken, the paperclips just fall. This tells us something super important. The magnetism isn't permanent. It's completely dependent on that electric current. To put it simply, no current, no magnet. Simple as that. Okay, so to really understand what's happening here, we need to rewind a bit. We've got to go back to the key scientific discovery that first blew the lid off this hidden connection between electricity and magnetism. So, this whole idea is based on a huge discovery made way back in 1820 by a scientist named Hans Christian Ørsted. He noticed something absolutely mind-blowing happens when you run an electric current near a simple magnetic compass. So check this out. This is the key. With the circuit off, the compass needle does what it always does. It points north. No surprise there. But the moment you close that switch and let the current flow through the wire, the needle twitches. It deflects. It actually moves. And that tiny little movement, that was everything. It was the proof everyone needed. An electric current creates its own invisible magnetic field all around it. That is the magnetic effect of electric current, and it's the core principle behind that whole science fair project.
Okay, great. So now we know that a current creates a magnetic field. The obvious next question is, well, how do we crank it up? How can we make that field even more powerful so we can actually use it for things? Well, it turns out we have two main dials we can turn to control the strength. First, you can increase the current. More juice means a stronger magnetic field. Makes sense, right? And second, you can wrap more turns of wire around the core. Every single loop adds its own bit of magnetic force, so the more loops you have, the more you concentrate that field and the stronger the whole thing gets. And believe me, we use this trick, this controllable magnetism, absolutely everywhere. It's the force that makes an electric bell ring, it's what spins the motor in your fan, and it's even what powers those gigantic cranes and scrapyards that can lift an entire car with just the flip of a switch. But hold on, magnetism isn't the only hidden thing happening inside that wire. Nope. There's a second, equally important force at play, and it's one you've definitely experienced yourself. Think about it. Have you ever held onto an electromagnet that's been running for a bit? Or maybe just felt your phone charger after it's been plugged in for a while? You've probably noticed it gets warm, right? Well, that is not an accident. This is what's known as the heating effect of electric current. Basically, as electricity tries to flow through a wire, the wire itself pushes back a little bit. It has resistance. And that resistance, it's kind of like friction. It turns some of that electrical energy into plain old heat. Now, sometimes this heat is just wasted energy. But we humans are clever, right? We've figured out how to harness it. This effect is exactly how your toaster works. It's how an electric kettle boils water and how a hairdryer blows hot air. We've literally turned this side effect into a feature to create heat whenever we want it. Okay, so we've got these two powerful effects, magnetism and heat, and they're both powered by the flow of electricity. But where does that electricity actually come from? To answer that, we need to peek inside the battery. The very first batteries, which were called voltaic cells, made electricity using straight-up chemistry. The idea was you take two different kinds of metal plates, those are your electrodes, and you dip them into a special liquid solution, an electrolyte. When you do that, a chemical reaction kicks off that basically pushes electric current out and through a circuit. And what's really cool is you can actually see this basic principle in action at home with, of all things, a lemon. The acidic juice in the lemon acts as the electrolyte,
If you stick two different metals in there, say a copper wire and an iron nail, you can generate a small but totally real electric current. How neat is that?
Now, obviously, carrying around a jar of liquid acid to power things isn't exactly practical, right? That's why the disposable batteries we use today are called dry cells. They work on the exact same chemical principle, but that sloshy liquid electrolyte has been replaced with a much more convenient and tidy, moist paste.
But of course, we didn't just stop with disposable batteries. Technology kept marching on, and now, almost all of our modern gadgets, phones, laptops, you name it, they all rely on rechargeable batteries like lithium-ion. We can charge them up and use them hundreds and hundreds of times. And if you look to the future, the next big leap is already on the horizon: solid-state batteries. The idea here is to get rid of the liquid or paste electrolyte altogether and replace it with a solid material. And this is a huge deal. It promises to make our devices safer, last way longer, and charge up a whole lot faster.
So think about that. We started this whole journey with a simple nail at a science fair that magically became a magnet, and we've ended up talking about the chemical reactions that are going to power our future. These hidden forces of electricity, magnetism, and heat, they're literally all around us. The real question is, as we get better and better at controlling them, what incredible things will they power next?
Have you ever really thought about what makes a ball fly through the air? Or what pulls you down a slide? Or even what stops your bike when you slam on the brakes? Well, it all comes down to these invisible pushes and pulls that are happening all around us, all the time. We call them forces. And today, we're going to pull back the curtain and see exactly how they work. To get us started, let's picture this. Two friends, Sonali and Regini, are out on this amazing bike ride. They feel the wind pushing against them, so they use their own strength, their own force to pedal harder. But then they start going down a hill, and even when they stop pedaling, they feel this awesome pull speeding them up. And Sonali asks the perfect question for us today. What is that something? What are these invisible forces at play?
All right, here's our game plan. First, we'll get into the world of forces. Then, we'll look at what a force can actually do. We'll check out the forces you can feel, and then the ones that work from a distance. And we'll wrap it all up by finally clearing up the whole gravity, mass, and weight thing. Let's do it.
So let's get right to it. What are these mysterious pushes and pulls that Sonali and Regini were feeling on their bike ride?
At its heart, it's actually super simple. A force is just a push or a pull. That's it. But here's the really important part. A force always happens because of an interaction between two different objects. You can't just have a push out of nowhere, right? You need a pusher, and you need something being pushed. It's always a two-way street. And, of course, this being science, we have to have a way to measure it. The standard unit we use for force is called the Newton, named after the one and only Sir Isaac Newton. We just write it as a capital N. So, whenever we talk about how strong a push or a pull is, we're talking in newtons. Okay, so we know what a force is, but what does it actually do? Well, it turns out a force can have four major effects on pretty much any object. Think of a force as a total game changer for an object. It can take something that's just sitting there and make it move. It can change how fast it's going, change which way it's going, or it can even change its actual shape. First up, a force can get things moving. Picture a soccer ball sitting perfectly still on the grass. It's not going anywhere, right? But then you come along and kick it. You apply a force and bam, it's flying down the field. That's force in action, creating motion from nothing. Next, force can change an object's speed. This is exactly what Sonali and Rajini were doing. When they wanted to go faster, they pedaled harder, applying more force to speed up. And it works the other way too. Hitting the brakes on your bike applies a force that decreases your speed. So speed up, slow down, it's all about force. Third, a force can change direction. Remember when the cyclists saw those sheep and had to swerve? By turning the handlebars, they applied a force that changed the direction of the bike. I mean, anytime you steer a car, a bike, or even a shopping cart, you're using force to change your path. And finally, a force can literally change an object's shape. Think about squeezing an inflated balloon or stretching out a rubber band. You're applying a force, and the object is deforming right in your hands. So forces don't just affect motion, they can affect the physical form of things too. Now that we know what forces can do, let's start sorting them out. We're going to begin with the ones that make the most sense to us, the ones that happen through direct touch. We call these contact forces. So you can pretty much divide all forces into two big categories:
On one side, you have contact forces. These are the pushes and pulls that happen only when two things are physically touching each other. And on the other side, we have the more mysterious non-contact forces, the ones that seem to work like magic across empty space. Let's tackle the contact forces first. The contact force we're all most familiar with is, without a doubt, muscular force. This is the force that our own bodies create. Every single step you take, anything you pick up, and every time Sonali and Ragini pushed down on those pedals, that was all muscular force, coming straight from their muscles contracting.
The other huge contact force is friction. Now, friction is basically the force that always tries to stop things from moving. It's the ultimate killjoy for motion. Remember when the cyclists hit that rough patch of road and had to pedal harder? That was friction fighting against them, and it always acts in the opposite direction of whatever way you're trying to go. So that brings up a really good question, right? Why is it so much easier to slip on a wet floor? Well, it's all about friction. That water gets between your shoes and the floor and acts like a lubricant, which drastically reduces the friction. Less friction means less grip, and suddenly you're on a slippery slide you didn't ask for.
Okay, we've talked about the forces we can feel directly. But now, what about those weird ones, the ones that seem to act like magic, with no touching involved at all? These are our non-contact forces.
There are three main types we're going to look at here. First, there's magnetic force. You know this one. It's that invisible push or pull you feel when you play with magnets. Then you've got electrostatic force, which is the reason a balloon sticks to the wall after you rub it on your hair. And finally, the big one, the one that affects everything, gravitational force, the pull that keeps our feet on the ground. And that gravitational force is the perfect transition to our last section. We're going to take a really close look at gravity because it's behind one of the most confused ideas in all of science, the difference between mass and weight. So let's clear this up. What is weight? In physics, your weight isn't just a number you see on a scale. Your weight is specifically the measure of the force of gravity pulling down on you. And since weight is a force, what's its official unit? You guessed it, the Newton. Okay, this is the most important part to get. Mass is the amount of stuff you are made of, the atoms and molecules. That amount doesn't change no matter where you go in the universe. We measure it in kilograms. Weight, on the other hand, is the force of gravity pulling on all that stuff. And because gravity is different on, say, the moon versus the Earth, your weight can actually change. And this chart makes it so clear. Let's take an object with a mass of 1 kilogram. That mass is 1 kilogram here on Earth, on the moon, on Mars, anywhere. It's constant. But look at its weight. Here on Earth, it weighs about 10 newtons. But take it to the moon, where gravity is much weaker, and it only weighs 1.6 newtons. Your mass stays the same, but your weight totally depends on where you are. Pretty cool, huh? So we've seen how forces are the engine of all change in the universe. They get things moving, they change directions, they shape our world through contact and from a distance. But I want to leave you with one last thing to think about. What happens when all the forces acting on an object are perfectly balanced? When the pushes and pulls all cancel each other out? Well, that state of perfect balance, that's a whole other amazing part of the story.
All right, we're going to uncover an invisible force that connects something as simple as an uncomfortable backpack to one of the most powerful, destructive events in nature, a cyclone.
It sounds like a riddle, right? But believe it or not, the answer comes down to one single fundamental idea that explains both why your bag feels heavy and how a massive storm gets started. So yeah, let's dive in. Okay, so you know that feeling when you're carrying a heavy bag? The source material talks about two kids, Mega and Pawan. They've got identical bags, same weight inside, but Pawan's is killing his shoulders. Why? His bag has these skinny little straps. Mega's, on the other hand, has broad straps, and she's totally fine. That difference right there, that's pressure in action.
So here's the crucial point. It's not just about how much force you're applying, the weight in the bag. It's about how concentrated that force is. The exact same force can feel completely different depending on how big or small the area it's pushing on is.
And this one idea explains so much stuff we see every day. It's exactly why a sharp knife cuts so easily. It focuses all your force onto that tiny little edge. It's why a nail goes into a piece of wood pointy end first. You take the same force, shrink the area, and boom, you get immense pressure.
Now, this whole principle isn't just for solid things like backpacks and nails. Not even close. It is absolutely everywhere. So next up, let's see how this exact same concept works with liquids and even the air we're breathing right now.
You've probably noticed this, right? Water tanks are always on the roof or up on a tower. Well, it's all about liquid pressure. The source explains that the pressure a liquid creates depends on the height of its column. So the higher up that water is, the more pressure there is at the bottom. And that's what gives you that good, strong flow when you turn on the tap.
Okay, now get ready for this number, because it's pretty wild. The air in our atmosphere is heavy, and it's always pushing down on us. The source says that the force of the atmosphere on a little area of just 15 by 15 centimeters, that's about the size of a small notebook, is equal to the weight of an object with a mass of 225 kilograms. That is a lot of weight.
I mean, really think about that. That is an absolutely mind-bending amount of force pushing on us from all sides. So what's stopping all that air from just flattening us into pancakes every single day?
Well, the reason is actually pretty elegant. Our bodies have their own internal pressure. You know, all the fluids and gases inside of us are pushing outward with a force that perfectly matches the atmospheric pressure pushing inward. It's this incredible invisible equilibrium. And understanding this whole balance thing is key, because as soon as that balance gets disrupted, when the pressure isn't the same everywhere, well, things start to move. And this is literally how we get wind.
It's a fundamental rule of the universe, really. Nature always wants to even things out. So air is always going to flow from a crowded, high-pressure spot to a less crowded, low-pressure spot. Think about air rushing out of a punctured tire. Same exact idea.
A perfect example of this happens at the beach every single day. During the day, the land heats up way faster than the water. That hot air over the land rises, creating a low pressure. Meanwhile, the air over the cooler sea is a high-pressure zone, so it rushes in to take the place of that rising warm air. And that is your sea breeze. Then at night, the whole thing reverses, all because of a simple difference in pressure.
Okay, so if pressure differences create a nice, gentle breeze, what happens when that difference is huge? What happens when the wind gets incredibly, incredibly fast? What else does it do?
This question, which comes right from our source material, gets us into some really fascinating and honestly kind of weird physics about what happens when air starts moving really, really fast.
That's right. This is where it gets a little counterintuitive. You'd think faster wind means more pressure pushing down, but it's the exact opposite. The faster the air moves over a surface, the less pressure it puts on that surface. You can try it yourself. If you blow between two balloons, they actually move together because you created a low-pressure zone between them.
And this is the secret to why roofs don't get pushed down in a storm, they get lifted off from below. The super fast wind racing over the top of the roof creates a low-pressure zone, but inside the house, the air is just sitting there at normal pressure. So now the pressure inside is higher than the pressure outside, and it literally pushes the roof up and away. The source even says that opening windows can sometimes help even out that pressure difference.
All right, let's scale this up one last time. We're going to take all these same ideas, low pressure, high pressure, rising air, and fast winds, and see how they combine to create the most powerful storm on Earth, a cyclone.
You can think of a cyclone like a giant, self-sustaining engine. It all starts with warm, moist air rising, which creates this super low-pressure spot. That rising water vapor turns into clouds, releasing heat, which makes the air rise even faster. This just sucks in more air from all around, and as that air rushes in, the Earth's rotation gives it a spin. This whole cycle just feeds itself, growing bigger and more powerful.
And the results of that engine are just devastating. We're talking winds up to 270 kilometers per hour, but one of the most dangerous parts is something called the storm surge. The powerful winds actually push the ocean into a huge mound, creating a massive wall of water, sometimes up to 12 meters high, that just crashes onto the land and floods everything. So when you boil it all down, it's pretty incredible. That one simple rule we started with, force divided by area, is the single thread that connects everything. It explains the backpack strap, the sharp nail, the sea breeze, the roof lifting off in a storm, and even the formation of a hurricane. And that brings us to a final thought to chew on, a question from our source material. We know that we'd still have pressure differences, right? So the wind would still blow. But without the planet's spin to give it that crucial twist, would these massive, rotating monster storms even exist? That's definitely something to think about.
Have you ever just looked around at the world, at a solid rock, a flowing river, or even the air you're breathing, and wondered,
what is all this stuff actually made of? Well, today we're going to go on a little investigation, a microscopic journey to uncover the one fundamental secret behind pretty much everything you can see and touch.
Okay, so to get started, let's chew on a simple puzzle. You can go to the beach and build a sandcastle, right? You can stack up all those little grains of sand. But have you ever tried to stack water? No way. It just flows all over the place. Why is that? And think about this too. You pour water into a glass and boom, it takes the shape of the glass. It doesn't really have a shape of its own. What's going on there on a level that we can't even see that lets it do that? And finally, what about a balloon? You can't see the air going in, but it totally inflates. It takes up space. It even gets heavier. Now, these questions might seem kind of basic, but the answers reveal the very nature of matter itself. So, to start finding some answers, we're going to need a clue. And lucky for us, we can find a really good one in something as simple as a piece of chalk. Just picture this experiment. You take a whole piece of chalk, you snap it in half, then you grind those pieces into a fine powder. But what if you could just keep going, grinding it down smaller and smaller and smaller, way past what your eyes could ever see? You know, eventually you'd have to reach a single, fundamental little speck of chalk, a particle so tiny that you just can't break it down any further. And that final, unbreakable little piece, that's what we call a constituent particle. And here is the big reveal, the first major clue in our investigation. Everything, the chalk, the sand, the water, is made up of a bazillion of these incredibly tiny particles.
Okay, I know what you're thinking. That's a huge claim. If these particles are way too small for us to see, how can we be so sure they're even there? We're going to need some proof.
So let's investigate with a little experiment you can literally do in your kitchen. Stir a couple of spoons of sugar into a glass of water. You stir it up, and after a moment, poof, the sugar crystals are gone. But you can still taste the sweetness, right? So where did the sugar go? The sugar didn't just vanish into thin air. Nope. It broke down into its own tiny constituent particles. Particles so small they were able to slip right into the gaps that were already there, in between all the particles of water. And that is our second major clue. So get this, matter isn't some solid, continuous block. It's actually more like a jar that's full of marbles. There are empty spaces between every single one. We call these interparticle spaces. And this simple idea that matter is actually mostly empty space is absolutely key to understanding how it all works. Let's see how this all starts to build. We've got two huge ideas now. All matter is made of particles, and there are spaces between them. With just one more concept, we can explain the difference between solids, liquids, and gases. And that final concept is something called interparticle attraction. You can think of it like an invisible force, like tiny little magnets that are always pulling all the particles toward each other. The strength of this attraction, this sort of invisible glue, is what really decides if something is a solid, a liquid, or a gas. And this table here, it just brings it all together beautifully. In a solid, see, the particles are packed super tight, and that attraction force is really strong. It locks them into a definite shape. But in a liquid, the attraction is weaker, so the particles can kind of slide past each other, which is why they take the shape of their container. And in a gas, well, the attraction is basically zero. The particles are far apart and just fly around to fill up whatever space they can. So we've got particles, we've got spaces, and we've got attraction. But you know what? There's one more piece to this puzzle. These particles aren't just sitting there. They are unbelievably dynamic. And what's amazing is that this isn't some brand new idea. Thousands of years ago, an Indian philosopher named Acharya Kanad was talking about Parmanu, these eternal, indivisible particles. How cool is that? Ancient wisdom was already hinting at modern science. And here it is, the key. These little particles are in constant random motion, all the time, even in a solid object that seems perfectly still, like your desk. Its particles are just vibrating like crazy in their fixed positions. They never truly stop moving. We can actually see this motion in action. If you drop a bit of dye into some cold water, it spreads out really slowly because the water particles are just moving sluggishly. But put that same drop of dye in hot water, it spreads almost instantly. Heating something up is basically like giving its particles a shot of espresso. It gives them more energy and makes them move way faster. This is exactly what's happening when a solid melts or a liquid boils. But what about gases? We can't see their particles,
but we can definitely detect their movement. For instance, you light an Ncert stick in one corner of a room. How does that smell get all the way over to the other side? Well, it's because the air in the room isn't empty, right? It's jam-packed with constantly moving air particles, and they're all bumping into the fragrance particles from the incense, just knocking them around like a game of pool until they've spread out everywhere. It's a perfect demonstration of gas particles in motion. Okay, so we've gone deep into this invisible, microscopic world. But why does any of this matter in our regular, everyday lives? What's the big deal?
This one single theory explains so much about our world. It's why you can't pile up water. Its particles just slide past each other. It's why air fills a balloon. Its particles are free to fly around and fill any space. It explains why you can smell incense across a room and why salt dissolves in the ocean. The behavior of these tiny, invisible particles literally shapes everything we see and experience every single day.
So, to wrap this all up, let's just quickly review the big ideas we've uncovered. 1. All matter is made of tiny particles. 2. There are empty spaces between them. 3. They're attracted to each other. 4. They are always moving. And 5. The way all these simple rules play together is what creates the entire physical world as we know it. And I'll leave you with one final thought to really chew on. If a chair is nothing more than a specific arrangement of particles and the empty space between them, what would be left if you could magically snap your fingers and make every single one of those particles disappear? What even is the chair itself? Thanks for tuning in.
Hey everyone, today we're going to do something pretty wild. We are going to deconstruct our entire world. I mean, everything you can see, everything you can touch, we're going to break it all down to its most basic, fundamental parts. So let's just dive right in.
I mean, really think about it for a second. It feels like this huge, complex question, right? But the answer is actually way simpler than you might think, and it is absolutely fascinating. We're about to take a journey from the everyday stuff all around you down to the very tiny particles that make it all possible.
And right there, that's our starting point. The air, the water, your phone, no matter how different they seem, they all share one fundamental thing. They're all matter. You know, they have mass, they take up space. But here's the cool part. Almost everything we see isn't just one thing. It's actually a combination of lots of different things all jumbled together.
So here's our game plan. We're going to start with something we all know, mixtures. Then we're going to start peeling back the layers, kind of like an onion, to uncover pure substances, then elements, and then compounds. And to wrap it all up, we'll see why this tiny, microscopic stuff has a huge, massive impact on our world.
All right, let's kick things off with mixtures. This is literally the science hiding in plain sight. In your salad, in your soda, you're dealing with them all day, every day, and you're probably not even thinking about the amazing chemistry that's going on.
So, what is a mixture, really? Well, the key thing to remember is that the ingredients don't actually change. They're just hanging out together. Each one keeps its own identity. Think about it. In a salad, a tomato is still a tomato. A piece of lettuce is still lettuce. You could, if you really wanted to, pick every single piece out. That's a mixture.
And mixtures come in two main flavors. On the one hand, you've got your non-uniform mixtures, like that salad. You can easily see all the different bits and pieces. But on the other hand, you've got uniform mixtures. Imagine dissolving sugar in water. It's definitely still a mixture, but those sugar particles are spread out so perfectly, so evenly that you just can't see them anymore.
And you know, mixtures are not just about tossing solids into liquids. Nope, they can be any combination you can think of. The air we're breathing right now, that's a mixture of gases. Soda is a gas mixed into a liquid. And what I think is super cool is that you can even have mixtures of solids. That's how we get really strong materials like steel.
Okay, so we've talked about mixing things together. Now let's go in the complete opposite direction. Let's talk about pure substances. And to do that, we kind of have to forget what we think pure means and learn the scientific definition. It's a bit of a mind bender.
Right, so in everyday life, pure just means, nothing bad has been added. But in science, pure means something incredibly specific. It's made of only one type of particle. This is why something like milk is not scientifically pure. It's actually a mixture of water, fats, proteins, all sorts of stuff. A true pure substance can't be separated by any physical means. You can't just pick the parts out.
So if you can't separate a pure substance physically, can you break it down at all? I mean, what happens if we take something we know is pure, like water, and we try to break it?
And we can! This is such a cool experiment. You run an electric current through water,
and you start seeing these bubbles form. But these aren't just air bubbles. When you test them, one of the gases makes a little pop sound. That's hydrogen. The other gas makes a flame burn brighter. That's oxygen. We just literally ripped pure water apart into two completely new things.
And that brings us to the next level down, the element. The hydrogen and oxygen we just made, those are elements, and we call them that because you just can't break them down any further. This is it. This is rock bottom. These are the fundamental Lego bricks of our entire universe.
And to give you some perspective, we know of 118 of these elemental building blocks. The vast majority of them are solid, like iron or gold, 11 of them are gases, and get this, only 2 are liquid at room temperature, a metal, mercury, and a nonmetal, bromine, just 2.
Okay, so we found our building blocks, the elements. Now for the really exciting part. What happens when they don't just mix, but they combine? This is where we move beyond just a simple jumble of things and start creating something completely, totally new.
This quote just says it all. It blows my mind every time I think about it. You take hydrogen, which is a fuel. You take oxygen, which fire needs to burn. You'd think putting them together would make some kind of super fire, right? But no. When they combine chemically, they make water, which puts fires out. The new thing is nothing like the parts that made it.
And that new substance is called a compound. It's when elements are chemically locked together in a specific recipe, a fixed ratio. And the result is a substance with brand new properties. It's not a mix, it's a total transformation.
Here's the perfect way to see the difference. In sample A, we just mix some iron and sulfur together. You can still see the little yellow and black bits, and a magnet can pull the iron right out. It's just a mixture. But in sample B, we heat them up. They react. Now it's a new black substance. A magnet does nothing to it. And if you add acid, you get a completely different gas that smells like rotten eggs. See, it's a whole new thing, a compound.
So, elements, mixtures, compounds. Why do we care? Why does any of this matter? Well, because understanding this stuff is the absolute foundation for basically all modern innovation. Let's look at how these simple ideas build our entire world. Seriously, understanding these building blocks is like having a superpower. It's what lets scientists invent life-saving medicines. It's how engineers design super strong, lightweight materials for planes and buildings. The smartphone in your hand is a miracle of manipulating elements and compounds. This knowledge is behind almost every piece of technology we have. And if you want to see just how far we can take this, look at this. This is graphene aerogel. It's made from just one element, carbon, the same stuff in a pencil lead. But it's arranged in this incredible delicate structure that makes it the lightest solid material on the entire planet. This stuff could change everything from space travel to electronics. That's the power of knowing your building blocks. So there you have it. We went from a simple salad all the way down to the fundamental elements of the universe. We've learned the rules for how they mix and how they can combine to create amazing new things. So the only real question left is, now that we know what the world is made of, what are we going to build next?
Have you ever really thought about the simple magic happening right there in your glass? You know, whether it's a sports drink or just a cup of tea, there's this incredible, invisible science at play. It's what decides how things mix, what floats, and what sinks. So today, let's pull back the curtain and see what's really going on. I mean, seriously, think about it for a second. When you mix up an oral rehydration solution, an ORS, with some salt, sugar, and water, how is it that every single sip tastes perfectly balanced? It's not like you get a mouthful of salt and then a mouthful of sugar, right? So what's the secret inside that glass? Well, the answer is hiding at a level we can't even see, the microscopic level. It's all about creating that perfectly mixed drink. And the first thing you need to know is that not all mixtures are created equal. Not at all.
Okay, so check this out. On one hand, you have salt in water. You stir it up and poof, the salt just seems to vanish, spreading out perfectly. That's a uniform mixture. But on the other hand, you try the same thing with sand in water, and the sand just says, nope, and sinks right to the bottom. That's a non-uniform mixture. And that perfectly blended, uniform kind, well, it has a special name. That special name is a solution. And to really get what a solution is, we need to meet its two key players, the solute and the solvent. So yeah, that perfectly mixed drink is called a solution. It's when things are mixed so well, so evenly, that you can't even tell the different parts apart anymore. Your sports drink, your lemonade, your morning coffee, all of them are classic examples of solutions. First up is the solute.
The solute is basically the stuff that gets dissolved. So in our ORS drink, the salt and the sugar, both of those are solutes. They're the ingredients that look like they're disappearing.
And then you've got the solvent. The solvent does all the heavy lifting. It's the thing doing the dissolving. Water is an amazing solvent, which is why we call it the universal solvent. It's usually the liquid you have more of. So it's pretty simple. You add a solute to a solvent, and boom, you get a solution.
And get this, it's not just about liquids. The very air you're breathing right now is a solution, a gaseous one. Since there's more nitrogen than anything else, nitrogen acts as the solvent, and oxygen and all the other gases are the solutes dissolved in it. How cool is that? Okay, so this brings up a pretty logical question, right? If you're stirring salt into a glass of water, can you just keep adding spoonful after spoonful forever, or is there a point where the water just gives up? Well, it turns out there is absolutely a limit, a very clear one. And when a solvent hits that limit, we say it has reached its saturation point. I want you to picture this. You take a glass of water, you add 1 spoonful of salt, give it a stir, it's gone. Dissolved. You add another one, same thing. But then you get to a point where you add 1 more spoonful, and it doesn't matter how long you stir. It just sinks to the bottom. That right there, that is the saturation point in action. This brings us to 2 really important terms. As long as that water can still take on more salt, we call it an unsaturated solution. It's got more room. But the second it hits that wall and can't dissolve another crystal, it becomes a saturated solution. It's full. But here's a neat little trick. What if you want to dissolve more stuff? Well, for most solids, all you have to do is add a little heat. Heating up a solvent, like water, gives its molecules more energy. They start moving around faster, making more room for solute particles to squeeze in. It's exactly why you can dissolve way more sugar in hot tea than you can in iced tea. Okay, so we've got a handle on things that dissolve, but what about the stuff that doesn't dissolve at all? Think about oil and water. They just don't mix. And notice something else? The oil doesn't sink like that extra salt did. It floats right on top. This opens up a whole new can of worms. Why do some things float and other things sink? Answering this question takes us out of the world of chemistry and drops us right into the world of physics. And trust me, the answer isn't as simple as you might think. You know, we often just say something floats because it's lighter. I mean, an iron bar feels way heavier than a wooden log of the same size. But in science, we need to be a little more precise. And the real word for this property, the one that truly explains everything, is density. Yep, understanding density is the key. It's the final piece of the puzzle that unlocks why some things float and others take a dive. So what exactly is density? It's actually pretty simple. It's just the amount of stuff, or mass, that's packed into a certain amount of space or volume. The formula is super straightforward. You just take the mass of an object and divide it by its volume. That's it. Here's a great way to think about it. Picture a bus that is totally packed with people. That's high density, lots of mass and a small volume. Now picture that exact same bus, but with only a few people scattered around. That's low density. The space, the volume of the bus, didn't change, just the amount of stuff inside it. Now, if we look at some actual numbers, the rule becomes crystal clear. An object with a lower density than the fluid it's placed in will float. See? Both oil and ice have a density just a little less than water, and what do? They float. But aluminum, it's way, way denser than water, so it sinks like a rock, every time. And this rule doesn't just apply to solids and liquids. When you heat up air, its particles get all excited and spread out. The mass stays the same, but the volume gets bigger, which means its density goes down. So that less dense hot air literally floats up through the cooler, denser air around it. That is exactly how a hot air balloon works. So you see, density isn't just some random concept from a textbook. It fundamentally shapes our entire world. The fact that ice is less dense than water is huge. It means lakes freeze from the top down, creating an insulated layer so fish can survive the winter. It's a simple property with truly massive consequences. All right, to wrap things up, I'm going to leave you with a little brain teaser. An unpeeled orange will float in a bucket of water. But if you take that peel off, the orange sinks straight to the bottom. So, now that you know all about mass, volume, and density, can you figure out why that happens? It's a fun one to think about. Hey everyone, and welcome. Today we're going to dive into some amazing physics that's hiding in plain sight. We're talking about the simple curves and mirrors and lenses that bend light, kind of warp reality, and honestly make our modern world possible. And it all kicks off with one very familiar question. Right? You've seen this 1,000 times on your car's side view mirror. But have you ever really stopped to wonder why? Why does that mirror lie to you? And why is that lie actually a really important safety feature? It's a fantastic question.
And believe it or not, that one little warning, that's our key. If we can answer this one question, we can unlock the principles behind literally everything, from a funhouse mirror to a magnifying glass to a giant telescope and even the lens inside your own eye.
So, let's start there. Let's solve the mystery of mirrors. We'll kick things off with an experience I bet a lot of us have had, seeing our reflections do some very, very strange things. Just imagine you're at a science center. You walk up to a bunch of those cool, curved mirrors. In one, your face is suddenly enormous. In the next one over, you're a tiny, shrunken version of yourself. And in the third one, if you take a step back, whoa, you're suddenly upside down. So what is going on here? Well, unlike a flat mirror in your bathroom, these are spherical mirrors. And their curve, that's where the magic is.
The solution to this whole funhouse mystery, it really just boils down to two basic types of curved mirrors, concave and convex. If you can get these two shapes, you can explain everything.
And here's the best part. You don't need a science center to see this for yourself. Just go grab a shiny spoon. The inside of the spoon, you know the part that holds the soup, it curves inward like a little cave. That's a concave mirror. Now flip it over. The back of the spoon, which bulges outward, that's a convex mirror. This one simple thing shows you both types of curves perfectly. Okay, now let's actually look at what you see in that spoon. Look into the concave side, the inside, and hold it close. Your reflection is upright, right? And it's magnified, bigger than normal. But now slowly pull the spoon away from your face, and bam, your image flips completely upside down. Now try the other side, the convex back. No matter how close or far away you hold it, your image is always upright and it's always smaller. That difference is everything. So why does this happen? Why does one side flip you upside down and the other doesn't? The answer is all about the fundamental way that light itself behaves when it hits these curves. This is the real aha moment. First, we need one quick, super simple rule that applies to all mirrors, whether they're flat or curved. It's called the law of reflection. All it means is that the angle light hits a mirror is the exact same angle that it bounces off. That's it. Simple, elegant, and it's always true. Okay, so here's secret number one. A concave mirror with that inward curve takes all the parallel rays of light that hit it and bounces them all inward. It focuses them or converges them to a single spot. This ability to gather light is its superpower. You can literally use a concave mirror to focus sunlight and burn a hole in a piece of paper. And secret number two? You guessed it, a convex mirror does the exact opposite. Its outward curve takes all those parallel light rays and spreads them out or diverges them. This makes the light look like it's coming from a much wider area, which, as we'll see, is incredibly useful. Okay, so we've cracked mirrors, which reflect light. Now let's see what happens when light passes through a curve. Let's talk about lenses. And the amazing thing is, the very same principles, converging and diverging, they still apply. Just like with mirrors, there are two main types of lenses. A convex lens is thicker in the middle and gets thinner at the edges, like a classic magnifying glass. And a concave lens is the opposite. It's thinner in the middle and thicker at the edges.
And here's where it all clicks together. A convex lens acts just like a concave mirror. It takes light rays that pass through it and bends them inward, converging them to a focal point. That's exactly how a magnifying glass makes letters look bigger or can focus sunlight to start a fire.
And you know where this is going? A concave lens acts just like a convex mirror. It takes light rays and spreads them out or diverges them. So let's just lock that in. Concave mirrors and convex lenses both gather light. And convex mirrors and concave lenses both spread light out. Now for the best part. Let's see how these simple ideas of gathering and spreading light show up absolutely everywhere, shaping our world in some incredibly useful and, frankly, brilliant ways. So, concave mirrors are light gatherers. Where do we use them? Well, think about car headlights or flashlights. They use a concave mirror to take the light from a small bulb and focus it into a powerful, straight beam. A dentist uses a tiny one to get a magnified up-close view of your teeth. And huge reflecting telescopes use massive concave mirrors to gather the faint light from stars that are millions of light years away. And what about convex mirrors, the light spreaders? Well, this takes us right back to our first question. The reason that warning is on your car mirror is because it's a convex mirror. Its diverging nature gives the driver a much, much wider field of view. Yeah, the image is smaller, which is why objects are closer than they appear, but you can see so much more of the road next to you. You see the same thing in stores as security mirrors, so one person can see the whole shop at a glance. And lenses, of course, are everywhere. From the eyeglasses that correct our vision by bending light just perfectly before it reaches our eye, to the complex systems inside cameras, microscopes, and telescopes. But maybe the most incredible lens of all is the convex lens that's right inside your own eye. And here's a final kind of mind-blowing thought for you. The convex lens in your eye works just like the simple ones we talked about, which means it projects an upside-down image onto the back of your eye, your retina. So the world you are seeing right this second is actually being flipped right side up by your brain, constantly, without you ever knowing it. It's a non-stop act of correction that literally creates your reality. Pretty wild, right? Something to think about.
For thousands of years, the only clock humanity had was hanging right over our heads, the sky itself. Today, we're going to explore how the moon and stars did way more than just light up our nights. They actually built the very framework for how we measure our days, months, and years.
Seriously, think about it. Have you ever been outside, sun shining, and you look up and there it is, a pale, almost ghostly moon? Well, that exact sight is what sparked the curiosity of a girl named Mira, and it's a mystery we're going to start with today.
So, picture this. Mira's at a kite festival. Colors everywhere, and she spots the moon. Now, she knew its shape changed. That was normal. But seeing it during the day got her thinking, why? What was really going on up there to make it change its shape every single night? Okay, first things first. Let's tackle Mira's question head on. Why is the moon sometimes a daytime guest? And what's the deal with its ever-changing look?
To really get it, we've got to decode the science behind the moon's phases. And it turns out, the secret isn't some huge cosmic event. It's really just all about your point of view.
And let's get one thing straight right off the bat. The most common misconception is that the phases are caused by the Earth's shadow. Nope, that's something totally different called a lunar eclipse.
The actual reason is much simpler and, frankly, way cooler. Half of the moon is always lit by the sun. Always. The phases we see are just us, here on Earth, getting a different view of that sunny side as the moon travels on its monthly journey around our planet.
You know, you can actually see this for yourself with a super simple experiment. Grab a ball and stand in a dark room with one lamp on. The lamp is the sun, the ball is the moon, and your head is Earth. Now, hold the ball out and slowly turn in a circle. As you turn, watch how the light on the ball seems to change. That's it. You're seeing the phases of the moon right there in your room.
So once the moon is full and bright, it starts what we call waning. That just means the part we can see getting lit up starts to shrink night after night, heading back towards being a new moon. And the opposite of that is waxing. This is when we go from a barely there sliver of a crescent and it grows or waxes bigger and bigger each night until, bam, a brilliant full moon.
Okay, so we get the phases now, but so what? Why did this simple cycle matter so much to our ancestors? Well, this is where the story pivots from just astronomy to human history, connecting these rhythms in the sky to our deep need to measure time itself.
Our whole concept of time is basically built on three giant, predictable clocks in space. The spin of the Earth on its axis, that gives us our day. The moon's full cycle of phases, that gives us the month. And Earth's big trip all the way around the sun, well, that gives us our year.
For thousands and thousands of years, this was it. The sky was the ultimate clock. It was perfectly reliable. It told you when to plant your crops, when to harvest them, and how to mark the big moments in your life. It was a universal timekeeper for everyone on the planet.
But there was a problem with this beautiful cosmic clockwork, a kind of mathematical glitch, you could say. You see, the neat and tidy cycles of the moon and the sun, they don't actually line up perfectly. And that created a massive puzzle for ancient timekeepers.
So here's the puzzle, laid out plain and simple. If you count 12 full cycles of the moon, you get about 354 days. We'll call that a lunar year.
But the time it takes for the Earth to actually go around the sun, a solar year, is about 365 days. They just don't match.
That means every single year, a calendar that only follows the moon will fall behind the seasons by about 11 days. Now, 11 days might not sound like a lot, but over a few years, that gap becomes a huge problem. Your summer festival suddenly ends up in the spring.
To fix this, different cultures came up with 3 totally brilliant solutions. Some, like in the Islamic calendar, created purely lunar calendars. They stick to the moon, which is why a holiday like Eid moves through the seasons year after year. Then you have solar calendars, like the one most of the world uses. It pretty much ignores the moon and just adds a leap day every few years to stay locked in with the seasons. And then there's the lunisolar calendar, which is this amazing hybrid. It follows the moon, but then it cleverly adds an entire extra month every 2 or 3 years to get back in sync with the sun.
And you can see these systems in action right here. Look at Eid al-Fitr. It's on a pure lunar calendar, so it moves back about 11 days every year. But now look at Diwali. It's on a lunisolar calendar. See how it shifts a bit, but that extra catch-up month keeps it anchored right there in the autumn every single year. Pretty smart, right?
So, our journey started with all of humanity looking up at one single natural satellite. But in our modern world, well, the sky has gotten a whole lot more crowded.
Think about it. For almost all of human history, the moon was our one and only companion in orbit. But in just the last 70 years or so, we've launched thousands of our own artificial satellites, creating this brand new, incredibly complex layer in the space right above our heads.
And these new man-made moons have become absolutely essential to our lives. They're the backbone of, well, almost everything, from the GPS on your phone to the weather forecast to global communications and critical scientific research. We depend on them every single day.
Which brings us to a final, really big thought. For millennia, we just watched the predictable, natural cycles of the heavens to understand our world. But now we're creating our own complex systems in orbit. So what new cycles, what new and unforeseen patterns are we setting in motion? And how are we going to manage the new challenges, like the growing problem of space junk, that come with becoming the masters of our own sky?
You know, have you ever thought about how something like adding fish to a pond could somehow make flowers bloom on the shore? Or how our taste for a certain food could, believe it or not, cause an insect plague? These aren't just weird thought experiments. Nope. They are real-world examples of this invisible web that connects everything in nature. And it turns out the smallest little ripple can create a massive wave. So today, we're going to pull back the curtain and see exactly how it all works. All right, let's start with a real-world puzzle. A mystery, really. In parts of India, something strange and honestly pretty dangerous has been happening. Elephants are leaving the safety of their forests and just wandering right into human villages. And the big question is, why? Why would they do that? I mean, seriously, think about it. Why would a massive animal, one that's perfectly at home in the wild, risk a really dangerous run-in with people? It's definitely not for a quick snack. The answer, it turns out, isn't really about the choices the elephants are making. It's about the choices being taken away from them. And that, well, that reveals a much deeper story about how nature actually ticks. The truth is, it's not a choice at all. It's an absolute necessity. Their entire world is changing. The lush places they rely on for food, they're disappearing. Water holes are just drying up. Forests are shrinking because of construction. Their world is literally closing in on them. So they're being forced into our world, really just in a desperate search for a way to survive. It's such a powerful reminder of a simple, simple truth. In nature, everything is connected. Okay, so to really get a handle on these connections, we kind of need to understand the basic rules of the game. So let's break it down and look at the 2 simple building blocks that set the stage for, well, for all of life's drama. First up is the habitat. The easiest way to think about it. It's just an organism's address. It's where it lives. But it's not just any old random spot. It's the specific place that provides everything, and I mean everything, that organism needs to survive. Food, water, shelter, the whole shebang. So every single habitat is made up of 2 key parts. On one hand, you've got the biotic components. That's just a fancy word for all the living stuff. The plants, the animals, even the tiny little microbes you can't see. And on the other hand, you have the abiotic components, the non-living things. Think water, soil, sunlight, air. And here's the kicker. You need both. They're both absolutely essential. All right, let's see how this actually works in the real world. Just take a pond and a forest. I mean, they're both habitats, right? But their building blocks are totally different. In a pond, you've got the living stuff like fish, frogs, and algae mixing with the non-living stuff like water and sunlight. But in a forest, you've got trees, birds, and deer interacting with soil, air, and temperature. See, it's that unique mix of the living and the non-living that makes each place what it is.
And when you take all of that and put it together, I mean, all the living things interacting with all the non-living things in one specific area, what you get is an ecosystem. That's the whole system, right there. The entire web of life and the physical world it lives in, all working together. Okay, so we've got the building blocks down. Now, this is where it gets really, really cool. Let's look at the truly mind-blowing part, that invisible web of connections between all those parts. And you know what? These relationships are often hiding in plain sight. So let me throw a puzzle at you, and this comes from a real scientific study. It sounds like it defies all logic. How could adding fish to a pond possibly help flowers grow on the shore? I mean, they don't even live in the same place. The answer, though, shows just how deep and weird these connections can get. You're not going to believe this chain reaction. Okay, so it all starts with the fish. They're added to the pond, and they start eating dragonfly larvae. Step 1. Well, that simple little act means fewer adult dragonflies make it out of the water. Okay, so what? Well, it turns out dragonflies love to eat bees and butterflies. They're major predators. So with fewer dragonflies flying around, what happens? The bee and butterfly populations just, boom, they thrive. And all of a sudden, you have way more pollinators visiting the flowers on the shore, which leads to better pollination, more seeds, and, you guessed it, more flowers. A tiny change in the water completely changed the land around it. How wild is that? And that right there is what a food web is all about. It's not some simple straight line, A eats B eats C. No, it's this incredibly complex, tangled network of connections. And as we just saw, if you pull on just one single thread, even a thread you think doesn't matter, the entire web can start to vibrate in really unexpected ways. So, we've seen how a small addition can have this huge effect. But what happens when a critical piece is suddenly removed? What happens when a thread in that web doesn't just vibrate, but it snaps completely? Well, here's a classic and pretty cautionary story. Back in the 1980s, there was this huge global demand for frog legs, and it led to massive overharvesting in India. What happened next was just a cascade of chaos. With the frogs, a really key predator, suddenly gone, what do you think happened? The insect populations they used to eat just exploded. This forced farmers to start using tons of heavy chemical pesticides, which just poisoned the environment even more. The damage got so bad, the government had to step in and ban the export of frog legs altogether. It's just a crystal clear example of how yanking out one single piece can make the whole system start to fall apart. And this really highlights a super important idea. The balance in nature isn't this static, frozen thing, like a statue. It's constantly shifting and adjusting. I love how the source material puts it. This balance is dynamic, not fixed. It's like a constant dance. And while it's amazingly resilient, a sudden, huge change, like, getting rid of all the frogs, can shatter that dance completely. Okay, so let's recap. We've seen the puzzle with the elephants, we've learned the basic rules of the game, and we've seen exactly what happens when those rules get broken. So now, let's bring it all home. Let's talk about why this stuff matters directly to every single one of us. Here's the bottom line, really. We are not separate from these ecosystems. Not at all. We are a part of them, and we are completely, 100% dependent on them for our own survival. And all the amazing benefits they give us, there's a name for that: ecosystem services. And just look at what those services are. I mean, these aren't luxuries we're talking about. They are the absolute fundamentals of life itself. We're talking clean air to breathe, clean water to drink, the fertile soil that grows our food, even protection from things like storms and floods. We get all of this for free from healthy, functioning ecosystems. Think about the year 1987. That's when UNESCO recognized just how valuable one of these ecosystems is. They declared the Sundarbans a World Heritage Site. And that wasn't just some symbolic pat on the back. It was a global acknowledgement of how incredibly important this place is. The Sundarbans, this place is an absolute powerhouse. It's the world's largest mangrove forest, and it acts like a natural shield, protecting coastlines from brutal storms. But here's the thing.
Even this incredibly vital ecosystem is now under threat from deforestation and pollution. The very system that protects people is being damaged by people. It's just a powerful, stark reminder of the fragile balance we are all a part of.
So I want to leave you with a final thought to chew on. This invisible web we've been talking about, it's not just off in some distant forest or a faraway pond. It's right outside your door, right in your own neighborhood. So my question for you is, what's one connection in nature that you've never noticed before, right where you live? Maybe it's the way certain bees only visit a specific type of flower. Maybe it's the birds that always show up right after it rains. I promise you, if you start looking, you'll start to see the threads of this incredible web absolutely everywhere.
You know, when you think about it, in this fast, silent universe filled with literally billions of planets, there's one that really stands out. Our home, Earth. It's this vibrant, buzzing, living world, just teeming with an incredible diversity of life. So this isn't just some story about a rock in space. It's the story of the only home we've ever known, and we're going to dive into what makes it so unbelievably special.
And that's the big question, right? Billions and billions of worlds out there, and as far as we can tell, this is the only one with life. Why? What is it about this little blue marble that makes it so unique? So let's put on our detective hats and start following the clues to figure out what really makes our planet a living world.
Okay, so where do we even start our investigation? Well, first, we've got to understand just how fragile this whole life thing really is. We tend to think of Earth as this huge, solid rock, but for everything living on it, the reality is, well, it's a lot more delicate than you'd think.
This right here, this is an incredible way to think about it. Seriously, every mountain, every ocean, every forest, every single one of us. We all exist on this impossibly thin, delicate layer. Everything we know, our entire story, is happening on that super thin layer.
So for our first big clue, all we have to do is look next door. I mean, just look at these numbers. Venus, with its ridiculously thick atmosphere, is a searing 450 degrees Celsius. Mars, it's freezing cold with a super thin atmosphere. But Earth, a nice comfortable 15 degrees on average, with an atmosphere that's just right and liquid water. These aren't just numbers on a chart, people. These are the first big pieces of our puzzle.
And all of that leads us straight to our first major clue, what scientists like to call the Goldilocks conditions. Turns out, for a planet to have life, a whole lot of things need to be, just right.
It all starts with this idea, the habitable zone. Think of it like the perfect spot in a solar system. It's not too close, not too far from its star. It's just the right distance so that water, the key ingredient for life as we know it, can stay liquid.
And this really shows you why that sweet spot matters so much. If we were just a little bit closer to the sun, our oceans would literally boil away. A little farther out, and they'd be frozen solid. Our orbit is what keeps us in that perfect liquid state, day in, day out, for billions of years.
But it's not just about distance, right? The Goldilocks thing doesn't stop there. Turns out, size is a really big deal too. Earth's mass gives us the perfect amount of gravity. It's strong enough to hold on to our precious atmosphere, so it doesn't just drift off into space like on Mars. But it's not so powerful that it would crush life. Once again, it's just right.
Okay, so we're in the right place, we're the right size. What else? Well, space is a pretty dangerous neighborhood. Our next clue shows that Earth actually has its own built-in defenses. A couple of invisible shields, you could say.
And here they are. First, you've got the ozone layer, which is basically the planet's sunscreen, blocking the worst of the sun's UV radiation. Then you have the magnetic field, which is generated deep down in the Earth's core. It's like a giant force field pushing away dangerous particles from the sun and from deep space. Without both of these working together, life on the surface would be a no-go, absolutely impossible.
Okay, so our last big clue isn't just one thing. It's a whole system. It's not just about what makes life possible, it's about what allows it to keep going, to adapt, and to thrive over billions of years. It's basically the ultimate teamwork.
Look at how all this works together. The air, the water, the land, life itself. They're not separate things at all. Nope, they are totally connected. The land gives nutrients to life. Life, like plants, puts oxygen into the air. The water helps control the climate. It's all one beautiful, balanced system that keeps itself going. But wait, how does a system like that last for billions of years? I mean, how does it keep itself going? The answer? Reproduction. It's the amazing ability to pass on the instructions for life from one generation to the next.
And life has two main strategies to get this done. On one side, you've got asexual reproduction, basically making perfect copies. That's awesome for just keeping things stable. But on the other side, you have sexual reproduction, which mixes the instructions from two parents. And this is where things get interesting. It creates all sorts of new variations, and that's the engine that drives adaptation and gives us this incredible, diverse, and resilient world.
So, these two strategies have let life adapt and thrive for billions of years, creating this amazing world we see. But there's a final twist to our story. See, a new force has shown up on the scene, and it's changing the rules of the game, fast.
And this is the challenge of our time, what some people call the triple planetary crisis: climate change, losing biodiversity, and pollution everywhere. But here's the thing. Unlike challenges in the past, these three are all connected. Each one makes the others even worse. And they're all being driven by, well, by us.
When you boil it down, climate change is about a pretty simple fact. By burning fossil fuels, we're unleashing huge amounts of carbon that were safely locked away underground for millions of years. All that carbon acts like an extra blanket wrapped around the planet, trapping more heat and messing with the delicate energy balance that has kept Earth so stable for so long.
And that brings us to this number, 1.5 degrees Celsius. It's become a huge deal, a really critical symbol. It's the goal from the Paris Agreement to try and limit global warming and avoid the worst effects. It's a pretty stark reminder of just how sensitive our planet's finely tuned systems are to even tiny changes.
So, that brings us to the end, and to a question for every single one of us. The story of life on Earth is an epic. It goes back billions of years. For almost all of that time, nature called the shots. But now, we're the ones holding the pen. The very conditions that make our world so unique are now being shaped by our choices. So the question is, what's our chapter going to say?
You know, we're surrounded by, well, stuff. Chairs, water, the air we're breathing right now. But have you ever really stopped to think about what it's all actually made of? Today, we're going to pull back the curtain and take a look at the secret life of everything you see and touch. And it all starts with a simple question, a little mystery from everyday life. Seriously, why does the smell of hot food travel so much farther than cold food? It seems kind of random, but the answer? Well, it unlocks the fundamental rules of the entire physical world. And trust me, by the end of this, you'll know exactly why.
You know, for thousands of years, people have been trying to figure this out. Early Indian and Greek philosophers had their own theories, right? They thought everything was made of basic elements like air, earth, fire, and water. And while their ideas have changed a bit, the quest is still the same. Today, modern science has a single, powerful word for all of it: matter.
So what is matter? It's actually beautifully simple. If something has mass, if it's made of stuff and it takes up space, then guess what? It's matter. It's pretty much the scientific name for, well, everything. I mean, think about it. From the giant stars burning millions of miles away to the tiniest little speck of sand on a beach, it's all matter. The food on your plate, the air filling your lungs, even a single drop of water. It's all part of this one huge family. Okay, but here's where it gets really cool. Matter isn't just one solid continuous block. It's actually made up of tiny individual pieces. And the best part? We can prove it with a super simple experiment you could do in your kitchen right now. Picture this. You fill a glass with water, you mark the level very carefully. Then you stir in a spoonful of salt until it just disappears. Now, you'd totally expect the water level to go up, right? But it doesn't. Not even a little bit. It feels like a magic trick, but it's pure science. The salt didn't just vanish into thin air. The teeny, tiny particles of salt actually squeeze their way into the invisible empty spaces between the particles of water. It's kind of like finding an open seat in a really crowded movie theater. And just like that, this little trick proves that all matter is made of particles with gaps between them. So we know there are gaps, but just how small are these particles? Well, they're small, like mind-bogglingly small. Get this. Just 2 or 3 tiny crystals of a substance called potassium permanganate can spread out and turn 1,000 liters of water bright pink. 1,000 liters. That means each one of those little crystals must be made of millions and millions of even smaller particles. Okay, so matter is made of tiny particles with space between them. Got it.
But there's another crucial piece to this puzzle. These particles, they are never ever sitting still. They are in a constant chaotic dance. And this movement explains so many things we see every single day.
This random mixing has a name. It's called diffusion. So when you light an incense stick, its particles start zipping through the air, mixing with the air particles until they eventually reach your nose. And hey, this brings us right back to our first question. The particles in hot food are buzzing with a ton of energy. They move way faster and spread out much farther, carrying that delicious smell with them. That's why you can smell it from all the way across the room.
But wait a minute, if these particles are always moving around, why doesn't everything just, fly apart? Well, it's because they also attract each other. The analogy of a human chain is perfect for this. Some particles are locked together, like people linking their arms tightly. Others are just barely touching fingertips. This different strength of attraction is the absolute key to understanding the different states of matter. And that leads us perfectly to the 3 states of matter we all learned about in school: solid, liquid, and gas. Now, what's so important to get here is that these aren't fundamentally different things. It's all the same particles, just behaving differently based on how much energy they have and how strongly they're clinging to each other. This table breaks it down nicely. In a solid, those particles are packed in super tight, with a really strong attraction, so they hold a definite shape. In a liquid, that attraction is weaker. The particles can slide past each other, which is why a liquid takes the shape of its container. Think of water flowing. And in a gas, well, the attraction is almost zero. The particles are just flying around freely, filling up whatever space they're in. That's why you can compress a gas so easily. There's just so much empty space in there. So if the state of matter is all about particle energy and attraction, it totally makes sense that we can change it, right? Of course, by adding or removing energy, which we usually do with heat, we can force matter to transform from one state to another. Let's just follow the journey of water. As solid ice, its particles are locked into a neat structure, just kind of vibrating in place. As you add heat, they get enough energy to break free and start melting into liquid water, where they can all slide past one another. Add even more heat, and they get so energized they escape completely, boiling off into steam, a gas where the particles just zoom all over the place. But something really weird happens during these changes. As ice is melting, the temperature gets stuck at 0 degrees Celsius, even though you keep pumping heat into it. So where is all that energy going? The answer is in a pretty cool concept, and the clue is right there in the word itself. Here's the deal. That extra heat is called latent, or hidden heat. It's not making the particles move faster, which is what we measure as temperature. Nope. Instead, all of that energy is being used for one specific job: breaking the bonds that hold the particles together as a solid so it can finally change into a liquid. It's hidden energy with a very important mission. Now, most things go from solid to liquid to gas, but some substances like to take a shortcut. It's called sublimation, and it's when a solid turns directly into a gas. This is exactly what's happening with dry ice. That smoke you see isn't smoke at all. It's solid carbon dioxide turning straight into a gas. It's also why mothballs seem to just vanish over time.
But liquids don't always need to reach their boiling point to become a gas. I mean, think of a puddle drying up on a sunny day. It's definitely not boiling, but the water is still disappearing. This is evaporation, and it's happening all around us, all the time.
And a few things can speed up this vanishing act. If you spread wet clothes out, you increase the surface area, giving more particles a chance to escape. A hotter day gives them more energy to make a break for it. A windy day literally blows the escaped water particles away, making room for more to leave. And less humidity means the air isn't already full of water, so it can take on more. And here's why this is so important to you and me. Evaporation causes cooling. It's a natural air conditioner. For a particle to escape from a liquid, it has to grab energy from whatever's nearby. So when we sweat, the evaporation of that sweat pulls heat energy away from our skin, which is what makes us feel cooler. It's the very same reason an old-fashioned earthen pot can keep water cool even on a blazing hot day. So there you have it. From the smell of your dinner to the reason you feel cool after a swim, it all comes down to one big idea. Our world is made of countless tiny particles in constant, invisible motion. Once you start to see the world that way, you start to see the secret life of everything. So what are you going to see differently now?
All right, let's jump right in. Have you ever really stopped to think about that word pure? What does it actually mean when we're talking about, the stuff that makes up everything around us? Well, in this explainer, we're going to get to the bottom of it. I mean, seriously, think about it. You're walking through the grocery store and you see it slapped on everything, right? Pure milk, pure juice, pure ghee. And our brains are kind of wired to see that label and just think, yep, that's the good stuff. No funny business here.
And boom, right there. That's the big disconnect. See, for you and me, pure just means, nothing weird has been added. But for a scientist, oh, it's a completely different story. To them, that carton of milk is actually this crazy jumble of water, fats, proteins. It's literally a mixture. And scientifically speaking, it's not pure at all.
So let's just get right into it. We're going to tackle this head on and break down this myth of pure.
Okay, so if the milk isn't pure and the juice isn't pure, what in the world is? What does a scientist actually mean when they use that word?
And here it is, the big definition. For a substance to be scientifically pure, it has to be made of just one single type of particle. That's it. Every little piece of it has to be chemically the exact same. No other stuff mixed in. Period. It's way, way more strict than how we use the word every day.
So this super strict definition basically lets scientists sort all matter into two big families. Everything you can touch, see, and feel fits into one of these two buckets.
And here are those two families, side by side. On one side, you've got your pure substances. On the other, you've got mixtures, which is just what it sounds like, two or more pure things just kind of hanging out together. The really important difference is that you can separate a mixture with physical tricks, right? Like filtering something or boiling off water. But a pure substance? Nope. You can't break it down that easily. Now, since most of the stuff we run into day to day is actually a mixture, from the air we breathe to the coffee we drink, let's take a quick tour. So even mixtures have their own little subfamilies. First, you've got homogeneous mixtures, where everything is perfectly and evenly blended. Think about salt dissolved in water. Once it's stirred, you can't see the salt anymore, right? It's uniform. Then you have the heterogeneous ones. These are, well, they're not uniform at all. You can totally see the different parts, like a handful of dirt or oil floating on water. Let's dig a little deeper into those perfectly blended ones. The fancy science name for a homogeneous mixture is simply a solution. And you know these: lemonade, soda water. They're perfect examples. Everything is mixed up so well that every single sip is exactly the same. That's a solution. And get this, solutions aren't just liquids. The very air we're breathing right now, it's a solution. A gas solution, to be exact. It's a perfect, homogeneous mix of mostly nitrogen and oxygen with a few other gases thrown in, all blended together seamlessly at the particle level. So, what really makes something a solution? Well, first, the particles are tiny. I mean, so small you can't see them, and they won't even scatter a beam of light. And second, they're super stable. You can leave a glass of salt water on the counter for a week, and the salt is never going to just sink to the bottom. It stays mixed. Okay, now let's hop over to the other team, the heterogeneous mixtures. A great example here is a suspension. This is when little solid bits are just floating around in a liquid, but they're not actually dissolved. Muddy water is the absolute classic. The dirt is just suspended in there. And yeah, as you probably guessed, the properties here are basically the exact opposite of a solution. You can see the particles. They're big enough that if you shine a light through, you'll see the beam. And the big one, they're unstable. Let that muddy water sit for a while, and all the dirt is going to end up at the bottom. So we've got solutions, which are perfectly mixed, and suspensions, which are clearly not. But what about the weird, mysterious middle ground? Well, that's where colloids live. A colloid is a master of disguise. It looks like it's perfectly mixed, but if you zoomed way, way in, you'd see it's actually not. And yep, our good friend milk is the star example. What makes colloids so interesting is this funky mix of properties. The particles are in this sweet spot, bigger than in a solution, but still too small for us to see. But they are big enough to scatter light. That's a cool phenomenon called the Tyndall effect. And here's the kicker. Just like solutions, they're stable. The particles don't settle down. They just stay spread out. I love this chart. It just lays it all out so clearly. You can see everything side by side. It all comes down to particle size, doesn't it? That one factor determines how it looks, if it scatters light, and whether it's stable or not. It's the perfect cheat sheet for the world of mixtures. Okay, so we've spent a lot of time on mixtures. Let's switch gears. We're going to go back to that other big family, the pure substances. This is where we get into the real fundamental building blocks of, well, of everything.
Now, even in the pure club, there are two types of members. You've got your elements. These are the absolute basics. Think of the periodic table, stuff like oxygen, iron, and gold. You can't break them down into anything simpler. Then you have compounds. This is what you get when you take two or more elements and chemically lock them together in a specific recipe. Water, H2O, is probably the most famous compound out there. And this is such a key difference. A mixture is just a bunch of stuff tossed in a bowl together. A compound is something brand new. The original ingredients are gone, and a new substance with totally different properties is born. The example of salt is just perfect for this. You take sodium, a super reactive metal, and chlorine, a poisonous gas. Yikes! But when they combine chemically, you get table salt, totally harmless. That's the power of a compound. All right, let's put it all together. Now that we have all this new scientific vocabulary, let's look at the world from a chemist's point of view. So that milk in your fridge, the one with pure written on the carton, you now know its secret identity. It's a colloid, a very specific type of heterogeneous mixture where little fat and protein bits are dispersed in water. And the salt right next to it in the shaker, well, that's a compound. That one actually is a pure substance, scientifically speaking, because every single particle is identical sodium chloride. And really, that's the cool part, isn't it? Things we see as simple on the surface are often incredibly complex. So I'll leave you with a little challenge. Next time you're in your kitchen, just look around. What about that salad dressing? The butter? Your coffee? What else is actually a mixture in disguise? Once you start looking, you'll see them everywhere.
Today, we're grabbing our magnifying glasses and putting on our detective hats to solve one of the oldest mysteries there is. What is everything actually made of? Seriously, we're about to crack open a case that goes back thousands of years to find the fundamental building blocks of, well, reality itself. So, let's get into it.
I mean, really stop and think about it for a second. If you could just zoom in and in and in on anything, like your hand or the screen you're looking at or even the air you're breathing, what would you find at the very, very bottom? This single question has kept thinkers and scientists up at night for centuries because, figuring it out is the key to understanding, well, pretty much everything.
The simplest way to get your head around it is to think about a giant brick wall. The whole wall is really just a collection of individual bricks, right? That's the core idea here. All the complex, messy, amazing stuff we see around us must be built from some kind of simple, fundamental brick. But for the longest time, that's all it was, just a really clever idea.
And this idea is ancient. Way back in 500 BC, the Indian philosopher Maharishi Kanad talked about Parmanu, a particle you just couldn't divide any further. Around the same time, over in Greece, Democritus and Leucippus came up with the word atoms, which literally means uncuttable or indivisible. But here's the catch. For over 2,000 years, this was all just talk, pure philosophy. There was zero proof, no real evidence. It was a fantastic guess, but a guess nonetheless, until the 18th century, when our detective story finally gets its first real solid clues.
Okay, so this is where things get really interesting. The mystery moves out of the philosopher's armchair and straight into the science lab. Scientists started noticing that chemicals don't just randomly glom together, they follow very strict rules. And these rules, well, they were the first pieces of hard evidence that something really fundamental was going on underneath it all.
Let's look at the work of a brilliant guy named Antoine Lavoisier. He came up with a super simple but absolutely genius experiment. He took two different chemicals, let's call them X and Y, and put them in a sealed glass flask, but he made sure they didn't mix. He sealed it up tight and weighed the whole thing. Then he just tilted the flask, the chemicals mixed, and a reaction happened. After it was all done, he weighed it again. So what do you think he found? Any change?
Zero. Zilch. Nada. The mass was exactly the same, down to the tiniest measurement. What that meant was, whatever stuff he started with was all still there at the end. It had just been rearranged. This incredibly simple observation pointed to a huge, fundamental rule of the universe.
And that rule is now known as the law of conservation of mass. You can't just make matter appear out of nowhere, and you can't make it vanish. It's always accounted for. And that, my friends, was clue number 1 in our mystery. Now for clue number 2, which came from another scientist named Joseph Proust. He noticed something incredibly precise about how things combine.
Take water, for instance. Doesn't matter if you get it from a glacier, a puddle, or make it in a lab, the ratio of hydrogen to oxygen by mass is always 1:8, every single time. Same thing with ammonia. It's always a 14:3 ratio of nitrogen to hydrogen. It's like every chemical compound has its own strict, unchangeable recipe.
This discovery became our second big piece of evidence, the law of constant proportions. So think about where we are. We've got two unbreakable rules. One, stuff doesn't just disappear. And two, chemical recipes are fixed. But why? These laws were great at describing what was happening, but they gave absolutely no explanation for how it was happening.
So the stage is set. The clues are on the table. We have these two big rules of the game. All we need now is a brilliant detective, someone who can look at all this evidence and finally piece together the solution to this 2,000-year-old mystery.
And that detective, our hero, was an English school teacher named John Dalton. In 1808, he was the one who finally connected all the dots. He took that ancient philosophical idea of atoms and slammed it together with these brand new scientific laws, and he came up with a theory that changed absolutely everything.
Dalton's theory was just so beautifully simple. He said, okay, everything is made of these tiny particles called atoms. You can't create them, you can't destroy them. All the atoms of one element, like gold, are totally identical. But, say, a gold atom is different from a silver atom. And here's the kicker. They combine in simple, whole number ratios, like one of these, two of those, to make all the different compounds we see.
And just look how perfectly his theory explained the two big laws. The law of conservation of mass? Of course. If reactions are just atoms rearranging themselves, then nothing is ever lost. And the law of constant proportions? Well, that makes sense too. A compound like water is always made of the same combination of hydrogen and oxygen atoms, which means its recipe is always the same. It was a perfect fit. The theory explained all the evidence. Case closed.
But Dalton's theory did way more than just solve a mystery. It basically gave scientists a whole new language to describe the entire universe. I mean, if atoms were the real building blocks, we needed a way to write them down and talk about them, right?
Dalton himself got the ball rolling with these little pictorial symbols, like a circle for oxygen, a circle with a dot for hydrogen. It was a cool start, but let's be honest, a little clunky. Pretty soon after, a chemist named Berzelius suggested the much simpler system we all use today. Just use one or two letters from the element's name. H for hydrogen, C for carbon. So much easier.
Okay, so we have symbols for the atoms, but how on earth do you weigh something that's impossibly small? Well, the short answer is, you don't. You weigh it relative to something else. Imagine a fruit seller who doesn't have any standard weights, so he just grabs a big watermelon and says, okay, this watermelon is my standard. I declare it weighs 12 units. Then he can cut it into 12 equal slices. Now he can weigh an apple by seeing it weighs the same as one slice of watermelon. He's just created his own relative scale from scratch.
And that is exactly what scientists did. They picked one particular atom, carbon-12, to be their watermelon. They declared it weighs exactly 12 units, and then they defined one atomic mass unit, or U, as exactly 1/12 of that carbon atom. And boom, suddenly we have a universal scale we can use to weigh every other atom in the universe against.
All right, so let's recap. We have our alphabet, the chemical symbols, and we have a way to know how much they all weigh. Now it's time to learn the grammar. How do we actually combine these letters to write the words and sentences of matter? In other words, the chemical formulas.
The key idea here is something called valency. The easiest way to think about it is that it's the combining power of an element. It's like each atom has a certain number of arms that it can use to link up with other atoms. For example, hydrogen has one arm, oxygen has two.
Here's a fun way to picture this. Imagine an octopus has a valency of 8, so it has 8 arms, and a human has a valency of 2 arms. If that octopus wants to hold hands with people so that every single one of its arms is holding a hand, how many people can it hold on to? Well, 8 arms divided by 2 arms per person, it can hold 4 humans, right? That's the basic logic behind how atoms combine to make chemical formulas. And there's a really simple trick for figuring this out. It's called the crisscross method. Let's try it for magnesium chloride. First, you write the symbols, Mg and Cl. Then you write their valencies right above them. That's 2 for magnesium and 1 for chlorine. Now you just crisscross those numbers down to the other element. So the 2 from Mg goes to the Cl, and the 1 from Cl goes to the Mg. You end up with MgCl2.
It's as simple as that.
And there you have it. It's an incredible detective story, right? We went from this fuzzy philosophical idea all the way to a complete working language. Dalton and the brilliant scientists who came before him, they gave us the alphabet of the atoms and the grammar of valency. They literally taught us how to write the recipe for anything in the universe.
So we've learned how to read the basic language of reality itself, and it really makes you wonder, doesn't it? If atoms are the letters and all these chemical formulas are the words, what kind of incredible stories is the universe writing all around us, just waiting for us to read them? Thanks for joining me on this one.
For centuries, we thought the atom was the universe's ultimate building block. You know, fundamental, unbreakable. But what if that tiny solid ball was hiding an entire universe inside itself? Today, we're going to journey through the incredible discoveries that literally cracked open the atom and revealed a world of mind-bending complexity.
So how did we get from a simple, solid sphere to the wild, complex model we know today? It's a story of scientific rebellion, really. Every new discovery chipped away at the old ideas, paving the way for a complete revolution in how we understand, well, everything.
All right, so our story kicks off near the end of the 19th century. The whole idea of an unbreakable atom was about to face its first big test. And believe it or not, it all started with scientists just messing around with electricity.
The first cracks in the old theory started to show when a guy named E. Goldstein noticed these strange canal rays, basically beams of positive charge. Then, a few years later, J.J. Thomson nails down their counterpart, the negatively charged electron. Now, this was a huge moment. The atom wasn't one solid thing after all. It was made of smaller, charged pieces. All of a sudden, the indivisible was divisible.
And here's the thing. These parts were just wildly different. The electron and the proton had charges that were perfectly equal and opposite, balancing each other out. But when you look at their mass, no contest. The proton was an absolute heavyweight, about 2,000 times more massive than the electron. The electron was so light its mass was barely even a rounding error.
Okay, so scientists now have two key pieces of the atomic puzzle. The next massive challenge was, how do they all fit together? And that leads us to the very first real attempt at a model of the atom.
And that was the million-dollar question that J.J. Thomson wanted to answer. It was pretty clear that protons were buried deep inside the atom and hard to get out, while electrons were easier to knock off. But what did that actually look like?
So Thomson came up with what we now call the plum pudding model. Just picture the atom as a big ball of positive fluff with these little negative electrons scattered throughout, kind of like raisins in a pudding. It was simple, it was neat, it explained why atoms were neutral, but as we're about to see, this pudding was about to get blown to bits. Now, Thomson's model was a fantastic first step, but in science, every great idea has to face the music. And for this model, the music came from one of the most famous experiments in the history of physics, led by the one and only Ernest Rutherford.
The setup for this experiment was honestly just brilliant in its simplicity. Rutherford's team basically built a tiny atomic cannon. They fired a stream of alpha particles, which are essentially tiny, heavy, positively charged bullets, at a sheet of gold foil that was unbelievably thin. And they surrounded the whole thing with a screen that would light up whenever a particle hit it, so they could see exactly where they went.
Okay, so here's what they were expecting. According to that pudding model, where the positive charge is all spread out and diffuse, these heavy alpha particles should have just punched right through the gold foil. I mean, maybe they'd get nudged a tiny bit, but nothing dramatic.
And for the most part, that's what happened. Most of the particles sailed right through. But then, something completely wild happened. A few were deflected at odd angles, but, and this is the crazy part, a tiny, tiny fraction of them, about 1 in 12,000, ricocheted. They bounced almost straight back, as if they'd hit a brick wall. This was not supposed to happen.
You can just imagine the shock in the lab. In fact, Rutherford himself put it best. He said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. Something was seriously wrong with the pudding model.
So this one bizarre result just flipped everything on its head and led to three huge conclusions. First, since most particles went right through, the atom had to be mostly empty space. Second, for a particle to bounce back like that, the atom's positive charge couldn't be spread out. No, it had to be packed into an incredibly tiny, dense core. And third, that core must also contain nearly all the atom's mass. Rutherford called this dense center the nucleus.
So, based on this stunning discovery,
Rutherford proposed a brand new model for the atom. But, as often happens in science, in solving one massive problem, he accidentally created another one. And it was a doozy.
The new picture of the atom was a total game changer. I mean, we went from Thomson's pudding model to Rutherford's vision of a miniature solar system, a dense, positive nucleus at the center with these tiny electrons orbiting around it. It was beautiful, but it had one fatal flaw.
See, according to the laws of physics as they were understood back then, any charged particle moving in a circle, like an electron, should constantly be giving off energy. This would make it lose speed and spiral down into the nucleus in less than a second. If this were true, every atom in the universe should instantly collapse. Matter as we know it couldn't exist. But, look around. It clearly does. So what gives?
The solution to Rutherford's unstable atom didn't come from classical physics. It came from a Danish physicist named Niels Bohr, who brought the weird and wonderful new ideas of quantum mechanics into the picture.
Bohr's idea was both simple and totally radical. He basically said, what if we just break the rules? He suggested that electrons can't just orbit anywhere they want. They're only allowed to exist in specific special orbits, or what we call energy shells. And here's the kicker. While an electron is in one of those special orbits, it just doesn't radiate energy. It's a stable path. This quantum leap explained why atoms don't just collapse on themselves.
And Bohr's model wasn't just a clever fix, it basically wrote the rulebook for chemistry. He and his colleague Bury laid out a set of rules for how electrons fill these shells. They figured out that each shell can only hold a certain number of electrons, and, this is key, that the outermost shell is what determines how an atom behaves. These rules are the very foundation of how elements bond and why the periodic table looks the way it does.
So this new quantum view of the atom, plus one final piece of the puzzle, gives us the modern blueprint we use to describe literally every element in the universe.
First up, the atomic number, which we call Z. This is super simple. It's just the number of protons in the nucleus. And that number is everything. It's the atom's unique identity. An atom with 6 protons is always carbon. An atom with 79 protons is always gold. No exceptions. It's the law.
Next, we have the mass number, or A. Now, pretty much all of an atom's mass is packed into that nucleus. The mass number is the total count of protons plus another particle that was discovered later by James Chadwick, the neutron. Neutrons have no charge, but they're just as heavy as protons. And together, we just call all those particles in the nucleus nucleons.
And that discovery of the neutron leads us to a really cool concept, isotopes. These are basically different versions of the same element. They have the same number of protons, so they're chemically identical, but they have a different number of neutrons. For example, every single carbon atom has 6 protons, but most have 6 neutrons, while a few rare ones have 8, making them a little heavier. It's still carbon, just a slightly different flavor.
So in just a few short decades, our whole picture of the atom was turned completely upside down. We went from a simple, solid ball to this complex quantum world of protons, neutrons, and electrons. This new understanding unlocked the secrets of chemistry, but it also opened a brand new Pandora's box. Because it led to the next big question. What happens when you try to split that nucleus? The answer to that, well, it would kick off the atomic age. But that is a story for another time.
So, have you ever really stopped to think about how a living thing is, well, built? I mean, we talk a lot about organs, right? The heart, the lungs, and we know they're made of individual cells. But there's this really crucial level of organization sitting right in the middle. And that's what we're diving into today, the fundamental fabric of life itself, biological tissues. These are the specialized materials that build literally everything, from the leaves on a giant redwood tree to the very brain you're using to process my voice right now.
Okay, just imagine this for a second. You want to build a skyscraper. What if you just dumped a giant pile of steel, glass, and concrete onto a construction site and hoped for the best? It'd be a disaster, right? You need a plan, you need organization. Well, life faces the exact same problem, just on a microscopic scale, inside every single one of us.
I mean, really think about it. Your body is this bustling metropolis with trillions of citizens, your cells. So how on earth do they all work together? How do they coordinate to do everything from digesting your lunch to forming a single thought? How does nature take what could be total chaos, a mob of cells, and turn it into, well, you? The answer is just a brilliant, brilliant strategy of organization. You know, if you're a single-celled organism like an amoeba, Life's pretty straightforward. That one cell is a total jack of all trades. It has to hunt, eat, breathe, everything all on its own. But when you start talking about complex life, that's just wildly inefficient. So, evolution came up with a game-changing solution, a division of labor. It created these specialized teams of cells where each team gets really, really good at doing just one job.
And that right there, that's the elegant solution that made all of this complex life possible. To solve that huge problem of organizing trillions of cells, evolution's masterstroke wasn't creating tons of new cell types. No, it was creating a whole new level of organization, tissues.
So what exactly is a tissue then? Well, the best way to think of it is as a highly specialized team. It's a group of cells, all pretty similar in structure, that work together to pull off one specific function. And they do it with incredible efficiency. These aren't your general-purpose cells. These are the elite specialists of the body.
And this is where you really see that specialization in action. Instead of every single cell trying to do everything, you get muscle cells that are dedicated to one thing and one thing only, contracting to create movement. You get nerve cells, the communication experts, built just to transmit signals. And blood, it acts like the body's courier service, a fluid tissue that's all about transporting oxygen and nutrients. Each team is a total master of its craft.
But here's the thing. Not all tissues are created equal. The kind of tissues an organism has is completely shaped by how it lives its life. And there's no better way to see this in action than by comparing two totally different teams, plants and animals. Just look at this contrast. It's amazing. A plant's whole life is defined by being stuck in one spot. It has to be rigid so it can grow up towards the sun, right? So it makes total sense that a lot of its support tissue is actually made of strong, dead cells. Why? Because they provide structure without using up precious energy. Now, animals, we're the complete opposite. We are built to move, and that requires flexible, living tissues that burn a ton of energy. It's two completely different strategies for survival, leading to two totally different biological toolkits.
All right, let's kick things off with plants. Their entire tissue structure is just a masterclass in engineering for a stationary life. It's all about how to stand your ground, reach for the light, and pull water from the earth, all without ever taking a single step.
So, plant tissues basically break down into two main types. First up, you've got meristematic tissue. The easiest way to think of this is as the plant's permanent construction zones. These are just pockets of cells that are constantly dividing, and they're what drive all the plant's growth. Then, once those cells grow up and specialize, they become permanent tissue. They've found their lifelong career, whether it's being part of a leaf or a root.
And you can actually prove this with a super simple experiment. Just an onion in a jar of water. You'll see the roots grow from their very, very tips, and if you snip off just the end of one of those roots, poof, it stops getting longer. This shows us, plain as day, that the meristematic tissue, the plant's growth engine, is packed right into those specific little zones.
Now, within those permanent tissues, you've got a few simple types. Parenchyma is kind of like the plant's pantry. It's all about storing food. Then there's collenchyma, which gives the plant flexible strength, letting stems bend in the wind instead of just snapping. And then you have sclerenchyma. This stuff is all about pure, rigid hardness. Seriously, the next time you're struggling to crack open a coconut, just remember you're going head-to-head with sclerenchyma tissue. It's basically a fortress made of dead cells with these ridiculously thick walls. And then you've got the complex tissues. These basically form the plant's vascular system, or you could just call it its internal plumbing. You have the xylem, which acts like a one-way straw pulling water and minerals up from the roots. And then you have the phloem, which does the opposite job. It's a network that distributes all that sugary food made in the leaves down to every other part of the plant. It's this beautiful, super efficient two-way highway. Okay, time to switch gears completely and talk about the animal kingdom. Here, the entire design philosophy is just different. Animal tissues aren't built to stand still. They are an arsenal built for action, for moving, for sensing, for reacting to a constantly changing world. And believe it or not, all of this action is powered by just four main types of tissue. You've got epithelial tissue, which is the body's protective covering. You've got connective tissue, providing all the underlying support. Then muscular tissue, our engines for movement. And finally, nervous tissue, the body's high-speed internet.
Okay, now, to really get a handle on one of the most diverse and, frankly, surprising tissue groups, connective tissue, you have to understand this one key idea. It's not always about the cells themselves, but about the stuff in between the cells. This substance is called the matrix, and it can be anything from a jelly to a fluid to something dense or even rock hard. And that matrix is what defines what the tissue actually does.
And the diversity here is just incredible when you stop and think about it. Would you believe that blood is technically a connective tissue? It is, because its cells are just floating around in a fluid matrix called plasma. Then, at the complete other end of the spectrum, you have bone. That's also a connective tissue, but its cells are trapped in a hard, rigid matrix made of calcium. Everything from the bendy cartilage in your ear to the tough ligaments holding your bones together, it all falls under this one huge category, and it all comes down to that matrix.
All right, next up, the body's engines, muscular tissue, and it comes in 3 flavors. First, you have the muscles you can actually control. That's your striated or skeletal muscle that lets you walk around or wave hello. Then you have the muscles you don't control, the smooth muscle that's working away silently inside your stomach and blood vessels. And finally, there's the superstar of the group, cardiac muscle. You only find it in the heart, and it's this tireless involuntary engine that just keeps beating, rhythmically, for your entire life. Amazing!
And last but not least, we have the body's high-speed communication network, nervous tissue. This stuff is built from special cells called neurons, and they are designed for one purpose and one purpose only: to grab a signal and fire it across the body at incredible speed. This lightning-fast network is what lets us think, feel, and react to the world around us in a fraction of a second. Okay, so let's zoom back out and look at the big picture. None of these tissues work in a vacuum. They are the fundamental building blocks, and they all interweave and cooperate to create this absolute masterpiece of engineering that is a living body. And here it is, the whole hierarchy of life laid out. You start with specialized cells. They group together to form functional tissues, like muscle tissue. Then, those tissues combine to build organs. Your heart, for example, is this brilliant mix of muscle tissue, nervous tissue, and connective tissue, all working together. And then, those organs team up to create organ systems. But the real key takeaway here is that tissues are that essential bridge. They are the crucial organizational step that lets life make the giant leap from a simple cell to a complex organ. It really is an amazing story, isn't it? From a simple idea, a division of labor between cells, the entire stunning complexity of life just emerges. Tissues are the architects behind all of it. And, understanding them has already completely changed medicine, but it also leaves us with this huge final question. As our ability to engineer biology gets better and better, what's the next frontier? I mean, could we one day design and print brand new tissues on demand to repair any injury or cure any disease? The story of these living materials is definitely far from over.
All right, today we are going on a journey into a world that's totally hidden from the naked eye, but it's a world that is the absolute foundation of every single living thing on this planet. We're diving deep inside the cell.
So let's start with maybe the most basic question there is. What are we actually made of? I mean, if you could zoom in, past your skin, past the tissues, what is the fundamental, most basic building block of life itself?
Well, to find the first clue, we have to travel way, way back, all the way to 1665. There was a scientist named Robert Hooke, and he was looking at a super thin slice of cork through a microscope that he had actually built himself. And what he saw, well, it changed science forever.
He saw this structure that looked kind of like a honeycomb, just full of these tiny, tiny compartments. He decided to call these little boxes cells, which comes from the Latin word for a little room. And that name, it totally stuck. It was a huge moment, really, the very first time anyone realized that living things were made up of these distinct, separate units.
And it turns out those little rooms are it. They are the basic building blocks. And not just for cork, but for every single organism you can think of, from the tiniest little bacterium to the biggest blue whale. It all comes down to the cell.
And what's really cool is you don't just have to take my word for it. This is something you can literally see for yourself with just a basic microscope. If you take a thin little peel from an onion, put it on a slide with a drop of stain to make things visible, you'll see them, these perfect rows of distinct rectangular little rooms.
And here's a fascinating little fact. The cells from a giant onion look pretty much identical to the cells from a tiny one. The size of an organism isn't determined by the size of its cells, but by the number of its cells. They really are the universal building block.
Okay, so if a cell is a little room, or a building block, the next obvious question is, what's inside it? Is it just an empty box?
Oh, not even close. Let's zoom in a little further. Inside every one of those cells, there are even smaller structures called organelles, which literally translates to little organs. And honestly, the absolute best way to think about a cell is like a bustling microscopic factory. Every organelle is like a specialized department with a very specific job to do to keep the whole operation running smoothly.
So, our first stop on this factory tour is this huge interconnected network of membranes. It's called the endoplasmic reticulum, or just ER for short.
Think of the ER as the factory's main assembly line and internal transport system all rolled into one. One section, called the rough ER, is covered in these little protein-making machines. The other section, the smooth ER, handles making lipids, things like fats and oils. It's a real production and delivery powerhouse.
So once all those proteins and lipids get built on the assembly line, where do they go next? Well, they head over to the Golgi apparatus.
This is, for all intents and purposes, the factory's shipping department. The Golgi takes the stuff from the ER, does a little quality control, modifies it, and then packages it all up into these little transport bubbles. Then it ships them off to wherever they need to go, either inside the cell or even outside the body.
Now, any good factory is going to produce some waste, right? It needs a cleanup crew, a recycling center. In the cell, that job belongs to the lysosomes.
These are basically little sacs filled with incredibly powerful digestive enzymes. They break down trash, get rid of any foreign invaders, and recycle old, worn-out organelles. They're what keep the cellular factory clean and running efficiently. In fact, and this is pretty wild, if a cell is too badly damaged, they can actually burst and digest the entire cell from the inside out, which is why they've earned the nickname suicide bags.
Of course, none of this work, not the building, not the shipping, not the cleaning, none of it can happen without energy. And that brings us to what is probably the most famous organelle of them all, the mitochondria.
This is the undisputed powerhouse of the cell. Mitochondria are like tiny little power plants that take in nutrients and convert them into something called ATP. You can think of ATP as the energy currency for the cell. It's like the cash that pays for absolutely every activity.
But who's running this whole operation? Who's telling the assembly line what to build and the shipping department where to send it? For that, we have to go to the most important office in the whole factory, the nucleus.
The nucleus is command central. It's the CEO's office. It's sealed off from the rest of the factory, and inside it holds the master blueprint for everything the cell is and everything it does, the DNA. All the instructions for everything are written in that genetic code.
Okay, so not all these factories are designed exactly the same way. In the living world, there are really two fundamental designs. You've got prokaryotic cells, like bacteria, which are pretty simple. They don't have a nucleus. Their DNA just kind of floats around. And then you have eukaryotic cells, like the ones in plants and animals, which are much more complex. They have that true nucleus and all those specialized departments, the organelles we just toured.
And even within that complex eukaryotic design, you see some key differences. Just look at plant cells versus animal cells. Plant cells have a rigid outer wall for support. They've got special organelles called chloroplasts for photosynthesis, and a huge central vacuole for storage. Animal cells, they don't have any of those things.
So we've seen what a cell is, what's inside of it, and the different designs they come in. But this brings up one last, really crucial question. If all of life is made of cells, where do new cells come from?
The answer came back in 1855 from a scientist named Rudolf Virchow. He stated this simple but incredibly powerful truth. All cells arise from pre-existing cells. They don't just pop into existence out of nowhere. They have to be born from other cells through a process of division.
And this division happens in two main ways. For just your everyday growth and repair, cells use a process called mitosis. This is basically cellular cloning. One cell divides one time to create two perfect identical copies. But for reproduction, a special process called meiosis is needed. In that case, a cell divides twice to create 4 unique new cells, each with only half the genetic info, ready to combine and create a whole new organism.
And that leaves us with a final, pretty profound thought. If every single cell in your body came from a pre-existing cell, and those cells came from other cells, and on, stretching all the way back through every generation, where did the very first one come from? That's a question that takes us to the very beginning of life itself.
All right, today we're going on a trip, and this isn't just any trip. We're going to break down the actual physics of how things move. We're talking about the core ideas that describe every single journey you've ever been on, whether you're just walking to the store or flying across the country. So let's get started. We've all been there, right? That weird, confusing feeling. For a second, your brain just can't figure it out. Well, that little illusion is the perfect place to start because it gets right to the heart of a huge idea in physics. You see, that train trick happens because all motion is, well, it's relative. To really understand if something's moving, you have to compare it to something else. Physicists call this a reference point. Think about it like this. Say you're on a bus. To the person sitting right across the aisle from you, you're just sitting there, not moving at all. But to someone standing on the sidewalk watching the bus go by, you're flying past them. So who's right? The crazy thing is, both of you are. It all just depends on your point of view. Okay, so once we've established that we're actually moving, how do we start to describe that journey? Well, the first two things we need to get straight are distance and displacement. Now, they might sound kind of similar, but they tell completely different stories about where we've been. Distance is the easy one. It's literally the total ground you covered. If you walk a mile to the park and a mile back home, you've walked a distance of 2 miles. It's just like the odometer in your car. It just keeps on counting up the miles no matter which direction you're headed. Displacement, though, is a little different. It's all about the most efficient route. You can think of it as the crow flies path. It doesn't care about all the twists and turns you took. All it cares about is the straight line from where you started to where you ended up. It's the ultimate shortcut. And here's where it gets really interesting when you put them side by side. Distance is just a number, what physicists call a scalar. But displacement has a direction, making it a vector. And this leads to a really cool, kind of mind-bending idea. You could run a whole marathon, covering a huge distance. But if you finish at the exact same spot you started, your displacement is 0. Let's make this super clear with a quick example. Imagine a swimmer named Usha. She's in a pool that's 90 meters long. She swims all the way to one end, touches the wall, and swims all the way back. So what's her distance? Well, that's easy, right? It's 90 meters there and 90 meters back. She swam a total distance of 180 meters. You can bet her muscles feel every single one of those meters. But what about her displacement? Well, think about it. Where did she start? At the edge of the pool. And where did she finish? At the exact same spot. So her overall change in position is a big ol' 0. She did a lot of work, but she ended up right back where she began. You can see how that distinction between distance and displacement is super important, and it leads us right into our next pair of ideas. Now that we know how to measure the path, let's talk about how fast we're moving along it. And, just like before, we've got 2 words for this: speed and velocity. Speed is exactly what you think it is. It's what the speedometer in your car shows you. If you drive 60 miles and it takes you an hour, your speed is 60 miles per hour. Nice and simple. Velocity is like speed's smarter, more detailed cousin. It takes that speed and adds the all-important piece of information we saw before: direction. I mean, it's one thing to hear a storm is moving at 20 miles per hour. It's way more useful to hear it's moving at 20 miles per hour due west, right? That's velocity. So we've covered steady journeys, but let's be real. Most trips aren't that simple. We speed up, we slow down, we turn corners, and physics has one single powerful word that covers all of that change: acceleration. Now, this is a really key idea. Most of us hear acceleration and we just think of hitting the gas pedal. But in physics, hitting the brakes is also acceleration. It's just negative acceleration. And get this, because velocity includes direction, even just turning a corner at a constant speed is a form of acceleration because you're changing your direction. Let's look at Rahul on his bike. When he starts pedaling and speeds up, his velocity is increasing. That's positive acceleration. A little while later, he sees a stop sign and hits the brakes. His velocity decreases. That's negative acceleration. See? 2 totally different actions, but they're both described by the same core concept. Okay, so we have our building blocks: displacement, velocity, and acceleration. Now for the really cool part. We can actually tell the entire story of a journey without using any words at all. We can do it with a simple graph. A velocity time graph is an amazing tool. Just by looking at the line, you can see the whole trip. If the line is flat, you're moving at a constant velocity. If the line is sloping up, you're accelerating. If it's sloping down, you're slowing down. It's like a movie of your motion.
Now, here's a little puzzle for you. If you look at the line on the graph and then calculate the total area of the shape underneath that line, what do you think you'd be measuring? What physical thing does that area represent?
You ready for this? It's the total distance you traveled. How amazing is that? The area under the curve on a velocity time graph is your distance. It's just a beautiful, elegant way that math perfectly describes the physical world.
Let's finish up with one last, kind of tricky case that ties all of our ideas together perfectly. Let's talk about moving in a circle. It seems simple, but it's a great test of what we've learned.
Imagine an athlete running around a track. If it's a rectangle, they have to make 4 sharp turns. If it's a hexagon, they make 6 turns. If it's an octagon, 8 turns. You see where this is going, right? A perfect circle is basically a shape with an infinite number of tiny continuous turns. You're always turning. And what do we decide about turning? Any change in direction is a change in velocity, and any change in velocity is acceleration. So, and this is the cool part, an object moving in a perfect circle at a totally constant speed is still accelerating the entire time because its direction is constantly changing.
So here's the bottom line. These aren't just words in a textbook. They're the language that describes how everything around us moves. So the next time you're in a car or a bus, try to think like a physicist. When the car pulls away from a stoplight, you're feeling acceleration. While you're cruising on the highway, your velocity is pretty constant. And when you pull back into your driveway, what's your total displacement for the trip? It's a really cool way to see physics happening all around you, every single day.
All right, let's dive into the invisible rules that run pretty much everything around us. We're talking about force, motion, and of course, the genius who put it all together, Isaac Newton. You know, for centuries, some of the smartest people on Earth were totally stumped by a few seemingly simple questions. So let's see if we can unravel them. So, let's start with the big one. Why does anything move at all? I mean, what makes a ball fly or a car speed down the highway? What's the fundamental reason for motion? It sounds so basic, right? But this question puzzled thinkers for thousands of years.
But here's the real kicker, the question that really threw everyone for a loop. Why do things stop? Think about it. You push something, and it eventually slows down and stops. That one simple observation led to a huge misunderstanding about how the entire universe actually works.
For the longest time, the common wisdom was that things just, well, they wanted to be still. Rest was considered the natural default state for everything. Movement was something you had to force, and as soon as you stopped forcing it, things would just go back to their lazy resting state. Turns out, that's completely backwards. And it took a couple of brilliant minds, Galileo and then Newton, to totally flip that idea on its head.
Okay, so to understand why that old idea was so wrong, we have to start with a concept we all deal with every single day, even if we don't think about it. We have to talk about force.
So what is a force, really? Well, you can't see it, but you can definitely feel it. It's just a push or a pull. It's the effort you use to open a heavy door, it's the kick that sends a soccer ball flying, or even just pulling open a drawer. A force is anything that can get an object to speed up, slow down, change direction, or even get squished like a rubber ball.
Now, here's a crucial point. Not all forces actually cause something to move. Imagine a game of tug-of-war. If both sides are pulling with the exact same strength, that rope isn't going anywhere, right? We call those balanced forces. But the second one team pulls just a little bit harder, the forces become unbalanced and the rope starts moving towards the stronger team. That unbalanced force, that's the secret sauce for creating motion.
Let's make this super practical. You're trying to push a heavy box across the floor. You give it a little push, and nothing. What's going on? Well, the force of friction is pushing back on you with an equal force. They're balanced. But then you really lean into it. You push harder, and finally, your push is stronger than the friction. The forces are now unbalanced, and voila, the box starts to slide. It's all about winning that tug of war.
And this brings us right to the doorstep of Sir Isaac Newton's first great law of motion. This is the law that finally corrected that ancient mistake. You could almost call it the law of laziness, or maybe the law of stubbornness.
Okay, let's just let that sink in for a second. This is revolutionary. What Newton is saying here is that objects don't want to stop. In fact, objects are perfectly happy to just keep doing whatever they're already doing, whether that's sitting still or cruising along at a constant speed. The only thing that can change that is an outside, unbalanced force.
And this tendency, this stubborn resistance to change, has a name: inertia. Everything that has mass has it. An object at rest wants to stay at rest. An object in motion wants to stay in motion. Inertia is just an object's built-in, don't bother me.
And you've totally felt this your entire life. You're standing on a bus, and it suddenly takes off. The bus moves, but your body's inertia tries to keep you in the same spot, so you feel like you're thrown backward. Or when a car slams on the brakes, the car stops, but your body's inertia wants to keep right on going forward. That's why we have seatbelts.
And here's the key takeaway about inertia. It's all about mass. It's a really simple rule. More mass equals more inertia, period. That's why you can easily give an empty shopping cart a shove, but you're probably not going to have much luck trying to push a freight train. The train just has way more mass, and therefore way more inertia.
So if the first law tells us that you need a force to change motion, the second law tells us exactly how much force you need. This is where things get really powerful, because now we can start putting numbers on it.
And here it is, one of the most famous and powerful equations in all of science. Force equals mass times acceleration. F equals ma. This beautiful little formula is the mathematical heart of motion. It tells us that the force required to move something depends on two things: how much stuff is in it, its mass, and how quickly you want to change its speed, its acceleration.
Now, interestingly, Newton himself thought about this a little differently. He talked about an object's quantity of motion, which today we call momentum. It's just the object's mass times its velocity. So you can also think of the second law this way. A force is what you apply to change an object's momentum. A big, heavy bowling ball rolling fast has a ton of momentum, and you're going to need a big force to stop it.
Now, check this out, because it can be a little counterintuitive. It can actually take more force to accelerate a light object really, really fast than it does to accelerate a heavier object more slowly. You just have to do the math. As you can see here, getting that lighter 2-kilogram object to speed up quickly takes 10 newtons of force. But getting the heavier 4-kilogram object to speed up slowly only takes 8 newtons. It's a perfect demonstration of F equals ma.
All right, and that brings us to Newton's third and final law of motion. And this one is just beautiful. It shows us that in our universe, nothing ever acts alone. Forces always come in pairs. It reveals this deep, elegant symmetry in how things interact.
I'm sure you've heard this one before, right? For every action, there is an equal and opposite reaction. What it means is that anytime you push on something, that something is pushing back on you with the exact same amount of force, just in the opposite direction. Always, no exceptions.
So let's use a classic example to really see what this means. Imagine a sailor trying to jump from a small boat onto a dock. To get himself moving forward, he has to push off of something. So he pushes backwards on the boat with his feet. We'll call that push the action force.
And here's the magic. At the exact same instant that the sailor pushes on the boat pushes back on the sailor with an equal and opposite force. That is the reaction. And it's that reaction force from the boat that actually launches him forward and onto the dock. You literally cannot have one without the other. Okay, so a super common question is, wait, if the forces are equal and opposite, why don't they just cancel each other out? And the key is that they are acting on different things. This brings us right back to F equals ma. Think about a gun firing a bullet. The gun pushes on the bullet with the exact same force that the bullet pushes back on the gun. But because the gun has so much more mass, its acceleration, the recoil you feel, is way smaller than the bullet's acceleration. Equal forces, but very different effects. So let's put it all together now. These three laws, they aren't just some abstract rules from a physics textbook. They are literally the operating manual for how motion works in our universe, from planets orbiting the sun all the way down to how you're able to walk across a room.
So just to recap the big ideas one more time, Newton's first law is all about inertia, that objects are stubborn and resist changes in motion. The second law gives us the math, F equals ma, linking force, mass, and acceleration. And the third law shows us that beautiful symmetry of action-reaction. Forces always come in pairs. And with just those three ideas, you can explain pretty much any motion you see.
So I'll leave you with this thought. Now that you know these rules of the game, the world might start to look a little different. The next time you're watching a football game and a player makes a sharp cut, or you just see a bird pushing off a branch to take flight, ask yourself
Can you see the laws of motion at work? Can you spot the inertia, the forces, and the reactions? You'll find that the answer is yes. They're absolutely everywhere.
Let's talk about gravity. It's this incredible invisible force that literally holds our entire world together. It keeps our feet planted on the ground, and it keeps the Earth spinning around the sun. And the story of how we figured it all out, well, it starts with something really, really simple. This is the classic question, right? The one that supposedly popped into Isaac Newton's head. And it really does seem like a paradox. An apple falls straight down, thud, hits the ground, but the moon just hangs up there, night after night. How on earth can both things be happening? Well, Newton's genius was realizing they aren't a contradiction at all. In fact, they're the exact same principle at work. So what is this shared secret? It's the idea that the same force pulling that apple out of the tree is also reaching all the way out into space and grabbing onto the moon. It was a huge leap. Newton connected an everyday event with something absolutely cosmic. And in doing so, he uncovered a fundamental rule of the universe. Okay, get ready for this, because it's a little bit of a mind bender. The moon is falling all the time. But, and this is the key, it's also moving sideways really, really fast. So as gravity pulls it down, its forward motion makes it curve, constantly missing the Earth. It's in this perfect, delicate balance, creating an orbit. If gravity suddenly switched off, the moon would just zip away in a straight line, off into the cosmos. You can actually feel this for yourself. Imagine you're whirling a stone on a string. You feel that constant pull, right? The string is pulling the stone inward, forcing it to go in a circle. That's what we call a centripetal or center-seeking force. The second you let go of that string, boom, the stone shoots off in a straight line. Well, for the moon, Earth's gravity is that string. It's the invisible cosmic tether holding it in place. And this is where things get truly epic. Newton didn't just stop with the Earth and the moon. He realized this invisible connection, this force of attraction, wasn't special. It exists between every single object in the universe. You, me, this planet, distant stars, everything is pulling on everything else. And here it is, the official law. Now, I know that sounds pretty academic, but it boils down to two super simple ideas. One, the more stuff or mass something has, the stronger its pull. And two, the farther apart things are, the weaker the pull gets. This is the secret code. This one beautiful little equation lets us calculate that gravitational force between any two objects anywhere. It's the formula that describes the dance of the cosmos. So let's decode this thing really quick. F is the force we're solving for. M and M are just the masses of our two objects. Bigger masses mean a bigger F. Simple enough. Now D is the distance. But look, it's squared. That's a huge deal. It means that if you double the distance between two things, the force doesn't get cut in half. It drops to a quarter of what it was. And finally, there's G, the universal gravitational constant. It's just a fixed number, a sort of cosmic conversion factor, first measured by Henry Cavendish, that makes the math work out perfectly. Okay, but wait a minute, this is a great question. If the apple is pulling on the Earth, why doesn't the Earth lurch up to meet it? And it's true, the force is identical. But Newton also gave us another law. Force equals mass times acceleration. Since the Earth's mass is, astronomically huge compared to the apple, the acceleration it experiences is so ridiculously tiny that we could never, ever notice it. All right, so we've been talking big and universal. Let's bring this right back down to Earth and look at what this means for the simple act of something falling. In physics, when we talk about free fall, we're talking about an idealized situation where gravity is the only thing happening. We're ignoring stuff like air resistance for a moment. And in this state, things don't just fall. They pick up speed. They accelerate. And here on Earth, that acceleration is a very specific number, 9.8 meters per second every second. We call it g. But here is the absolutely wild part. That number is the same for everything. A piano, a pebble, a person. It doesn't matter how heavy something is. That's right. If you could get rid of all the air in a room and drop a bowling ball and a feather at the same time, they would hit the floor at the exact same moment. It feels wrong, but it's true. The only reason a feather floats down in the real world is because of air resistance pushing up on it. And that leads us to a really, really important point that trips people up all the time. We tend to use the words mass and weight as if they're the same thing. In physics, though, they are totally different. So here's the deal.
Your mass is the amount of actual stuff you're made of. It's measured in kilograms, and it never, ever changes, no matter where you go in the universe. Your weight, on the other hand, is the force of gravity pulling on that mass. Since gravity changes depending on where you are, your weight changes too. This is the perfect example. If you went to the moon, your mass, the amount of you, would be exactly the same. But the moon is much smaller than Earth, so its gravitational pull, its g, is way weaker. The result? You'd weigh only about 1/6 of what you do here. Same you, different pull. Okay, so we've nailed the force that pulls everything down. But what about the things that seem to defy gravity? I mean, how can a ship made of thousands of tons of steel float on water? To figure that out, we need to look at another force, one that pushes up.
And that upward push is called buoyancy. You've definitely felt this. It's the force that shoots a beach ball back to the surface when you try to hold it underwater. It's why you feel so much lighter when you're wading into a swimming pool. The water is literally pushing up on you.
The person who cracked this code was the ancient Greek scientist Archimedes. Legend says he figured it out while getting into his bathtub and watching the water level rise. He realized that the upward buoyant force on an object is exactly equal to the weight of the water it shoves out of the way. Eureka! So every time you put something in water, you have this constant battle of forces. You've got gravity pulling the object's weight down, and you've got the water pushing up with this buoyant force. And whoever wins this tug of war determines whether the object sinks or floats. And the winner is decided by one simple thing, density, which is just how much stuff is packed into a certain amount of space. A piece of cork floats because it's way less dense than water. The upward buoyant force easily wins. An iron nail, on the other hand, is super dense. Its weight overwhelms the buoyant force, and down it goes.
Which finally brings us back to that giant steel ship. Yes, a solid block of steel is super dense and sinks like a rock. But a ship isn't a solid block. Its hull is shaped to displace a huge amount of water, and it's filled with enormous amounts of air. So its average density, all that steel plus all that air spread out over its huge volume, is actually less than the density of water. And that's the secret. That's why it floats. So there you have it. From a simple falling apple to a massive floating ship, we've seen the invisible pushes and pulls that define so much of our world. It really makes you wonder, doesn't it? Beyond gravity pulling down and buoyancy pushing up, what other hidden forces are at play all around us, shaping our reality every single second? That's a thought for next time. Thanks for joining me.
You know, we all talk about hard work, right? But what if I told you that in the world of physics, spending hours and hours studying for a big exam might actually count as zero work? It sounds crazy, I know. So today we're going to untangle the real physics of effort by digging into three huge connected ideas: work, energy, and power.
And this really just lays out the paradox perfectly. Over on the left, you've got things that feel absolutely exhausting. Studying your brain out, holding a heavy box until your arms shake, and on the right, things that seem, well, pretty easy. But here's the kicker. In physics, the stuff on the right is a clear example of work, while the stuff on the left, maybe not so much.
And yeah, that brings us to the big question, doesn't it? It feels totally backward. How can all that mental effort, all that physical strain, just not count? Well, it turns out that science has a very, very specific definition for work, and we are about to break it down.
So here's how we're going to tackle this. First, we'll dig into that work paradox. Then, we'll get the real scientific definition. From there, we'll talk about energy, which is basically the fuel for work, and its two main forms. Then we'll look at power, because that's all about speed. And we'll wrap it up with the one big law that rules everything.
All right, let's dive right into this paradox. It's that super frustrating feeling when you are completely wiped out, but according to a physicist, you might not have done any work at all.
So think about Kamali, cramming for her exams. She is using a ton of mental energy. Or, picture yourself pushing against a giant boulder with every ounce of your strength. Your muscles are on fire, but that rock, it doesn't budge an inch. Even just standing perfectly still with a heavy bag on your head is exhausting, right? Well, in all of these cases, scientifically speaking, zero work is being done on the object.
This quote just nails it. Our everyday feeling of hard work and the precise scientific definition are two totally different things. So, what exactly is that scientific definition?
Okay, this is where it all starts to make sense. See, the scientific definition of work has nothing to do with how tired you feel. It's actually much, much simpler, and it all boils down to two very clear, non-negotiable rules.
And here they are. It's a two-part test. First, a force has to be applied to an object. And second, that object has to move. It needs to be displaced. If you're missing either one of those things, if there's no force or if nothing moves, then absolutely no work is done. It's really that simple.
We can even put a number on it with a pretty simple formula. Work equals force times the displacement, or the distance it moved. And we measure this in a unit called the joule. Just to give you an idea, 1 joule is about the amount of work it takes to lift a small apple 1 meter straight up.
So let's run a few things through our two-part test. An engine pulling a train? Well, there's a force, and the train is definitely moving. So yes, work is done. Pushing a tiny pebble? Same deal. Yes. Now, the donkey is a tricky one. It's applying an upward force on the load to fight gravity, right? But it's moving horizontally. Because the load isn't moving up, no work is done by that specific upward force. And standing still with a heavy load, you're applying a force for sure, but there's zero displacement, so no work. See how that works?
Okay, so if doing work means you need a force and some movement, then what gives something the ability to apply that force in the first place? And that question leads us directly to our next big idea, energy.
Energy, at its core, is just the capacity to do work. If an object has energy, it has the ability to push or pull on another object and make it move. You can think of it like this. When one thing does work on another, it's basically just a transfer of energy. And that's exactly why they share the same unit, the joule. They're really two sides of the same coin.
Now, energy isn't just one single thing. When we're talking about mechanics, it usually comes in two main flavors. So we're going to break down the difference between the energy something has because it's moving and the energy that's kind of stored up, just waiting to be used. So on one hand, you have kinetic energy. That's the energy of motion. And on the other, you have potential energy, which is all about stored energy, based on where an object is or what shape it's in. To put it simply, kinetic is the energy of doing, and potential is the energy of waiting. Think about a cricket ball moving at high speed right before it hits the wicket, or a speeding car on the highway. I mean, anything that's moving has kinetic energy. The faster it goes, or the heavier it is, the more kinetic energy it has, and the more work it can do when it runs into something else.
So what about potential energy? Well, the classic example, and it's a great one, is a bow and arrow. When you pull back that string, you are doing work on the bow. That energy doesn't just vanish. It gets stored in the tension of that bent bow and stretched string. That stored up energy is potential energy. And here's where the magic happens. The second you let go of that string, all that stored potential energy is instantly converted into kinetic energy, which sends the arrow flying forward. The potential to do work becomes the actual motion. It's an amazing transformation. So we've covered what work is, and we've talked about the energy you need to do it. But there is one last piece to this puzzle. It's not always about if you do the work. Sometimes it's about how fast you do it. And that is where power comes into the picture.
Let's look at this example. We have two girls, girl A and girl B, and they both climbed the exact same rope. Since they weigh the same and they climbed the same height, they did the exact same amount of work. But girl A did it in just 20 seconds, while girl B took 50 seconds. Because girl A did the same work in less time, we say she was more powerful.
So that's all power is. It's just the rate of doing work. The formula is simply work divided by time, and we measure it in watts. A more powerful car engine, for example, doesn't necessarily do more work, it just does that same work a whole lot faster. Now we've seen how energy can change form, right? From potential to kinetic in that bow and arrow, but what are the rules that govern all these changes? Well, that brings us to one of the most fundamental, most important laws in all of physics.
It's called the law of conservation of energy, and it's huge. Basically, it says you can't just create energy out of thin air, and you can't make it disappear either. You can only change it from one type to another. The total amount of energy in a closed system is always constant.
Okay, let's do a quick recap. The big takeaways are: 1. Scientific work needs two things, a force and movement. 2. Energy is what lets you do work, and it shows up as either kinetic, the energy of motion, or potential, which is stored energy. 3. Power tells you how fast you're doing that work. And finally, all of this is governed by that one unbreakable rule: energy is never lost, it just changes its clothes. Which brings us right back to where we started. If you're pushing on a solid wall that isn't moving, you're doing zero scientific work on it. But you are definitely using your own energy and getting tired. So if that energy isn't going into the wall,
and we know it can't be destroyed, where does it go? Something to chew on. Thanks for joining me.
All right, today we are going on a journey, but not to a place you can find on a map. We're diving into the invisible world of sound that's all around us all the time. We're going to follow a single sound wave from the moment it's born all the way to our ears, and then we'll even explore the sounds we can't hear at all. Let's get started. So, let me ask you this. What if I told you that every single sound you've ever heard, the roar of a jet, the whisper of a friend, my voice right now, it all started with a wiggle? It sounds kind of weird, right? But it's absolutely true. Every sound begins with the exact same thing, a simple back and forth motion. A wiggle, or as scientists call it, a vibration. Every journey has to have a starting point, and for a sound wave, that starting point is the moment of creation. There is one non-negotiable, absolutely essential ingredient for any sound to even exist, and that is a vibration. So, what is a vibration, really? Well, put simply, it's just a super rapid to and fro motion. Think about a guitar string after you pluck it, or the skin of a drum when you hit it. Even the vocal cords in my throat right now, they're all wiggling back and forth. That initial, fast movement is the very first domino to fall in the chain reaction that we call sound. Now, this is where we can make the invisible visible. If you strike a tuning fork, you hear a clear note, right? But you can't see the metal moving. But watch what happens when that invisible movement interacts with the world. You touch it to a little suspended ball, and bam, it kicks it away. You dip it in water, and it sends splashes flying. This shows us that a vibration isn't just some abstract idea. It's a real physical movement that carries real energy. Okay, so we've got our vibration. That's step one. But how does that initial wiggle from, say, a guitar string, travel all the way across the room to our ears? Well, it needs a ride, so let's move to the next stage of its journey. You know how in space movies you always hear big explosions? Well, fun fact, you wouldn't. Sound can't travel through the vacuum of space like light can. It absolutely needs something to travel through, and that something is called a medium. For us, most of the time, that medium is just the air around us. But sound travels just fine, sometimes even better through water or solid objects. Now, here's a super important point that messes a lot of people up. When I'm talking, the actual air particles from my mouth don't fly across the room and into your ear. Think of it like a slinky. If you push one end, you see that wave of energy travel all the way down, right? But each individual metal ring just kind of moves back and forth in its spot. The air particles in a sound wave do the exact same thing. The energy travels, but the particles themselves just bump into their neighbors and pass it along. So as that tuning fork or guitar string is vibrating back and forth, it's creating a chain reaction. When it pushes forward, it squishes the air particles together, creating a little pocket of high pressure. We call that a compression. Then as it moves backward, it leaves a space with fewer particles, a low pressure zone, and that's called a rarefaction. So a sound wave is really just this repeating pattern of high and low pressure, traveling through the air. And of course, scientists have a name for this. It's called a longitudinal wave. All that fancy term means is that the particles are wiggling back and forth in the same direction that the wave of energy is traveling. It's basically a push-pull wave, and that's how sound gets from point A to point B. But obviously, not all sounds are the same, are they? A deep, booming drum sounds totally different from a high-pitched whistle. So what gives each sound its unique identity? Well, it really comes down to two main characteristics. First up, you've got pitch, and pitch is all about frequency, which is just a way of saying how fast the source is vibrating. A slow vibration, like a thick bass guitar string, creates fewer waves per second. Our brain hears that and says, okay, that's a low pitch, but a really fast vibration, like from a tiny flute, creates tons of waves per second, and our brain interprets that as a high pitch. Simple as that. The second part of a sound's ID card is its loudness. This is determined by something called amplitude. And amplitude is really just about the force of that first vibration. So if you tap a drum really gently, you create a small disturbance, a small wave, and you hear a soft sound. But if you whack that same drum with all your might, you create a huge disturbance, a wave with a really big amplitude, and you hear a loud sound. More force means more amplitude, which means more volume. Okay, so our sound wave has been born from a vibration, it's traveled through the air,
But what happens when it runs into something, like a giant wall or the side of a mountain? It doesn't just disappear. Nope, it bounces. The principle behind this is actually really easy to picture. A sound wave hitting a hard surface acts a lot like a rubber ball hitting a wall. It just bounces right off. And this reflection is responsible for something we've all heard before, an echo.
So why don't you hear an echo in your living room? It all comes down to this one number, 1/10 of a second. That's about how long the sensation of a sound sticks around in our brain. So for us to hear a reflection as a separate, distinct echo, that bounce sound has to get back to our ears after that 0.1 second window has already passed. Let's do a little back-of-the-napkin math. Sound travels at around 344 meters per second on a normal day. So in that 1/10 of a second that our brain needs, that sound wave can travel a total of 34.4 meters. That's the minimum round-trip distance it has to cover, to the wall and back again. And since that's the round trip, the distance to the wall and back, the actual minimum distance to the obstacle itself is just half of that, 17.2 meters. If you're any closer, the reflection gets back to your ears too fast, and your brain just mushes it together with the original sound. No echo. Now, when you're in a big, empty space like a gym or a cathedral, and those reflections keep bouncing around over and over again, you get what's called reverberation. It's that big, lingering sound. And this is exactly why concert halls are designed so carefully, with things like heavy curtains and special bumpy tiles on the walls. They're there to absorb some of that sound and control the reflections, so everything sounds clear instead of like a jumbled mess. All right, for the last leg of our journey, we're going somewhere really cool. We're going to explore the sounds we can't hear. Because it turns out the range of sounds we humans can perceive is actually pretty small. There is a whole secret world of sound happening all around us, just beyond our perception. See, our ears are tuned to a specific band of frequencies. We can generally hear from a very low rumble of 20 hertz, or 20 vibrations per second, all the way up to a high-pitched squeak of 20,000 hertz. Anything with a frequency below our range is called infrasound, and anything above it is called ultrasound. And this is where nature just gets awesome. Our world is full of animals using these zones we can't access. Rhinos and elephants use super low-frequency infrasound to talk to each other over huge distances. On the other end of the spectrum, bats and dolphins use high-frequency ultrasound like a biological sonar system to navigate and hunt in the dark. It's incredible. Some moths have even evolved the ability to hear a bat's ultrasound so they have a chance to get away. And it's not just animals. We humans have figured out how to harness the power of ultrasound for some amazing technology. We use its high-frequency vibrations to clean tiny, delicate parts. We use it to find invisible cracks deep inside metal beams. And, of course, we use it in medicine, to get the first picture of a baby in the womb, or even to focus it so powerfully that it can break up kidney stones without ever making a single cut. So, there you have it. From a tiny wiggle in the air to a complex wave that paints a picture of the world. That's the journey of sound. And it's just a powerful reminder that we are constantly swimming in a sea of invisible forces. Right now, in the space you're in, there are light waves, radio waves, Wi-Fi signals. What other waves are you interacting with completely unaware, just waiting to be understood? Welcome to The Explainer. Today, we are diving into one of the biggest challenges we face. I mean, how do we feed everyone? We've got more and more people on a planet that isn't getting any bigger. So the pressure is really on to get creative. And you know what? Science is stepping up with some pretty amazing solutions. All right, so first things first, let's just wrap our heads around the sheer scale of this thing. Because, it's not as simple as just planting more fields. We're working with some pretty major limitations here. Okay, let's just look at India for a second. We're talking over 1 billion people. 1 billion. And the land there, it's already farmed pretty much everywhere it can be. There's just no more space to expand. And look, this isn't just about India, right? This is happening all over the world. The bottom line is, we have to get way more efficient with the land we've already got. And think about what it takes to feed all those people. We're talking more than 250 million tons of grain every single year. That number is just, wow. It really hammers home why we can't afford to be wasteful. Efficiency isn't just a buzzword, it's absolutely essential. All right, so how are we going to tackle all this? Here's the plan. We'll start with a big picture challenge, then get into the nitty-gritty of building better crops. After that, we'll look at everything from soil to storage, then rethink animal farming, and finally, bring it all together to see what a sustainable solution looks like.
Okay, section 1. Before we get into the solutions, we really have to understand the fundamental problem. It's this constant balancing act, right? We need to produce more food, but we also have to protect the planet for the long haul. How do we do both at the same time?
I mean, look, we've had massive wins in the past. You've probably heard of the Green Revolution, right? It totally transformed crop yields. And the White Revolution did the same for milk production. These were incredible successes, no doubt about it. But there was a catch. All that intensive farming put a huge strain on our natural resources. Our water, our soil, everything. And that brings us to the real heart of the matter. This isn't just a numbers game about producing more tons of food. It's about how we do it. The real challenge is finding ways to be productive sustainably. We have to innovate without, wrecking the very foundation we need to survive.
So, that's the big why. Now for the how. How in the world do we get more from the same amount of land and do it sustainably? Well, a huge piece of the puzzle starts before a seed ever touches the soil. It's all about building a better crop from the ground up, literally, from the genetic level. When you think about improving crops, it really comes down to 3 key areas. First, you've got to improve the crop variety itself. Then, you have to get better at managing how it's produced. And finally, you've got to protect what you've grown. So let's start with that first one, making better plants to begin with. This is where the real design work happens.
Seriously, you can think of these scientists as like crop architects. They're designing the perfect plant for the job. They use techniques like hybridization, which is basically just a super focused version of selective breeding, to cherry pick the best traits. Maybe they want a higher yield or wheat that's better for baking. Or, and this is a big one, they can build in resistance to pests or even drought. And get this, even something like making the growing season shorter can be a total game changer. Why? Because it means farmers might be able to get 2 or 3 harvests in a year instead of just 1.
Okay, so designing a super crop is step 1, but that's just the start of the journey, right? Now we've got to talk about the other 2 pillars, nurturing that crop while it grows and then protecting it once it's harvested. This is the whole journey, from the soil all the way to storage. It's funny, plants are a lot like people. They need a balanced diet to thrive. Sure, they get some basics from the air and water, but all the really important vitamins and minerals, that all has to come from the soil. And if the soil is running on empty, well, we've got to step in and give it a boost.
And that brings us to a really big choice in farming. You've got 2 main options here. On one side, there's manure. It's organic, it's amazing for the soil's long-term health, and it's a great way to recycle waste. On the other side, you've got commercial fertilizers. They are super effective at delivering a quick shot of specific nutrients, nitrogen, phosphorus, for a big yield. But there's a downside. Use too much and you can end up polluting waterways and really harming the tiny organisms that keep the soil alive. It's the classic dilemma, quick results now or long-term health for the future.
And it's not just about what you put in the soil, it's about how you plant in the soil. This is so clever. Instead of just one giant field of the same thing, a monoculture, farmers use these really smart patterns. You've got mixed cropping, which is basically agricultural insurance. If one crop gets hit by a pest, the other might be fine. Then there's intercropping, where you plant in specific rows. This can literally stop pests in their tracks, preventing them from wiping out the whole field. And my favorite, crop rotation. By changing what you plant in a field each year, you can naturally put nutrient back into the soil. It's just brilliant.
But the job isn't over when the crops come out of the ground. Not even close. You can do everything right and then lose a huge chunk of your harvest in storage. We're talking losses from insects, mold, moisture, you name it. It ruins the quality, reduces the weight, and can make the whole lot completely unsellable. It's a massive problem, which is why proper storage is so important. All right, we've talked a lot about crops, but that's only half the plate, isn't it? Our food system is also about animals. So let's shift gears and look at animal husbandry. That's just the scientific term for managing livestock. And trust me, there's just as much cool innovation happening here.
Take cattle, for instance. A lot of the improvement comes down to really smart breeding. You can take, say, an exotic breed, like a Jersey cow. They're famous for producing milk for a really long time, but maybe they're not so tough. So you crossbreed it with a local animal, like a red Cindy, which is super resistant to local diseases. What do you get? Hopefully a cow that gives lots of milk and stays healthy. It's the best of both worlds.
And when it comes to poultry, it's all about specialization. It's super focused. You've got chickens called layers, and their one job is to, well, lay eggs. Then you have broilers, which are raised for meat. They get a special high-protein diet to help them grow quickly and healthily. Two different goals, two completely different playbooks for raising them.
Okay, now this next one is one of my favorite examples of scientific thinking in action. It's called composite fish culture, and it's all about creating a super efficient, balanced little ecosystem. The idea is simple but brilliant. Instead of just farming one kind of fish, you raise a whole bunch of different species together in the very same pond.
And here is where the magic happens. The trick is to pick fish that don't compete with each other for food because they all eat in different parts of the pond. So you have your catlas, they feed up at the surface. The rohus hang out and eat in the middle. Then you've got mriggles, which are bottom feeders. They even throw in grass carps, whose job is just to eat the weeds. It's genius. No food goes to waste, every part of the pond is utilized, and the result is you can produce way, way more fish from that single pond. And this scientific approach isn't just for big operations. Even something like beekeeping, or apiculture, if you want to get fancy, is being optimized. Farmers are choosing specific breeds, like the Italian bee. Why? Because it's a honey-collecting machine, and as a bonus, it's less likely to sting. For a farmer, that's a perfect way to bring in some extra, reliable income from honey and wax. So, let's just take a breath for a second. We've just gone on a whirlwind tour of this amazing toolkit of ideas, from designing a perfect plant right down to its DNA, all the way to building a tiny, perfect ecosystem in a fish pond.
And if you look closely, there's one single idea that ties all of this together. It's the word sustainability. Because the real goal here isn't just to get one amazing harvest, it's to be able to do it again and again, year after year. It's about getting sustained yields without bankrupting the natural resources, the soil, the water that we all need to survive.
And that really leaves us with the ultimate question, doesn't it? The science is, well, it's incredible. It shows us a clear way forward. We have the tools. But using them on a global scale, that's the hard part. It's going to take an incredibly delicate balancing act, pushing for progress while protecting our planet for the future. And figuring out that balance, that's the great challenge for the future of food.
Have you ever just watched an apple slice turn brown? Or seen rust creep across an old bike? You know, it's easy to think of these as just things getting old, but they're not. They're actually tiny, invisible transformations happening right in front of us. And in this explainer, we're going to crack the code behind these everyday chemical mysteries.
Okay, so think about this for a second. What on earth could a rusty old nail possibly have in common with a bright, dazzling flame? Or, say, milk that's gone sour with a cake that's baking in the oven? I mean, they seem like total opposites, right? One is slow and quiet, the other is fast and, well, dramatic. But believe it or not, they all share the same fundamental secret.
And there it is. It's not magic, not at all. It's a chemical reaction. This is the amazing process where the very identity of a substance changes, where old chemical bonds break apart and new ones form to create something completely new. It's pretty much the engine of change for our entire universe.
But that's the big question, isn't it? I mean, we can't exactly zoom in and see the atoms rearranging themselves. So what are the clues? How can we become chemical detectives and spot the evidence? Well, it turns out there are some key signs you can look for. Here are the four big ones, the smoking guns, if you will. You might see a change in state, a liquid bubbling up and turning into a gas, or a sudden dramatic change in color. Maybe there's an evolution of a gas, like something fizzing. Or you might notice a change in temperature. The container gets hot or maybe even ice cold. If you spot any of these, chances are a chemical reaction is underway.
So, observing is one thing, but science needs a precise language to describe and even predict these changes. We can't just go around saying, the stuff changed. We need a system, a kind of chemical grammar that everyone, everywhere can understand and use.
And what's so cool about this is how you can see that language evolving. We start with a long, kind of clunky sentence. I mean, it gets the job done, but it's not very efficient. Then we move to a word equation, which is better, it's clearer, more direct, but that final step, the chemical equation using symbols, that's where the real power is. It's short, it's universal, and it's packed with information.
But before we can really start writing in this new language, we have to learn its number one, most important rule, the law of conservation of mass. This is, and I'm not exaggerating, the bedrock of modern chemistry. It just means you can't lose atoms or create new ones out of thin air. Every single atom you start with has to be accounted for at the end. They're just shuffled around into new partnerships.
So with that rule in mind, let's look back at our equation for burning magnesium. Mg plus O2 gives us MgO. Let's do a quick count. We start with 1 magnesium and 2 oxygen atoms on the left side, but we end up with only 1 magnesium and 1 oxygen on the right. Uh-oh, we've lost an oxygen atom somewhere. This is what's called a skeletal equation, and right now, it's breaking the law.
And it's not just that one. Let's take another example here, iron reacting with steam. This little table lays out the problem perfectly. The numbers just don't add up. We start with 1 iron atom, we end up with 3. We start with 1 oxygen, we end up with 4. This equation is totally unbalanced, and we've got to fix it.
So how do we fix this? We balance it. And honestly, this is where it gets kind of fun. It's like solving a logic puzzle. We can't change the actual substances, right? But we can change how many of each molecule we have. By tweaking those numbers out front, they're called coefficients, we can work through it step by step. First, let's tackle oxygen, then hydrogen, and finally iron, until everything is perfectly accounted for.
And voila! With the right coefficients in place, just look at that final count. 3 iron atoms on both sides, 8 hydrogen atoms on both sides, 4 oxygen atoms on both sides. Perfect! The books are balanced, the law of conservation of mass is happy, and now we have a correct, complete chemical equation.
Okay, so we've basically learned the grammar of chemistry. We know how to write a proper sentence, so now we get to read the stories. It turns out that most chemical reactions fall into one of just a few fundamental plot lines, or genres. And knowing these genres is absolutely crucial for chemists, whether they're designing a new medicine or creating a stronger building material. Let's take a look at the main types.
First up, we've got 2 types that are pretty much perfect opposites. A combination reaction is like a couple getting together. 2 or more things combine to form one single, more complex thing. On the flip side, you have a decomposition reaction. That's the breakup, where one complex thing breaks down into 2 or more simpler parts. Simple, right?
Next up is the displacement reaction. The best way to think about this one is like someone cutting in on a dance. You've got a more reactive element, in this case iron, that comes along and basically boots a less reactive one, copper, out of its compound. The iron takes the copper's place, and poor old copper is left all on its own.
And finally, we have the double displacement reaction. Now, if the last one was just someone cutting in, this is more like 2 couples on the dance floor deciding to completely swap partners. The sodium and the barium trade places, and in this particular reaction, it creates an insoluble solid that falls out of the solution, which we call a precipitate.
Okay, so we've learned the language, and we've learned the main story types. Let's go all the way back to the very beginning, back to that rusty nail and that dazzling flame, and let's solve this mystery once and for all. It all comes down to one specific and incredibly common process.
The secret process that connects them all is called oxidation. And put simply, it's what happens when a substance gains oxygen. That dazzling flame from the magnesium ribbon? That's just super fast oxidation, releasing a huge burst of energy. But that exact same process can also happen much, much more slowly.
Which brings us right back to our rusty nail. Corrosion, like the rusting of iron, is really just a much slower form of oxidation. The iron is gradually combining with oxygen from the air and water, and that forms that reddish-brown coat of iron oxide that we all know as rust.
And get this, it even happens to our food. Have you ever eaten chips or crackers that have gone stale? That weird off taste? That's called rancidity, and it's caused by the fats and oils in the food slowly oxidizing when they're exposed to air. It's actually why chip bags are often filled with nitrogen gas, to push all the oxygen out and keep them fresh.
So you see, from the energy being released inside your own body as you breathe, to the slow decay of leaves in a forest, chemical reactions really are the hidden architects of our world. So the question is, now that you know the clues to look for, what invisible reactions can you spot shaping your world right now?
You ever stop and think about the secret chemistry that's happening literally everywhere? I'm talking about in your food, inside your own body, even in something as simple as a bee sting. Well, today we're going to unlock the science of acids and bases. They're these powerful chemical opposites, and they pretty much shape our entire world.
Okay, let's start with something we've all felt. You ate a little too much, and now you've got that awful burning indigestion. You might reach for some baking soda, right? But you know, just instinctively, that drinking lemon juice would be a terrible idea. So why is that? It all comes down to the amazing power of acids and bases to cancel each other out. and we're about to see exactly how they do it. So, first things first, how in the world do we tell these two chemical opposites apart? Let's dive in and get to know their core personalities. At the most basic level, it comes down to taste in a simple paper test. Think about acids, like in lemons or vinegar. They're sour. And bases, well, they're bitter, kind of like soap. But, and this is a big but, tasting unknown chemicals is an absolutely terrible idea, so don't do it. Instead, scientists use a much safer method, litmus paper. It's super simple. Acids turn blue litmus paper red, and bases do the exact opposite, turning red litmus blue. It's a really clear visual way to tell who's who. You know, we have all these amazing chemical detectives or indicators to help us out. Litmus actually comes from a plant. But here's one you've probably seen in your own kitchen. Have you ever gotten a curry stain on a white shirt? The second you scrub it with soap, it turns this weird reddish-brown color, right? That's because turmeric is a natural indicator, and the soap you're using is a base. How cool is that? And get this, it's not just about what you can see. Some indicators actually work with your sense of smell. Yeah, they're called olfactory indicators. So for example, that really sharp smell of an onion or the sweet scent of vanilla, it can completely disappear if you add a base. But if you add an acid, the smell sticks around. It's a totally different way to play chemical detective. All right, enough with just identifying them. Let's see what happens when we actually make these things react. It is time for some chemical showdowns. Okay, this is a classic lab experiment, so watch this. You drop some zinc metal into an acid, and right away, it starts fizzing like crazy with all these bubbles. That's a gas being made. But what gas is it? Well, if you capture that gas in soap bubbles and then bring a flame close, you get this awesome little pop. That sound, that distinct pop, is the telltale sign of hydrogen gas. And that little pop just showed us a fundamental rule in chemistry. When an acid reacts with a lot of common metals, you always get two things, a salt and that hydrogen gas we just heard. Now, this isn't just some neat lab trick. It has major real-world consequences. So think about this. Why should you never store sour foods like curd or yogurt in brass or copper pots? Well, the curd is acidic. The pot is made of metal. You put them together, and you get that exact same reaction we just saw, which can spoil your food and even make it pretty harmful to eat. And now for the ultimate showdown, acid versus base. So we start with a base, and we add a few drops of an indicator that turns the whole thing this amazing, vibrant pink. Then, drop by careful drop, we add an acid. And you just watch. As the acid starts to cancel out the base, that bright pink color just vanishes. Poof, gone. It seriously looks like magic. And that magic is called neutralization. This is the answer to our very first question about the stomach ache. When a base and an acid react, they literally cancel each other out, and what you're left with is just a salt and plain old water. It's the perfect chemical peace treaty. So we've seen what acids and bases do, but the real question is, why do they do it? Let's dig a little deeper and uncover their secret identity. You know, if you look at all the different kinds of acids out there, what is the one single thing that connects all of them? What gives them their acidic superpowers? The answer, believe it or not, is super simple. It's water. A lot of acids, when they're dry, are kind of harmless. They're like sleeping giants. It's only when you dissolve them in water that their true, powerful personality comes out. Water is the key that unlocks everything. And here's a really cool experiment that proves it. If you put 2 electrodes into an acidic solution and hook them up to a light bulb, the bulb glows brightly. That's because the acid has released these tiny charged particles, we call them ions, into the water, and they let electricity flow right through. But if you try the same thing with, say, sugar water, the bulb stays dark. No ions, no electricity. Simple as that. And there it is. That's the secret. The true identity of an acid is its ability to release hydrogen ions, that's H+, in water. And for a base, its identity is releasing hydroxide ions, OH-. These little ions are responsible for everything they do. So, if it's all about these ions, can we actually measure how many there are? Can we put a number on just how acidic or basic something is? Oh, you bet we can. Let's talk about the pH scale. The pH scale is basically our ruler for acidity. It runs from 0 all the way to 14. And that little p in pH, it actually stands for the German word potens, which means power. So pH literally means the power of hydrogen. Here's the cheat sheet for how to read it. A pH of 7, right in the middle, is perfectly neutral. Think pure water. Anything below 7 is acidic, and the lower the number, the stronger the acid. Anything above 7 is basic, or what we call alkaline, meaning it has more of those hydroxide ions.
Okay, so why does any of this matter? Let's connect the dots and bring pH and everything else we've learned back to the real world, both inside you and all around you.
Look, getting the pH right is absolutely critical for life. Your own body has to stay in this super narrow, slightly basic range just to work properly. Even tiny shifts are a huge problem. Same thing in your mouth. When you eat sugary stuff, the pH drops, and when it gets below 5.5, that acid starts eating away at your teeth. On a planetary scale, when rain's pH dips below 5.6, we get acid rain, which can totally wreck lakes and forests. And of course, that antacid we talked about, it's just a mild base designed to neutralize the extra acid in your stomach. See, it's everywhere. And nature actually uses pH as a weapon. A bee sting hurts because it injects acid into your skin, which is why a mild base like baking soda helps soothe it. The stinging nettle plant does the same thing. It injects you with methanoic acid. But nature is clever, and it often provides the antidote right nearby. The dock plant, which is basic, can be rubbed on the sting as a traditional remedy.
And to bring this all full circle, let's go back to those salts that form when an acid and base neutralize each other. Here's a wild secret. A lot of them, like these gorgeous blue copper sulfate crystals, look perfectly dry, but they're hiding water molecules that are locked right inside their structure. We call it the water of crystallization. If you heat them up, the water escapes and they turn white. But then, and this is the cool part, just add a single drop of water back and that magic blue color instantly reappears.
So, there you have it. From soothing a stomachache to the color of a crystal, it's all part of this constant dance between acids and bases. The real takeaway here is that once you understand these basic ideas, you start seeing them everywhere. Chemistry isn't just in a lab. It's in your kitchen, it's in your garden, it's inside you. So the next time you see something that seems a little bit like magic, ask yourself, could it just be chemistry waiting to be explained?
Welcome to The Explainer. Today, we're going to dig deep into the elements that literally build our world. You know, we all think we know what separates a metal from a non-metal, but let me tell you, the real story is, well, it's way more explosive and fascinating than you probably remember from science class.
So let's start with the big question. What makes a metal a metal? I mean, it seems so simple, right? You can probably picture a piece of metal in your head right now. But is it really just about being shiny and hard? The answer, as we're about to find out, is buried deep, deep inside the atom itself.
All right, let's start with the basics, the textbook definition. We're taught that metals have that metallic luster. You know, they're shiny, they're supposed to be strong, you can hammer them into sheets, that's called being malleable, or pull them into wires, which is ductile, and of course, they're great at conducting heat and electricity. Non-metals, well, they're pretty much the opposite in every way. So case closed, right? Huh, not even close.
Because nature just loves to throw a wrench in the works. This is where all our neat little categories just completely fall apart. You've got mercury, which is definitely a metal, but it's a liquid. Then there's sodium, another metal, but it's so soft you can literally slice it with a butter knife. And on the other side, we have graphite, the stuff in your pencil, a non-metal that conducts electricity. And diamond, which is also non-metal, it's the hardest natural thing on the planet. So yeah, clearly just looking at them isn't going to cut it. So to get to the bottom of this, we've got to look past the surface. We have to go beyond the shininess and the hardness to find the real dividing line between these two elemental families. Okay, so if physical properties are totally unreliable, let's look at something else. Let's look at how these elements actually behave, their chemical reactions. Now that's where we find our next big clue.
And check this out. Just forget that image of a boring, stable chunk of iron. Some metals, like sodium and potassium, are so incredibly reactive that if you just expose them to the air, they can react so violently they burst into flames. They actually have to be stored under kerosene oil just to keep them from going wild. Now that is a powerful personality trait.
And what's really interesting is that we start to see a clear pattern here. There's a hierarchy. You drop potassium in cold water, and it's an instant, violent explosion. Magnesium, it needs hot water just to get a few bubbles going. Iron won't do a thing unless you blast it with steam. And gold? Gold couldn't care less. It doesn't react with water at all. This predictable pattern, this reactivity series, is a much, much better clue than just shininess. But what's causing it?
To understand that, we need to zoom in, way in. The real secret, the fundamental truth, lies at the atomic level, with those tiny little electrons whizzing around the nucleus. Okay, now this slide gets to the heart of everything. It's about motivation. Every atom has one goal in life, to be stable. Just like the cool kids, the noble gases. And the way to do that is to have a completely full outer shell of electrons. So look at sodium here. It has just one lonely electron in its outer shell. It is desperate to get rid of it. Chlorine, on the other hand, is just one electron short of a full set. It wants one, badly.
And this is where the magic happens. When a metal and a nonmetal get together, they don't share nicely. Nope, they make a transaction. The metal gives away its extra electrons, and the nonmetal swoops in and takes them. This transfer creates what we call an ionic bond.
So here it is, the big secret. Metals are defined by their tendency to give away electrons. They're the givers. And nonmetals, they're defined by their tendency to take electrons. They're the takers. That's it. That is the real elemental divide. So when sodium hands its electron over to chlorine, they form sodium chloride. Yep, common table salt. And now they're both stable, they're both happy, they both got what they wanted.
All right, so now that we know this atomic secret, this giveaway-takeaway relationship, we can finally understand how we manage to pull pure metals right out of the earth. Remember that hierarchy we saw with water? Well, it's all based on one thing: how easily a metal gives up its electrons. This creates the reactivity series, basically a ranked list from the most generous electron giver to the least. And this isn't just for a science test. This list is the absolute cheat sheet for chemists and engineers.
And this has some massive real-world results. The most reactive metals, like aluminum, they cling on to other elements in their natural ore so tightly that we have to use a brute force method, blasting them with huge amounts of electricity to break them apart. Meanwhile, the least reactive metals, like gold, are so unwilling to react with anything that we can literally just find them lying around in their pure native form. So we know what metals really are, and we know how to get them out of the ground, but how do we make them even better? And how do we protect them from their own reactive nature? Well, understanding reactivity is also the key to fighting back against nature. We know iron rusts because it's just trying to react with oxygen and water. So what do? We create barriers. We paint it, we oil it, or we do something really clever, like coating it with an even more reactive metal like zinc. That's called galvanizing. The zinc basically sacrifices itself to protect the iron underneath. Pretty smart. But the most powerful tool in our arsenal is alloying. This is where we stop being miners and start being creators. We start mixing different elements together to create brand new materials, materials with enhanced properties that are perfectly tailored for exactly what we need. And a perfect example you see every day is gold jewelry. You know, pure 24-karat gold. It's actually super soft. You could easily bend it. So to make it strong enough to be worn as a ring or a necklace, it gets mixed with stronger metals like copper or silver. That's what 18-karat or 14-karat gold is. It's an alloy. And this whole quest to master metals, it's not new. I mean, look at this iron pillar in Delhi. It's over 1,600 years old, weighs 6 tons, and it has barely rusted. Ancient metallurgists back then had figured out a process so advanced that modern scientists are still studying it today. It's just an amazing reminder of how long humanity has been on this journey. So when you think about it, from the salt on your food to the skyscrapers that shape our cities, it all comes back to a single simple act: an atom giving away an electron. Understanding this fundamental divide is what's allowed us to extract, protect, and combine elements to literally engineer the world around us. Which, of course, leaves us with a pretty big question. Now that we've built with alloys stronger than steel, what incredible new material will define our future? Have you ever stopped to think about what connects, well, pretty much everything? The food on your plate, the clothes on your back, even the very cells that make you, you? We're talking about carbon. And let me tell you, this quiet, unassuming element that basically runs the world from behind the scenes, it's hiding a fantastic secret. I mean, get this. The number of different compounds carbon can form is more than all the other elements combined, and it's not even close. So how? How does one single element manage to be that versatile, that fundamental to all life as we know it? Well, that's the mystery we're going to solve today. What is carbon's secret? Okay, so here's our first big clue, and it's a weird one.
You'd think, right, that something this important would be everywhere. But nope, it's actually incredibly rare. I mean, look at these numbers. The Earth's crust is only 0.02% carbon. The atmosphere, a measly 0.03%. It's a tiny, tiny fraction of the planet. And that right there brings us to this central puzzle, what I like to call the carbon paradox. How on earth can an element that's so scarce be the fundamental building block for, well, everything that matters? How can something so rare be so absolutely essential? Just think about your day for a second. The food you ate for breakfast? Carbon. The shirt you're wearing? Carbon. The medicine in your cabinet? The fuel in your car? The pages of a book? It's all carbon. And oh yeah, you. Every living thing from a tiny microbe to a giant whale, you are a carbon-based life form. It's wild, right? The paradox just gets deeper and deeper. So to start unraveling this mystery, we've got to look at how carbon interacts with other atoms. See, the secret isn't about what it takes or what it gives away. It's all about how it shares. Carbon is the ultimate team player, a master of compromise.
All right, quick chemistry lesson. An atom's main goal in life is to have a full outer shell of electrons. That's what makes it stable and happy. Carbon has 4 electrons in its outer shell, but it really wants 8. So what's it going to do? Gaining 4 more is a no-go. Its tiny nucleus just can't handle holding that many. And losing all 4? That would take a ridiculous amount of energy. So it's kind of stuck between a rock and a hard place.
But what if there's a third option? What if carbon doesn't have to choose at all? Instead, it finds this absolutely brilliant solution, sharing. It forms what we call a covalent bond by sharing its 4 outer electrons with other atoms. It's like a perfect handshake where everybody gets what they need. And this simple idea, this compromise, this is the absolute foundation of all of carbon's power. Now, this ability to form these strong, stable, sharing bonds is what unlocks 2 incredible, unique properties. Let's call them carbon's superpowers. And these 2 things, they explain literally everything. Superpower number 1, tetravalency. I know, it's a fancy word, but tetra just means 4. Simple as that. Because carbon has those 4 electrons to share, it's like it has 4 hands, ready to form 4 strong bonds at the same time. 4 connection points. This is huge. And if that was cool, get ready for superpower number 2, because this one is even more mind-blowing. It's called catenation. This is the ability for carbon to use those 4 hands to link up with other carbon atoms again and again and again. Seriously, no other element in the periodic table can do this anywhere near as well as carbon. So what does this actually look like? Well, this catenation thing means carbon atoms can just snap together, kind of like Lego bricks, building these incredibly long and super stable chains. But hold on, it gets better. They don't have to be just straight lines. Nope, these chains can branch off, like the branches of a tree, creating all these new, complex shapes. The variety just explodes.
And for the grand finale, these chains can even loop all the way back and connect to themselves, forming stable rings of different sizes. So think about it. You've got chains, branches, and rings. With just these few simple rules, carbon becomes this master architect, able to build a practically infinite number of structures. We're talking everything from simple molecules in natural gas to the mind-bogglingly complex double helix of our DNA.
So you put these 2 superpowers together, the 4 connection points and the ability to link to itself, and what do you get? You get a master of disguise. One single element that can show up in all these completely different forms. It all just depends on the blueprint, on how those atoms are put together. You want a perfect example? Look at diamonds and graphite. Both are 100% pure carbon. That's it. But in a diamond, the carbon atoms are locked into this super rigid 3D web, making it the hardest substance we know. Then you've got graphite, like the stuff in your pencil, where the carbons are arranged in flat sheets that just slide right past each other. That's why it's so soft and slippery. Same atoms, totally different worlds. And it's not just about how carbon arranges itself. It can also accessorize. Other little clusters of atoms, which scientists call functional groups, can attach to the main carbon chain. I love the analogy of charms on a bracelet. Each charm you add completely changes the whole thing. Slap on an OH group, and boom, you've got an alcohol. Add a COOH group, and now you've got an acid. It's like molecular customization. Okay, so this is all really cool chemistry, but how does it actually affect you? Let's bring it right into your home. Think about something you do every single day. Washing. How does soap, which is really just a fancy carbon molecule, actually get things clean? A soap molecule is basically a long carbon chain with a split personality. It has a tail end that absolutely hates water, it's hydrophobic, but it loves oil and grease. Then it has a head that's the complete opposite, it loves water. So when you wash your hands, all those little oil-loving tails rush in and grab onto the dirt, surrounding it. They form this tiny little cage, called a micelle, with the dirt trapped safely inside. All the water-loving heads stay on the outside facing the water. And when you rinse, the water just grabs those heads and washes the whole package, dirt and all, right down the drain. How cool is that? That is some powerful carbon chemistry, right in your sink.
So the mystery is solved. It turns out it's not about being common, it's about being clever. This ridiculously rare element, carbon, becomes the ultimate builder of our world, all because of two simple tricks: sharing 4 electrons and linking up with itself. From those simple rules, you get the insane complexity of life and everything around us. It built our entire world, and it built us. So the real question left is, what are we going to build with it next?
So let's get right into it. What does it actually mean to be alive? You know, it seems like a really simple question, but the answer, well, the answer is this incredible story about a constant, invisible battle that's happening inside of us right now. We're going to break down the amazing machinery that keeps everything going, from the tiniest microbe all the way up to a giant blue whale.
I mean, think about it. What's the real difference between a running dog and a rolling stone? At first glance, it's obvious, right? One's alive, one's not. Duh. But why? I mean, they're both moving. They're both pretty complex objects. The real difference isn't just the movement itself, it's about what's driving that movement.
And here's the secret. Life is basically an act of defiance. See, everything in the universe naturally wants to break down, to fall apart into chaos. But a living thing? It's this amazingly organized structure that is constantly, and I mean constantly, burning energy just to repair itself and fight against that breakdown. It's a war being fought at the molecular level every single second of every day.
So that's the core problem for absolutely everything that's alive. How do you keep it all together? How do you maintain this incredibly complex and organized system when the entire environment is basically trying to tear you apart? How do you keep the whole show on the road?
Well, the answer is a whole set of jobs that have to keep going, 24/7, no breaks. It doesn't matter if you're running a marathon or if you're fast asleep, these jobs are happening. Biologists have a name for them. They call them life processes. And these processes are the solutions to the problem of staying alive.
So let's start with problem number 1. All this constant repair work, it needs energy. And it needs building blocks, right? You can't run a factory without power and raw materials. And life is no different. You can't just wish for it, you gotta get it from somewhere. So, how?
The solution is nutrition. It's really all about the process of taking in food. And that food provides both the energy and the raw materials that you need from the outside world. This is the first absolutely critical step in powering the whole operation.
Now, to get this fuel, life has come up with 2 really ingenious strategies. On one hand, you have the autotrophs. Think of them as the self-feeders. These are organisms like plants that are super self-sufficient. They literally make their own food from sunlight and air. And then on the other hand, you've got the rest of us, the heterotrophs, or other feeders, who have to get our energy by, well, eating other organisms.
And since we're heterotrophs, we've got a pretty specialized system for this. Our digestive tract is basically a disassembly line. It all starts in the mouth, then moves down to the super acidic stomach for more breakdown, and then it finishes up in the small intestine. And that's where all those complex molecules are finally broken down into simple, usable bits that our body can absorb.
Okay, so we've digested our food, we've absorbed all the good stuff. But here's the thing. Those nutrients are just raw fuel. They're not actually energy. Not yet. You still need a process to unlock the energy that's stored inside those molecules.
And that process is respiration. Now, when you hear that word, you probably think of breathing, right? Lungs, taking in air. But we're talking about something deeper here, something happening in every one of your cells. It's cellular respiration, the chemical process of breaking down food, like glucose, to release energy that your cells can actually use to get work done.
So, here's the key takeaway. All that energy from respiration gets captured and stored in this amazing little molecule called ATP. You can think of ATP as the universal energy currency for the cell. Every single thing you do, from a thought firing in your brain to a muscle twitching, is paid for with ATP. For those of you who love the details, each little packet has about 30.5 kilojoules per mole of energy, but you don't have to remember the number. Just picture it as this perfect little rechargeable battery, sized just right to power one specific job inside a cell.
Now, it turns out there are a couple of ways our cells can do this. There's aerobic respiration, which uses oxygen and is incredibly efficient. It cranks out a ton of ATP. Then there's anaerobic respiration, which doesn't need oxygen but is way less efficient. And fun fact, if you've ever felt that burn in your muscles during a really hard workout, yeah, that's the lactic acid building up from your muscles doing anaerobic respiration.
But being this efficient at unlocking energy creates a whole new problem, a logistical nightmare. See, if you're a single cell, getting fuel and oxygen is easy. You just absorb it from whatever's around you. But for a big creature like us with trillions of cells, that's impossible. Most of our cells are buried deep inside. If we had to rely on just simple absorption, it would literally take years for a single molecule of oxygen to get from your lungs to your toes.
So what's the solution? Well, you build a high-speed delivery network. And that's exactly what our transportation or circulatory system is. It's this incredible system of pumps and tubes designed to haul essentials like oxygen and nutrients to every single cell, no matter how remote it is.
And to get that oxygen into the delivery system in the first place, our bodies have an amazing design. Get this, the tiny air sacs in your lungs, where the oxygen actually gets into your blood, have a combined surface area of about 80 square meters. That's a huge surface, all folded up neatly inside your chest, just to make sure you can get as much oxygen as possible from the air into your blood with every breath.
And the engine of this whole system is our amazing four-chambered heart. It's what we call a double circulation pump, and it's genius, really. The right side of the heart takes in all the used deoxygenated blood and sends it over to the lungs. Then the left side takes that fresh, oxygen-rich blood from the lungs and pumps it out with huge force to the rest of the body. Keeping these two blood types separate is absolutely key to meeting our high-energy needs.
Okay, so let's recap. We're getting fuel, we're unlocking its energy, and we're delivering it all over the body. We're almost there. But there's one final critical problem. All these chemical reactions, all this work, it produces waste. And if you just let that toxic waste build up, well, that's not good. You've got to have a way to take out the trash.
And that is where excretion comes in. It's the body's dedicated sanitation department. Its entire job is to collect all those harmful metabolic wastes and get them out of the body before it can poison itself from the inside.
In humans, the absolute star of the show is a tiny structure called the nephron. You have millions of these little filtering units in each one of your kidneys. And they're not just simple filters, they're super smart. They work by filtering your blood, pulling out all the waste products like urea. But then they cleverly reabsorb all the useful stuff your body wants to keep, like water, glucose, and salts, before finally sending the bad stuff out.
So there you have it. 4 big problems and 4 ingenious, interconnected solutions for staying alive. You got to get food, you got to unlock its energy, you got to deliver it everywhere, and then you got to clean up the mess. And together, all these life processes create the engine that powers that constant fight against chaos. They create the dynamic, incredible system that we call a living organism.
But this brings us to a really fascinating and kind of weird edge case. See, our source material points out that viruses, well, they don't do any of this stuff on their own. There's no internal movement, no repair, no maintenance, nothing. At least, not until they manage to hijack a living cell.
Which leaves us with a really big final question. If being alive is defined by this constant internal fight against breaking down, this active, 24/7 self-maintenance, then where do viruses fit in? Are they actually alive, or are they something else entirely? That is a great puzzle to think about.
All right, let's dive into something that's happening inside all of us right this second. How do living things, from us to the plants in the garden, actually control what they do and react to the world? It's all about this incredible survival toolkit that's been built up over millions of years. So let's start with a really simple question. You've definitely done this. You accidentally touch a hot stove, and your hand yanks back before your brain even gets the memo that it hurts. How does that happen? What's going on there? It's not magic, it's an amazing high-speed survival trick, and we're going to break down exactly how it works.
You know, when you really boil it down, life is just one reaction after another. Survival isn't just about the big things, like finding food. It's about constantly, and I mean constantly, responding to little changes in your environment in just the right way. Every moment is a test, and your body needs a system to ace it.
And what's so cool is how different these actions are. A cat chasing a mouse, a plant literally bending itself towards the sun, even you making the decision to whisper instead of yell in a quiet room. Every single one of these is a carefully controlled response.
It just goes to show that every living thing needs a super sophisticated system for control and coordination to make the right move. So, when things get really serious, when you need to react now, how do animals pull it off? Well, the first part of the answer is the nervous system. You can think of it as the body's special ops team, built for those moments when every single millisecond is critical. The best way to picture the nervous system is like a dedicated fiber optic internet cable running through your whole body. It's not like Wi-Fi, it's a direct physical connection. It sends these electrical impulses at insane speeds straight to a specific target, a muscle, a gland, wherever the message needs to go. It's direct, it's targeted, and wow, is it fast. So what's the actual hardware here? What are these cables made of? They're made of neurons. The neuron is the basic building block, that fundamental messenger wire. It's a special kind of cell that has one job, and it does it better than anything, passing a message from point A to point B. So how does a neuron actually fire? Picture this. A message comes in at one end, at a part called the dendrite. That message gets turned into a little electrical pulse that just zips down the length of the cell, down the axon. Then, right at the very end, it hits a tiny gap, called the synapse. To cross that gap, the electrical pulse triggers the release of chemicals that jump across and kickstart the whole process in the very next neuron. It's like an amazing biological relay race. Okay, so this system is incredibly fast, right? But there's a catch. There's a bottleneck. And that bottleneck is the brain. Sending a signal all the way up to your brain, having the brain figure out what's going on, make a decision, and then send a command back down, well, by the time all that happens, your hand could be toast. The body needed a faster way. It needed a shortcut. And this is the body's brilliant solution, the reflex arc. This is the emergency override switch. That hot signal travels from your hand to your spinal cord, and the spinal cord, without even bothering the brain, immediately sends a command back to your muscles to pull away. The brain finds out what happened a split second later, which is why you feel the pain after you've already moved. So let's be super clear on the difference here. A reflex, like pulling your hand from a flame, is totally involuntary. It's a lightning-fast protective move controlled by the spinal cord. But a voluntary action, like walking, is completely different. That's a deliberate choice, controlled by the brain, and it involves all sorts of complex things like balance and precision. Of course, we don't just live our lives as a bundle of reflexes. For everything else, from picking up your phone to figuring out a tough problem, we need the main headquarters, the command center, the brain. The brain is basically the ultimate CEO. It's constantly getting a flood of data from your eyes, your ears, your skin, from everywhere. It processes all that info, compares it to past experiences, and then makes decisions. It's in charge of every conscious thing you do, and it runs all the background programs that keep you alive, like your heartbeat and breathing, without you even noticing. You know, there's a quote from our source material that just nails this. A simple reflex might only use a few neurons, but thinking, oh, that's a whole other level. It's this incredibly complicated dance involving countless nerve impulses from tons and tons of neurons, all firing in complex patterns. It's the difference between a simple switch and a supercomputer.
But what happens when you need to send a message not just to one specific muscle, but to the entire body all at once? That point-to-point nervous system isn't really built for that. For body-wide alerts or for slower, long-term projects like growing, you need a totally different system.
Yeah, the big limitation of that hardwired electrical system is that it only reaches the cells it's physically plugged into. You can't send a million separate electrical signals to prepare your whole body for a big emergency. You need to send out a general broadcast.
And that's where the hormonal system comes in. Think of it as the body's Wi-Fi network. It broadcasts chemical messages, called hormones, into the bloodstream. And then, any cell in the body that has the right kind of receiver can pick up that message and act on it. It's definitely slower than the nervous system, but its reach is massive. Let's put this into a real-life situation. Okay, imagine you're walking down a dark street and you suddenly hear quick footsteps right behind you. Your body needs to get ready for one of two things, and fast: fight or flight. In that split second, your adrenal glands just dump a powerful hormone into your system, adrenaline. This chemical messenger floods into your bloodstream and travels everywhere, carrying one simple, urgent memo to every part of your body. Get ready for action now. And the body listens. Immediately, your heart starts pounding to get more oxygen to your muscles, you start breathing faster, blood gets rerouted away from stuff that doesn't matter right now, like digestion, and sent straight to your arms and legs. All of this is perfectly coordinated to make you as powerful and fast as you can possibly be.
Okay, so we've seen how animals use fast nerves and slower hormones. But what about plants? This is where it gets really interesting. They have to deal with threats and find resources too, but they don't have nerves, they don't have muscles. So how in the world do they pull it off?
It turns out plants have evolved two totally genius strategies. First, they have some really rapid movements that have nothing to do with growth. And second, they have slower, more deliberate movements that are all about growth. The mechanics behind this are just wild. When our muscles move, it's because specialized proteins are literally changing shape and contracting. But when a touch-me-not plant folds up its leaves when you touch it, it's not using protein, it's using water. The cells instantly change how much water is in them, causing them to either swell up or shrink down, and that's what makes the leaf fold. It's a completely hydraulic system. It's amazing. Now for the slower stuff, plants have their own versions of hormones. A perfect example is a chemical called auxin. It's made at the very tip of a growing shoot, and its job is to help cells get longer. So when sunlight hits one side of the plant, the auxin actually moves over to the shady side. This makes the cells on the shady side grow longer and faster, which physically bends the whole shoot towards the light. So clever. So there you have it, 3 completely different, totally ingenious strategies for survival. You've got the lightning-fast electrical wiring of the nervous system, the widespread chemical broadcast of the hormonal system, and the patient, powerful movement of plants driven by growth itself. Each one is a beautiful solution to the puzzle of life. So which one do you think is the most incredible? It really makes you think. Thanks for joining me. Welcome to The Explainer. Today, we're diving into one of life's greatest tricks, how it makes more of itself. It's a fantastic story, stretching from the simplest single-celled organisms just making copies, all the way to the incredible genetic shuffle that makes you, well, you. So let's get right into it.
Okay, so let's kick things off with a question. It sounds simple on the surface, but it really gets to the core of, well, everything. I mean, really think about it for a second. You need to eat, right? You need to breathe. But you, as an individual, you don't actually need to reproduce to stay alive. In fact, it takes a ton of energy. So why bother? If it's not for the individual survival, what's the end game here? And here's the thing. It was never really about the individual in the first place. It's all about the species. The true mission, the fundamental drive of life, is to make sure the pattern, that biological blueprint, keeps going long after any single one of us is gone. It's about ensuring there's a tomorrow for your kind. Okay, so how do you keep that pattern going? Simple. You copy the blueprint. And that master blueprint, the one for basically every living thing on this planet, that's DNA. It's a molecule tucked away in our cells that holds all the instructions for building a body. When you boil it all down, reproduction is just a 2-step dance. That's it. Copy the DNA, then split the cell. Sounds easy, right? But everything, all the incredible complexity of life, comes from this one simple process. And it's the how that's where the story really gets wild. All right, let's start with the simplest strategy out there, asexual reproduction. This is where one single individual handles the whole job, all by itself. Think of it as life's original copy-paste function. So the most direct way this happens is something called fission. You can see an amoeba doing it right here. One cell just pinches in the middle and splits into 2 new individuals. 1 second there's one, the next second there are 2. It doesn't get more direct than that. Now, it gets a little more complex with multicellular critters. Take the Hydra, for example. It does something called budding. A little mini-me, a tiny version of the parent, literally just starts growing on the side of its body. And once it's big enough, pop, it just attaches and floats away to start its own life. Kind of wild, right? And really, nature is full of these cool copy-paste tricks. You've got Spirogera, which can just break into pieces and each piece becomes a new one. Or a planaria, those flatworms that can regrow from just a tiny fragment. Then there's bread mold, rhizopose, which just shoots out these little spores that can land somewhere and start a whole new colony. So this all sounds super neat and tidy, right? Just making perfect copies over and over. But this leads to a huge, and I mean huge, question about how this copying thing actually works. The question is this: Are those copies really identical? Is it like putting a piece of paper on a photocopier and getting a perfect 100% flawless duplicate every single time? Well, the answer we get from the science is a big, resounding no. It turns out that no biochemical reaction, not a single one, is absolutely perfect. Little mistakes, little errors, they're just bound to happen.
And here is the twist that changes everything. The copies are super, super similar, but they are never, ever perfectly identical. It's more like trying to copy a massive book by hand. You're going to make a few typos, right? A changed word here, a missing comma there. These little glitches, these variations, they're actually part of the deal.
And this, right here, is where you see the absolute genius of the system. Those mistakes, they're not bugs, they're features. It's like evolution has its own built-in research and development department. Just imagine a bunch of bacteria hanging out in a pond, and suddenly the temperature spikes. Almost all of them die. But what about that one bacterium that has a random little typo in its DNA that helps it deal with the heat? Well, it survives, and all of its descendants inherit that awesome new trait. So you see, variation isn't just a backup plan, it's the very engine that drives evolution forward.
Okay, so if these random variations are so important, what if there was a way to speed things up? To create more variation and do it faster? Well, there is, and that's where sexual reproduction enters the picture. See, just waiting around for random DNA typos to happen, it works, but man, is it slow. The whole DNA copying system is actually really, really good at not making mistakes, so big, new variations are pretty rare.
Sexual reproduction is life's ultimate hack for this speed problem. Instead of just waiting for a new mutation to pop up, you take two different individuals, each with their own collection of unique variations. You mix their DNA together and bam, the offspring gets a totally new, novel combination of traits. It's like instead of waiting for the deck to give you one new card, you take two entirely different decks of cards and shuffle them together. You're guaranteed a new hand every single time.
So what we've got here are two completely different game plans for keeping a species going, and each one has its own set of strengths and weaknesses, depending on what the world is throwing at you. And it really all comes down to a classic trade-off. Asexual reproduction, it's super fast, super efficient, it's perfect if you live in a world that never, ever changes. You know, the classic if it ain't broke, don't fix it approach. But sexual reproduction, it's all about creating that constant stream of variation. And that is the ultimate survival kit for living in a world that's constantly changing.
Okay, let's bring this all together. What's the big picture here? What's the main takeaway when we look at these two totally different ways of making life?
Well, in a lot of organisms, this whole DNA mixing business involves two super specialized cells, which we call gametes. You've got the male gamete, think of a sperm cell. It's small, it's designed to travel, and it's on a mission to find the female gamete, the egg cell, which is much larger because it's packed with all the food and resources needed to get a new life started.
And that right there brings us full circle, back to the most important point of all. It doesn't matter if it's coming from the slow, steady drip of tiny copy mistakes or the crazy genetic shuffling of sex. It all leads to one thing: variation. Variation is what allows a species to survive over the long haul. It's the key to adapting, to enduring, and to thriving, no matter what the world throws at it.
So, when you think about it, what's the biggest lesson life has to teach us? It's that diversity, that variation. It isn't just a nice-to-have thing. It's the absolute foundation of survival. And that kind of leaves you with a big question, doesn't it? If this principle is so critical for survival in the biological world, what does that say about all the other complex systems we've built in our own world? Hello and welcome. Today we are diving into one of the biggest mysteries in all of biology: heredity. I mean, why do we look like our parents? It seems simple, but the answer is an incredible story of clues, detective work, and a code that connects all of us. So let's get into it.
You know, it's a question we've all asked ourselves at some point, right? You look in the mirror and see a piece of your mom here, a piece of your dad there. But how does that actually work? Why those specific things? It's a puzzle, and today we're going to put the pieces together.
Okay, let's start with a really simple visual example. Go on, check your earlobes. Are they kind of dangly and free, or are they attached all the way down the side of your head? These are just two versions of the same treat, and this idea of variation is right at the heart of our story.
To solve this mystery, we've got to travel back in time, back to the 19th century, and we need to meet our lead investigator, a monk named Gregor Mendel. He used a humble monastery garden as his laboratory to run one of the most important investigations in the history of science.
So what was Mendel's secret weapon? I mean, people had been wondering about inheritance for centuries, but Mendel brought something new to the table, something totally different: math. He didn't just look and describe, he counted. And you know what? That, right there, changed everything.
His toolkit was just brilliantly simple. He chose garden peas because they grow fast and have these really obvious contrasting traits. They were either tall or short, no in-betweens. He could control exactly which plants bred with which, and this is the most important part. He kept super detailed records of every single result.
And this is where we get to the real mystery of his experiments. We could call it the case of the vanishing trait, because what he found at first was, well, it was just plain weird. It was completely unexpected.
All right, so picture this. Mendel takes a purebred tall pea plant and crosses it with a purebred short one. Now, common sense might tell you you'd get medium plants, right? Or maybe a mix of tall and short. But nope, that's not what happened. Every single one of the baby plants was tall.
It was like the treat for being short just vanished. Poof, gone. It didn't blend in. It just disappeared. This was the big puzzle that Mendel absolutely had to solve. Where did it go?
And this is where it gets really, really cool. Mendel then took those tall offspring plants and let them self-pollinate. And in the next generation, that lost trait for shortness, it suddenly popped right back up.
And it didn't just reappear randomly, no way. It came back in this really precise, predictable pattern. For every 4 plants, about 3 of them were tall and 1 was short, a perfect 3-to-1 ratio. Now, for a mind like Mendel's, a guy who loved math, this wasn't just a coincidence. It was a massive clue.
This mathematical pattern was the key. It led Mendel to his incredible breakthrough idea. He realized traits weren't blending together at all. Instead, they were controlled by pairs of what he called factors, and some of these factors could basically hide or mask the others.
He called the tallness trait dominant. And what that meant was a plant only needed 1 copy of that tall factor to actually be tall. It was the loud one in the room. If it's there, you're gonna see it.
And the shortness trait, he called that recessive. This means the factor was still there, hiding in that first generation, but you could only see it if a plant inherited 2 copies of that short factor.
And this idea just brilliantly explains the difference between what's happening on the inside versus what we actually see on the outside. The genotype is the genetic code itself, big T, or big T, little t. But the phenotype is the physical thing we can see. Is the plant tall or is it short? So as you can see, you can have different genetic codes that result in the exact same look. Now, of course, Mendel had no idea what his factors actually were. It would take almost another 100 years of science to connect his amazing work in the garden to the molecule of life itself, DNA. So today, we know that Mendel's factors are what we call genes. And here's the chain of command. A gene is a specific section of your DNA, like a single recipe in a giant cookbook. That recipe gives the instructions to build one specific protein. That protein is the worker molecule that goes and does a job, which then creates the trait we can see. Yeah, so that link is absolutely crucial. A gene isn't the trait. A gene is the information for a protein, and the protein is what actually builds the trait. So a slightly different gene might make a different or less efficient protein, leading to a different trait, like a short plant instead of a tall one.
Okay, so let's bring this all back to us. These exact same rules of inheritance are chugging away inside every single one of us, and they determine some of our most basic characteristics, like our biological sex.
So here's how it works. In humans, most of our genetic info comes in 22 matched pairs of chromosomes. But that 23rd pair, the sex chromosomes, that one's a little different. Females have a matching pair of 2 X chromosomes, but males have a mismatched pair, 1 X and 1 little Y chromosome. And here's how that plays out when a child is conceived. A mother, since she only has X's, can only pass on an X chromosome. A father, on the other hand, can pass on either his X or his Y. So what does this mean? It means there's a 50% chance that the father's sperm cell that wins the race will be carrying an X, resulting in a baby girl. And there's a 50% chance it'll be carrying a Y, resulting in a baby boy. It's basically a coin flip every single time. So what's the big takeaway here? It's that since a child always gets an X chromosome from their mother,
It's the chromosome they get from their father, either that second X or a Y, that actually determines the biological sex of the child.
You know, it's pretty amazing when you think about it. We went from a monk just patiently counting peas in a garden to understanding the fundamental rules that guide all life on Earth. It really makes you wonder, if these simple, elegant rules can create all the incredible complexity we see around us, what other hidden codes are still out there, just waiting for someone to start asking the right questions?
All right, let's talk about light. We're going to pull back the curtain on a couple of its biggest tricks. I'm talking about the simple physics that explains, well, almost everything you see, from your own face in a mirror to the super powerful lenses inside your phone's camera. Let's get right into it. But first, let's start with a little mystery, one you've probably noticed 1,000 times but never really thought about. Have you ever looked at yourself in a spoon? You know how on one side you're totally upside down and on the other you're all stretched out and weird? Why is that? The answer, believe it or not, unlocks the two main ways we can control and manipulate light. Okay, so the very first thing you have to know about light is that it's kind of lazy. It loves to travel in a perfectly straight line. We call this path a ray of light, and this one simple rule is the foundation for literally everything else we're about to talk about.
But what happens when that straight path gets blocked? Well, that's when things get really interesting. We can force light to change its direction in two main ways. We can make it bounce off a surface, that's called reflection, or we can make it bend as it passes through something, and that's called refraction. Bouncing and bending, that's the whole game.
So, let's start with the bounce. When light hits something it can't pass through, like a mirror, it reflects. But when that mirror is curved, that's when it can do some truly amazing things.
And this brings us right back to our trusty spoon. Turns out the two sides of a spoon are a perfect model for the two main types of curved mirrors. The side that you'd scoop cereal with, the one that caves in, that's what we call a concave mirror. And the back side, the one that bulges out, that's a convex mirror. See, you already get it.
Think of a concave mirror as a sort of light collector. Its special curved-in surface grabs all the light rays hitting it and forces them all to meet up at a single, super-focused point. This ability to converge light, that's its superpower.
And that superpower is incredibly useful. You know the powerful beam from a car headlight? That's a concave mirror turning a tiny bulb's glow into a focused blast of light. The shaving mirror that lets you see every detail? That's a concave mirror, magnifying your reflection. They can even concentrate sunlight so intensely that they're used in solar furnaces to melt metal. Pretty cool, huh? All right, now let's flip the spoon over. The convex mirror does the exact opposite thing. Its surface bulges outward, and when light hits it, it scatters, spreading the rays out in all directions. Its job is to diverge the light.
Now, here's the really important part. Unlike the concave mirror, which can do all sorts of things, a convex mirror is super consistent. It doesn't matter how close or far you are, the image it makes is always the same. It's upright, it looks like it's behind the mirror, and it's smaller than the real thing. Always. This predictability makes them absolutely perfect for one very, very important job. You know that little warning on your car's passenger side mirror? Objects in mirror are closer than they appear. Why on earth would we use a mirror that messes with our perception of distance?
It's a trade-off. By making everything look smaller, that convex mirror can cram way more of the world into its reflection. It gives you a much wider field of view so you can spot a car sneaking up in your blind spot. It's a life-saving safety feature, and it's powered by pure, simple physics.
Okay, so that covers bouncing. But what about when light doesn't bounce? What happens when it actually passes through something like glass or water? Well, this is where light shows off its second big trick, bending. I guarantee you've seen this. You stick a straw in a glass of water, and right where it hits the surface, it looks like it's bent or even snapped in two. Your eyes aren't playing tricks on you. The light itself is actually bending. This phenomenon is called refraction.
So what's actually going on? Well, imagine you're pushing a shopping cart from smooth pavement onto some thick grass at an angle. The first wheel to hit the grass slows down, right? That forces the whole cart to turn. Light does the exact same thing. When it goes from air into water, it slows down, and that change in speed forces it to bend. That, in a nutshell, is refraction.
And by shaping glass in just the right way, we can totally control this bending. A convex lens, the kind that's thicker in the middle,
bends light rays inward, focusing them. And a concave lens, which is thinner in the middle, does the opposite, spreading those light rays out.
You know, here's a really easy way to remember all this. Lenses and mirrors are basically opposites. A convex lens, the one that bulges out, acts just like a concave mirror, the one that caves in. They both focus light. And a concave lens which caves in acts like a convex mirror which bulges out. They both spread light. Simple as that.
And that incredible focusing power of a convex lens is exactly what lets us magnify things. It takes the light rays coming from a tiny object, bends them, and creates a much bigger image for our eye to see. It's the simple, brilliant idea behind every single magnifying glass.
So there you have it. We've got 4 fundamental tools in our toolkit. 2 types of mirrors for bouncing light and 2 types of lenses for bending it. Let's put this all together and see how these 4 simple things are, well, pretty much everywhere.
So here's the final cheat sheet. Whether you need to focus light for a powerful headlight or spread it out for a car's side view mirror, whether you need to magnify the world through a camera or correct your own vision with glasses, it all comes down to these 4 basic tools. Just 2 ways to bounce light and 2 ways to bend it. That's the whole story.
But what's the one single rule that underpins all of this? Every single bounce, every single bend, it's this number. In the vacuum of space, light travels at an absolutely staggering 300 million meters per second. It's the ultimate cosmic speed limit. Nothing is faster.
And that speed limit is the key to everything. See, refraction, the bending, only happens because light is forced to slow down when it hits something like water or glass. And reflection follows its perfect, predictable laws because light travels at that constant, unbreakable speed. It's the one rule to rule them all.
So we've figured out how to bounce and bend light, and we've built our entire modern world with those 2 tricks. But here's a final thought for you. What if those aren't light's only tricks? Modern physics tells us that sometimes light acts like a tiny particle, and at other times it acts like a wave at the same time. So what happens when we truly master that trick? Well, that's a story for another day.
All right, today we're going to dive into the incredible science behind your most precious sense, your sight. We'll find out how your eye works just like a super advanced camera and how the world plays these amazing tricks with light to create everything from rainbows to blue skies.
So let's kick things off with a fun question. What could your eyes possibly have in common with a rainbow? Well, the answer, as we're about to see, is that they are both absolute masters at bending light. Let's get into it.
First up, let's just take a moment to appreciate the human eye. I mean, think about it. It's the organ that lets you see a sunset, read a friend's face, and just navigate this beautiful, colorful world. It's our most powerful connection to everything around us.
It's pretty amazing, right? How perfectly the eye maps onto a camera? Or actually, it's the other way around, how a camera mimics the eye. Light comes in through the cornea and lens, which are just like a camera's lens system. The iris? That's your aperture, deciding how much light gets in. And the retina at the very back of your eye? That's your own personal, super high-res, biological film sensor.
Okay, so how does this all work? Well, it happens in the blink of an eye, no pun intended. Light enters, the iris adjusts, and the lens focuses it perfectly. Then, cells on the retina turn that light into electrical signals, which shoot down the optic nerve. And finally, your brain puts it all together into the picture you see. All of this happens way faster than you can even think about it.
Now here's one of the coolest things about your eye. It has this superpower called the power of accommodation. This is basically your eye's built-in autofocus. The lens, which is made of this flexible jelly-like stuff, literally changes shape to adjust its focus. It's how you can look at your phone one second and then a plane in the sky the next, seamlessly.
But you know, that autofocus has its limits. For an average adult, the closest you can comfortably focus on something is about 25 centimeters. Any closer than that, and you'll notice things start to get a little blurry. We call that your near point.
The thing is, over time, that incredible power of accommodation can start to weaken. And when the eye loses some of that flexibility, it can lead to really common vision problems. Let's take a look at one of the biggest ones, myopia, which you probably know as nearsightedness.
So what's actually going on inside a myopic eye? Well, the lens is bending the light from things far away a little too much. This makes the image focus in front of the retina instead of right on it. And the result, blurry vision for anything in the distance.
And the fix? It's just some brilliantly simple physics.
You put a corrective lens, a concave lens to be specific, in front of the eye. Its whole job is to bend the light rays outwards just a tiny bit before they even hit your eye's own lens.
And you can see the result right here. That little pre-adjustment is just enough to nudge the focal point backward, landing the image perfectly on the retina. And just like that, distant vision is sharp and clear again.
You know, correcting vision is one thing, but restoring it is wow. And this is a fact that really sticks with you. Through eye donation, a single person can give the gift of sight to as many as 4 people who are suffering from corneal blindness. It's an absolutely incredible gift that can change someone's entire world.
So, we've seen how the lens in our eye is a master at focusing light to create a clear picture. But that makes you wonder, right? What's actually inside that light to begin with? Well, to find out, we need to pass it through a different kind of lens, a simple glass prism.
And that leads us to this beautiful phenomenon called dispersion. It's simply the act of splitting white light and revealing the secret rainbow of colors hidden inside. And a prism is the perfect tool for the job.
And what you get is that classic spectrum of colors we all know. You probably remember the acronym VIBGYOR from school? What's happening is that each color of light bends at a slightly different angle. Violet bends the most, and red bends the least. And that's what fans them out into that beautiful arc.
And now we can finally answer our question from the beginning. A rainbow is just dispersion happening on a gigantic scale. Millions of tiny water droplets in the air act like little prisms. Sunlight goes in and refracts. It bounces off the back of the droplet and then refracts again on its way out, splitting a light into that amazing arc of color we see.
But you know what? It's not just tiny water droplets. Our entire atmosphere is like this one giant, crazy lens, always bending and scattering sunlight to create some of the most spectacular optical illusions we see every single day.
For example, have you ever looked up at the night sky and just wondered, why do stars twinkle and flicker, but planets seem to shine with this steady, constant light? The answer is all about atmospheric refraction.
Okay, let's break this down. On the left, you've got a star. It's so unbelievably far away that to us, it's just a single point of light. As that one little beam travels through our turbulent atmosphere, it gets bounced around, and we see that as twinkling. But now look at the planets on the right. They're way closer, so they look like a tiny disk, not a point. All the light from that disk gets averaged out, which cancels out the twinkling and gives us that nice, steady glow.
And get this is another wild effect of our atmosphere. It actually bends sunlight around the curve of the Earth. What that means is we see the sun for about 2 minutes before it even physically crosses the horizon at sunrise and for 2 minutes after it's already set. So we get about 4 extra minutes of daylight every single day, all thanks to refraction.
But our atmosphere doesn't just bend light, it also scatters it. And this scattering effect is the secret behind maybe the biggest question we've all asked at some point. Why is the sky blue?
So here's the deal. The tiny particles floating around in our atmosphere are just the right size to be really, really good at scattering short wavelengths of light, and that's the blue stuff. They're not as good at scattering the longer wavelengths, like red. You can think of it like blue light getting bounced around in all directions, while red light just passes straight on through.
So when sunlight comes pouring in, that blue light gets scattered everywhere, like a pinball, filling the sky from every single direction. When you look up, your eye is just collecting all of this scattered blue light from all over the place, which is why the whole sky looks blue to us.
So, there you have it. Whether it's the lens inside your own eye focusing an image, or a water droplet creating a rainbow, or the entire atmosphere painting the sky blue, it all comes down to the same thing, the beautiful, incredible physics of light. The next time you look up, you'll know the amazing journey that light took just to get to you. And knowing all that, what will you look at differently?
Hey there, and welcome to The Explainer. You know, electricity is this invisible force that powers, well, pretty much everything in our modern world. It's so seamless, we almost never stop and think about how it actually works. So today, we're going to break down the fundamental principles that make everything from your phone to your toaster even possible.
Think about it. You do it dozens of times a day without a second thought. You flick a switch, and bam, the light comes on. But what really happens in that split second? What incredible, invisible chain of events did you just kick off? Well, that's exactly what we're going to uncover, so let's dive in.
All right, to get a handle on electricity, we have to start with the most basic piece of the puzzle, the flow. You can think of it just like a river. A river has a current of water, right? Well, an electrical wire has a current of charge. So, what does that actually mean?
At its heart, electric current is just charge on the move. That's it. And we measure this flow in a unit called amperes, or you've probably heard it as amps. It's basically just a count of how much charge is zipping past a specific point in a wire every single second.
Now, to really wrap your head around this, let's use a simple analogy we'll keep coming back to. Water flowing through a pipe. In this scenario, the electric current, the amps, is like the volume of water flowing. So more water gushing past a point every second, that's a stronger current. Simple as that.
So just how much charge are we talking about here? Well, 1 amp is what we call 1 coulomb of charge moving past a point every second. And a single coulomb is made up of this many electrons. That is 6 quintillion electrons. That's an almost unimaginable number of tiny particles flowing through your lamp cord every second for just 1 amp of current. It's absolutely staggering.
Okay, quick sidebar, but this is a super important one. Back when scientists first started studying electricity, they had no idea electrons even existed. They just guessed, and they guessed that the current was a flow of positive charges. We call that conventional current. It was only later that we discovered it's actually the negatively charged electrons that are doing the moving, which means they flow in the opposite direction of what we'd already drawn in all the textbooks. So for historical reasons, you'll still see conventional current in diagrams, but it's crucial to remember what's really moving under the hood.
Okay, so we've got this sea of electrons just sitting in a wire. But what makes them go? They don't just decide to start flowing on their own. They need a reason. They need a push. And that push, my friends, is what we call voltage.
Now, the fancy technical term for voltage is potential difference, but I think it's way easier to just think of it as electric pressure. A source, like a battery or the outlet in your wall, creates this pressure difference. And as soon as you connect a wire, that pressure shoves the charges along, creating our current. It's pretty straightforward. No voltage, no flow.
Let's bring back our trusty water pipe analogy. Voltage is just like water pressure. Imagine you have a tall water tank. The higher the water level, the more pressure there is at the bottom. If you hook a pipe to it, that pressure forces the water to flow out. More height means more pressure, which means a stronger push. It's the exact same idea with electricity.
So we have the flow, that's our current, and we have the push, that's the voltage. But, in the real world, nothing moves perfectly without a little friction. There's always something trying to slow things down. In the world of electricity, we call that resistance.
Resistance is, well, it's exactly what it sounds like. It's a property of a material that fights back against the flow of current. As all those electrons try to zoom through a wire, they're constantly bumping and crashing into the atoms of the wire itself, and all those little collisions slow them down. We measure this opposition in a unit called the ohm. And to complete our water analogy, resistance is like a narrow, constricted section of the pipe. It physically squeezes the flow, making it way harder for the water to get through. A big, wide, smooth pipe has super low resistance, but a thin, rusty old pipe, that has incredibly high resistance.
Now here's where it all comes together. These 3 big ideas, voltage, current, and resistance, they're all connected. And they're linked by this one beautifully simple, incredibly powerful little formula. It's called Ohm's law. And it just says, voltage equals current times resistance. V equals IR. Seriously, this one little equation is the absolute foundation for understanding how almost all electric circuits work. Now, resistance isn't just about how thick or thin the pipe is. The material itself makes a huge difference. Every material has its own built-in property called resistivity. And just look at these differences. They're massive. Silver has crazy low resistivity, which is why it's one of the best conductors out there. Nichrome is way higher, which is actually why we use it in things like toasters. And then there's glass. Its resistivity is so ridiculously high that it basically stops the flow completely. It's a fantastic insulator.
All right, so we've met our main characters: current, voltage, and resistance. Now, how do we actually arrange them to do useful stuff? Well, it turns out there are 2 basic ways you can build a circuit. You can connect things in series, or you can connect them in parallel.
So, in a series circuit, everything is strung together in one single loop, one after another. That means there's only one path for the current to take. But in a parallel circuit, the path splits up, letting the current flow through multiple branches all at the same time. This one simple difference has huge consequences. For example, if you have a string of old Christmas lights in series and one bulb burns out, poof, the whole string goes dark because the single path is now broken.
So why should you care about this? Well, because your entire house is wired in parallel. Every single outlet is on its own separate branch. This means every appliance you plug in gets the full, powerful voltage from the wall. It's why your TV doesn't dim when the refrigerator kicks on. And most importantly, it's why if one light bulb in your house burns out, the rest of your lights stay on. It's just a much smarter, more reliable way to build.
We've talked about the push, the flow, and the squeeze. But what's the end result of all this? I mean, what's the point? What do we actually get from pushing all these charges around? The answer is energy. Hey, remember how we said those electrons are constantly bumping into atoms as they flow? Well, that friction, that resistance, it does something really important. It generates heat. The energy from the voltage source that's used to push the current through that resistance gets converted directly into thermal energy. And this isn't some kind of flaw or inefficiency, it's a core principle of physics, and it's something we use all the time.
In fact, we've brilliantly designed countless devices specifically to take advantage of this heating. That's all a toaster is. It's just a special high-resistance wire that gets red hot to toast your bread. An old-school light bulb heats a tiny tungsten filament until it glows white-hot and produces light. Even a safety fuse in your car is just a little wire that's designed to get so hot that it melts and breaks the circuit if the current gets dangerously high.
And this really brings us to maybe the single most important takeaway of this whole thing. The electrons themselves, they're already inside the copper wires of your house. They just kind of circulate around and around. What you actually pay the power company for is the energy, the voltage, the push to get those electrons moving and doing useful work for you, like creating heat or light or sound. You're not buying electrons, you're buying energy.
So there you have it. The flow, the push, and the squeeze. Those are the fundamental rules that govern electricity. From the simple act of flipping on a light to the incredibly complex grid that powers our entire civilization, it all comes down to these basic principles. So now that you know the toolkit, I'm curious, what's the most clever or ingenious use of electricity you can think of? Thanks for tuning in.
Hey there, and welcome. Today, we're diving into this hidden connection that pretty much powers our entire world, a secret link between electricity and magnetism. You know, it's a story that kicks off completely by accident, but ends up inside, well, everything, from your TV right down to your own brain. So let's start with a puzzle. What on earth could a tiny little battery possibly have in common with one of those giant cranes that can lift a whole car? The answer, in a word, is electromagnetism. And trust me, by the time we're done here, you'll see exactly how they're connected.
Our journey starts way back in 1820 with a physicist named Hans Christian Ørsted. Picture this. He's in the middle of a lecture, and he notices something totally by chance. When he flipped a switch for an electric current, a compass needle nearby just twitched. It seems small, right? But that was it. That was the first real proof that electricity and magnetism weren't two different things at all. They were deeply connected.
Okay, so to really get what Ørsted saw, we first have to kind of visualize this invisible force field that's all around a regular old bar magnet. You can think of it as the magnet's personal space, its zone of influence.
There's this super cool classic experiment that makes this invisible force totally visible. If you sprinkle some iron filings around a bar magnet and just give the paper a little tap, poof, the filings snap into this beautiful, distinct pattern. And these lines aren't just random squiggles. They are literally tracing the magnetic field, showing us the exact shape and direction of the force.
Yeah, these lines actually follow some very strict rules. They always flow out of the North Pole and into the South Pole on the outside, always making these complete closed loops. And see where the lines are all bunched up close together? That's where the field is the strongest. But here's the most important rule. They never, ever cross. And why not? Well, think about it. A compass needle can only point in one direction at any single spot. All right, now that we've got that down, let's circle back to Ørsted's big discovery. This is where it gets really interesting, because now we're going to see how a simple flow of electricity creates its very own magnetic field. So, unlike a bar magnet with its north and south poles, the magnetic field around a straight wire with current flowing through it is different. It actually forms these perfect concentric circles all around the wire. It's like the electricity creates this invisible magnetic whirlpool. And, just as you'd expect, the further you get from the wire, the weaker that field gets. So, how do we know which way these magnetic circles are spinning? Clockwise? Counterclockwise? Well, for that, we have this wonderfully simple little trick called the right-hand thumb rule.
Go on, you can try this right now. Seriously, just imagine you're holding a wire. Now, point the thumb of your right hand in the direction the current is flowing. Now, just curl your fingers naturally. The direction your fingers are wrapping, that's the exact direction of the magnetic field. It's so simple, so tangible, and incredibly powerful.
Okay, but this is where we can really start to juice things up. By changing the shape of the wire, a straight wire we know gives us those simple circles. But if you bend that wire into a loop, the fields from all sides start to add up, getting way stronger in the middle. And then, if you wrap that wire into a tight coil, what's called a solenoid, well, that's when you get something truly amazing.
This is the real magic of the solenoid. Inside that coil, the magnetic fields from every single little turn, they all merge together into one super powerful, straight, and uniform magnetic field. It acts exactly like a strong bar magnet. But here's the kicker. It's a magnet we can turn on and off whenever we want.
So we've just used electricity to make a magnetic field. The next logical question has to be, right, what happens if we take our wire with its current and its magnetic field and we stick it inside another magnetic field, maybe from a permanent magnet? What happens then?
The answer is, and I'm not exaggerating, the key to almost all modern technology. The wire experiences a force. It gets pushed. The two magnetic fields, the one we made with the wire and the one from the other magnet, they push and pull on each other. And this interaction, this push, creates actual physical movement. That right there is the fundamental idea that makes every single electric motor in the world spin.
And just like we had a rule for finding the field's direction, you guessed it, we have another rule for finding the direction of this new force. This time, we just switch hands. We use Fleming's left-hand rule.
Let's try this one too. Grab your left hand, point your forefinger, your first finger, in the direction of the magnetic field. Now point your middle finger in the direction of the current. If you do that, your thumb will automatically point in the direction of the resulting force or the motion. Field, current, force. It's just that predictable.
Okay, that's enough theory. Let's bring all of this stuff out of the lab and right into your home, because these principles are working all around you all the time. So remember our powerful friend, the solenoid? Well, if you take a piece of soft iron and stick it inside that coil, you've just created an electromagnet. A magnet you can turn on and off with the flick of a switch. And this brings us right back to our first question. That junkyard crane? It uses a gigantic electromagnet. It turns the current on, it becomes a super strong magnet, picks up the car. Then it moves the car, turns the current off, and it's just a regular piece of metal again. Now, to get all these powerful effects in our homes, we need a steady supply of electricity. In a lot of countries, that power is delivered at a standard of 220 volts, which is the push that gets the current moving through the wires. And that power gets to you safely through a system of 3 wires. You've got the live wire that brings the current in, the neutral wire that completes the circuit so it can flow, and then you have the earth wire. And that one is a super important safety feature that protects you from electric shocks if something goes wrong. But of course, this current can be really dangerous. Things like overloading a socket by plugging too much stuff in, or having a short circuit where the wires touch can cause a massive sudden surge of current, and that can be a huge fire risk. So, what's our first line of defense? The humble electric fuse. It's basically a little bodyguard for your electronics. It's got this special thin wire inside that's designed to melt and break the whole circuit if the current gets dangerously high, stopping the problem right in its tracks. And now for a final, kind of mind-blowing twist. This whole principle, it doesn't just apply to copper wires in big machines. It also applies to you. The tiny electrical currents made of ions that travel along your very own nerve cells, they produce their own incredibly weak magnetic fields. And these fields, as tiny as they are real enough that we can actually measure them with a technology you've definitely heard of, an MRI, magnetic resonance imaging. And that brings us perfectly full circle. It all started with Ørsted's accidental glance at a twitching compass needle. And from that tiny observation, an entire field of science and technology just exploded into existence. His discovery wasn't just some neat little fact. It directly paved the way for the technologies that define our modern world, from radio and television to fiber optics. You know, it all began with just one person noticing one small, unexpected connection, which really makes you wonder, if a simple flow of electricity can create a force that completely reshaped human civilization, what other invisible connections, what other hidden forces are all around us right now just waiting for another curious mind to stumble upon them? Thanks for joining me.
Hello and welcome. Today we're diving into a topic that, well, it affects every single one of us, our environment. You hear it all the time, right? That things are changing? But what does that really mean? We're going to find out just how connected everything truly is, from the tiniest microbe in the soil to the biggest forest on the planet. So, to kick things off, let me ask you a question. What on earth could a little fish tank on your desk have in common with a huge, sprawling forest? Sounds kind of strange, I know. But the answer to this question, well, it gets right to the very heart of how our world works.
And the answer is, they're both ecosystems. That's right. Whether it's a massive forest, a tiny pond, or, yeah, even an aquarium that we built ourselves, they all run on the exact same set of rules. You could almost think of each one as its own little world in a bottle.
So what is an ecosystem, really? Well, it's basically a community where all the living things, we're talking plants, animals, you name it, are interacting with each other and with all the non-living stuff around them. You know, like in a garden, the bugs and the flowers are interacting with the soil, the sun, the rain. It's a complete working system.
Okay, so every single ecosystem is made of two main parts. First, you've got the biotic components. That's just a fancy word for all the living stuff. The plants, the animals, even us humans. Then you've got the abiotic components, the non-living parts. Think temperature, wind, soil, minerals. And it's the constant dance between these two that makes the whole thing tick.
All right, so now that we've kind of set the stage, let's meet the cast of characters. See, in any ecosystem, every organism has a specific job to do. And these roles are what create the foundation for what we all know as the food chain. First up, we've got the producers. And honestly, these guys are the MVPs of the entire system. Green plants are the perfect example. They take sunlight and, through photosynthesis, turn it into energy, into food. They are literally making energy available for every other living thing. Next in line are the consumers. Now, these organisms can't make their own food, so they get their energy by, well, eating other living things. This group covers everyone, from the herbivores who munch on plants, to the carnivores who eat other animals, and the omnivores who, eat a bit of everything.
And finally, we have nature's unsung heroes, the decomposers. This is the cleanup crew. We're talking about tiny microorganisms like bacteria and fungi that break down all the dead stuff and waste. They are absolutely essential because they send all those vital nutrients back into the soil so the producers can use them all over again. Just think about that for a second. What would actually happen if all the decomposers just disappeared tomorrow? All the dead leaves, old trees, and waste would just pile up and up and up. The soil would run out of nutrients, and the entire cycle of life would just grind to a halt. It's kind of mind-blowing how important these tiny organisms are.
Okay, we've met the players. Now, let's follow the money, or in this case, the energy. In an ecosystem, energy is the currency, and we're about to see how it gets passed around between all these different roles. This is way more than just who eats who. It's a fundamental transfer of power.
So this right here is a classic food chain, a really simple, straight line of energy. For instance, the grass, a producer, soaks up energy from the sun. A goat, a primary consumer, comes along and eats the grass. And then maybe a human, a secondary consumer, eats the goat. See? The energy flows in one direction from one level to the next.
And each of these steps has a technical name. It's called a trophic level. So in our little example, the grass is on the first trophic level, the goat's on the second, and the human is on the third. You can just picture it like a ladder of energy.
But here's the real kicker. It's not a perfect transfer. Not even close. On average, only about 10% of the energy from one level actually gets stored and passed on to the next one. Just 10%.
So where does the other 90% go? It's just lost. It's used up as heat when organisms digest, move around, just live their lives. And because so little energy makes it up the ladder each time, food chains have to be short, usually only 3 or 4 steps long. There's just not enough energy left to support anything longer.
Of course, in the real world, things are rarely that simple. Most animals eat more than one thing, and they get eaten by more than one predator. So it's not really a chain at all. It's a food web, a super complex, messy, interconnected network of who eats whom. It's much more like a tangled web than a neat little line.
Now, this flow of energy has a pretty dangerous side effect. Because when organisms eat, they aren't just getting energy. They can also be swallowing harmful man-made chemicals that have snuck their way into the environment.
And this leads to something called biological magnification. It's a big term, but the idea is simple. Chemicals that don't break down easily, like certain pesticides, get more and more concentrated as they move up the food chain.
Let's just trace how this works. Imagine some pesticides from a farm wash into a nearby lake. Little aquatic plants absorb them. Then small fish eat those plants. Then bigger fish eat the small fish. At every single step, that pesticide becomes more concentrated, which means the creatures at the very top of the food chain, and yeah, that includes us, can end up with the highest, most dangerous dose of these chemicals.
This whole chemical problem is just one example of our impact. So let's zoom out a bit and look at two other huge environmental issues that have really been created by our modern way of life. First, let's talk about the ozone layer. Way up high in our atmosphere, there's this layer of ozone gas that acts like a planetary shield, protecting all of us from the sun's most harmful UV rays. It forms naturally, as you can see, but then we started using these synthetic chemicals called CFCs. They used to be in everything from refrigerators to spray cans, and these CFCs drift up there and just start tearing those protective ozone molecules apart.
But here's the thing. This story actually has a good ending. Once scientists figured out how dangerous this was, the world actually listened. In 1987, the United Nations got basically everyone to agree to stop making CFCs. And it worked. It's a really powerful reminder that when we work together, we can actually solve these huge environmental problems.
Okay, the second big issue, garbage. The stuff we throw away basically falls into two buckets. On one side, you have biodegradable waste, things like food scraps or paper. This is the stuff that decomposers can break down. But on the other side, you have non-biodegradable waste. We're talking plastics, glass, metals. This stuff can't be broken down, and it just sits in the environment for hundreds, sometimes even thousands of years. This quote really says it all, doesn't it? It shows how our best intentions can sometimes have these massive, unforeseen consequences. Take the simple disposable cup. It was introduced to be more hygienic, which sounds great, but nobody stopped to think about what would happen when we started throwing away millions and millions of them every single day.
And that really brings us to our final thought. From the intricate food webs to the trash we throw away, it's pretty clear our choices have a huge effect on the delicate balance of our ecosystems. So I want to leave you with a question to chew on. If our lifestyles are part of the problem, what single change in your own daily routine do you think could make the biggest positive difference?